All right, now let's discuss about metrics monitoring. So, metrics monitoring platform, ideally, what this their role is helps us to collect performance data. It can be CPU related data, memory data, throughput, latency from the servers and services, and stores it as time series data, and helps us to visualize it on dashboards, triggers alerts when something goes haywire, and like when thresholds are breached. So in real world, think like Datadog, Prometheus, or Grafana, or AWS CloudWatch. So those are the kind of platforms that exclusively help us with the metrics monitoring and all that stuff. So that's the at a high level what is the metrics monitoring platform. And now let's try to list down the requirements, breaking down into functional and non-functional. So requirements, first thing is the platform that we're trying to design should be able to ingest metrics. So here the metrics can vary from CPU, memory, latency, throughputs, from whatever the services that user is trying to build. So that is first requirement that we need to meet when we are trying to design the system. The second point is they should be able to query and visualize all the metrics whatever they want on dashboards in the various panels, ability to filter, aggregate, and based on time ranges and all that stuff. They should be able to do that using our platform. The third requirement is basically we should provide an option for them to define various alert rules, like with the thresholds, like or time windows and all that stuff. So basically it can be something like, let's say if a P99 latency is something going haywire, like greater than 500 milliseconds or 1 second, then we definitely know that there's something wrong for 5 minutes or 10 minutes. So then we need to know what's happening. So that is something they will define a rule, something like if P99 latency is greater than 500 milliseconds or 1 seconds for like 5 minutes window or 10 minutes window, give me an alert so that I can go and look which service or what server is breaking and resulting into this action. All right, so that's the third requirement that we should be able to meet. The fourth one is they should be able to receive notifications when such alerts happen. So we should be very proactive when something happens, and we should let them know either through their Slack channels or like pager duties or emails or whatever the channel that they configure. So these are like four functional requirements that ideally expected from the metrics monitoring platform. Now that functional requirements are clear, so here even if we want, we can think of like more of like log aggregation, full text search, or distributed tracing like spans and traces that we normally see in Jaeger, and anomaly detections if there is any using some or ML algorithms or AI integrations and all that stuff. But those are like good to have, but I'm just mentioning them. So now let's switch to non-functional requirements. So here this is very important, non-functional, because whenever we are trying to build kind of like infrastructure related problems, because the systems that we are going to monitor can range from a single team's servers or services to fleets of hundreds of thousands of servers. So getting the sense of the scale of the lower range and upper bound is very very important when we are trying to design a system, so that we know the bottlenecks exactly where and what we need to handle. So let's say like we need to design for monitoring 500k servers. That's very very big fleet. So at least assuming if each server emits maybe let's say 100 metric data points every 10 seconds, that's like nearly 5 million metrics per second at peak. So each data point assume is a small, like having like fields like timestamp, metric, value, labels. At roughly it can be like 200 bytes or so. Even if we look at that volume, it we need to store 1 GB per second. That's a huge data that we'll be need to support storing. That is very raw ingestion and all that stuff. So these are like, crux of the problem that we need to keep in mind when we are trying to design of that kind. So now non-functional, like I said, so we should be able to scale for 5 million metrics per second ingestion into our system, and maybe assuming we are managing fleet of 500k servers or more, and keeping these things in mind, we should try to build our system. And the next is basically whatever the dashboard queries that users are trying to make, on-call engineer or engineer responsible for monitoring for various panels in a dashboard, the results that we are going to return should be instantaneous, and they should not feel like they are waiting for something. So because they'll be asking for a span of days, weeks or months, so we need to be very efficient in scanning all the rows that we have over the period of the time, filter, aggregate and all that stuff. So very efficient querying is something that we need to design. And the third is basically the alert latency should be less than 1 minute window, so that they don't miss and it doesn't cost much for them if their servers are down, if the downtime is more. So these alerts, if something is wrong, we should let them know within the 1 minute of that incident happened. And the fourth point is high availability. Here basically we should not miss any incident capturing or metrics capturing. It's okay if we show stale data in their dashboards for a while, and eventually showcasing correct data, that's acceptable. But going our system down is something it's not acceptable, because this is the place from which they will know if their system is working or not. So this is not negotiable, and we should make sure that it's always highly available. And the last requirement is basically system should handle like late or out of order data. There might be like network delays and all the other problems are common, but still we should not miss that. But we should handle all of this edge cases and scenarios gracefully for whenever you're trying to ingest data into our platform. So these are the like core non-functional requirements that we are supposed to meet. And now that functional and non-functional requirements are clear, let's try to define the core entities that ideally we can think of when it comes to systems of this kind. So first is basically the label. So here it can be of a key value pair attached to a metric. So that lets us to even filter. For example, it can be like host equals to server 2, or region is some Asia Pacific or US East or something like that. So those are the things that we need to maintain. So those are called label key value pair. And the second entity is metric. So here this is more of a named measurement that we normally create with labels and value at point in time. For example, I can say CPU usage, host server 2, and region US East, US West is 0.75. So this is something metric that I am trying to look for, measure for. Same way we can have like memory usage or latency related stuffs and all that thing. So that's the entity that we need to have in this system. And the third entity is series. So series is basically the full sequence of timestamp comma value pairs for one specific metric plus label combination. So here same so CPU usage of particular host over time in one series, and CPU usage of another host over time in different series. So this is for period of timestamps, what are the CPU usage and all those things. So this is the for a particular time window, and that is this core entity which helps us to track, and that is the series. And the fourth one is alert rule, and this should be straightforward. So this helps the users to set particular condition that helps to trigger notifications when breached or violated. So it is going to be combination of the above entities like metric, query, threshold, and duration. It can be something like, if the average memory usage or average CPU usage in particular host, like US East or US West, is above 70%, 80% for 5 minutes, then user needs some alert so that they can know that if they have to spin up a new server, and if they have to do something else, is something they need to know. So that's the alert rule entity. And the final thing is a dashboard. So dashboard is a place where they will have collection of the panels, each displaying a query result as a chart or a table, so that they can monitor and see if something is going not according to their plan. So these are like core entities that we can think of when it comes to systems of this kind: labels, metric, series, alert rule, and dashboard. Fine. So this is the thing. And now that we know this core entities, at least rough flow, let's try to understand when it comes to systems of this kind in more infrastructure related stuff. So we assume user services or generate metric data points like CPU, memory, latency, and send them to our platform. The platform ingests. So ingestion is service, something that we'll see later. At a high level, I'm just trying to have a rough brief flow. It ingests and validates and stores metrics as something like time series data, and that storage is also something separate we need to take care of. And then user tries to now query those metrics through our dashboards, filtering and aggregations across time ranges. And same thing, alerts related services will be talking to our query service or storage and all that stuff. And when alert is breached, we might have something like separate notification or something which is responsible to send it to Slack, email, PagerDuty, and all that stuff. So that's like rough data flow. Now let's check on the APIs or system interface. So I think this should be pretty straightforward, and I'm just trying to be as simple as possible here. So here, mostly given the scale of this particular system or problem that we are trying to deal, mostly they won't be in JSON, or so they might be using like protobufs or similar binary format, because the JSON's payload size is going to pile up significantly, and it's something going to had a lot of latency again. So but for us for our purpose, I'm just have it in JSON itself here. So first endpoint is ingestion related. So here it's going to be post endpoint, so metrics ingest. So we get something like list of the metrics objects. So metrics objects can be something like it can be the name, CPU usage, and the labels attached with like host, server 1, and what's the value and the timestamp and all that stuff. So like this we might get the multiple list of these objects, and then we try to ingest into our system. So this is one endpoint. And the now second is basically we need a way to query metrics. So it can be a get endpoint. So metrics query, and the query params can be in the form of it can be in the its own DSL language, like PromQL or something like that. So average CPU usage in the region US East, and the start is like some time, and end is some time, and step or window like 60, and it gives us the timestamps, the list of all the timestamps and the values, so that we can use it to showcase it in particular dashboard or chart or something like that. So this is one endpoint to query the metrics and all. And the third endpoint is like to create a rules like with a particular threshold, so and store it in our DB or so. So it can be as simple as that: post endpoint, alerts, rules, and they create a name like memory usage, and query can be like average memory usage region US East, and if it crosses this needs to be triggered. So like for 10 minutes, and notifications when we need to send Slack, war room, or on-call channels that they usually maintain. uh, to handle all these kind of things. So these are like, roughly at least, brief endpoints that we can straight away think of. It's just the foundation, but let's see if this evolves as we go deeper into one point at a time, from functional and non-functional. So let's now take one point from the at a time from functional, and let's see how we can discuss or how it evolves as we explored. Okay, so first thing is should be able to ingest metrics. Here the CPU, memory, latency, other things from services. So the simplest thing that I can straight away think of is here. So let me yeah, so here assuming we have here servers, fleet of servers can be like 500k, 100k, 200k, whatever the servers that we have. So it just straight away consumes our post metrics endpoint, and we get the data into our ingestion service, and that service writes to our storage. So this is like, rough single system simple approach that I straight away think of to solve this. But the here we know the caveat here is 5 million metrics per second will definitely collapse this engine service and also the database, because they can hardly handle in terms of like 100k or so, but this volume is definitely going to collapse that. So now we need to think of like what are the approaches that we need to think of to support a scale of this kind. So first thing straight away is we can think of is scaling our ingestion service horizontally. So that's the thing. So I'll just try to add more instances of ingestion service so that let's say like if one ingestion service can handle 100k writes per second, so I'll try to add like 50 of them or something more of ingestion services, and I assume like now ingest service can easily handle. But this still doesn't solve the downstream problem, meaning still our database needs to face 5 million writes per second from different sources here, from all these different instances, and this is something our database is not going to handle, and it's going to collapse, and our whole system is going to go down. So this is something that we can definitely not choose to meet the first point. And the second approach that we can think is decoupling with the message queue. So here the approach is straightforward. So what we do is like we try to introduce a Kafka here. So this Kafka between our ingestion service and the storage. So here servers, whatever it is, they send metrics to our ingestion service, and with here we might have some validation checks, and then we do publish it to the Kafka topic, and maybe it might be partitioned by metric name, or like it can be like hash of metric name plus labels. So this now out of the box helps us to handle back pressure thing. So basically any spikes from the producer, Kafka helps us to absorb that, and while consumer can process at their own pace. So that's something back pressure handling is taken care by Kafka, and also like durability metrics are persisted in Kafka until it's consumed by some ingestion consumer or so, and multiple consumer partitions can process data in parallel. So here the efficiency is also there. So this is something that we can think of like decoupling with a message queue. But here this really adds operational complexity and latency. Typically still adds latency, maybe it can be in the range of 20 to 50 milliseconds. So, and also we need to handle consumer failures and ensure at least once delivery semantics and all that stuff. So the final approach that we can rely on is basically this is the standard approach that is being adopted even in the real world applications thing, agent based collection with the local buffering. So here so what idea is basically, instead of servers pushing directly to our central ingestion service, whatever we were thinking of, so what we do, like we run a small background process on each server itself. So often called, those are called like collector or agent in monitoring systems. So that gathers metrics locally and periodically we can use that to flush as a batches via Kafka and then consume in a regular way that we used to do. So this basically the collectors or agents or whatever, they do collect metrics locally at high frequency and buffers and batches metrics locally and flushed via Kafka into our system. So this basically now we are shifting completely to work at the edge, reducing the load on our main ingestion service. So now instead of we worrying about 5 million requests per second hitting our this ingestion service, since agents do work locally and we periodically flush, the request drastically exponentially reduce it to 50k requests per second or so, less than that. So this way we try to prevent that many kind of requests to our service and make sure that we do still meet the requirement that we are supposed to meet. So this is how we can meet the first functional requirements. And of course this basically this approach, it comes with little bit of overhead, like we need to add deployment complexity into our consideration, and also manage agent versions, configs and failures across like all the fleet of servers that we are supporting. But of course this is comes with the trade-off that really meets our needs, and we need to deal with that. So this is the first requirements and the approach that we use to meet. And now let's try to switch to second point in our functional requirements. So second point is basically should be able to query and visualize metrics on dashboards. So this is like how can we now where do we store, and like if the people are trying to come to our dashboards and they ask like show me the P99 latency for all API endpoints in USCs for over last 6 months or 6 hours, broken down by endpoint, that's like millions of data points that needs to be scanned, filtered, aggregated and returned in under a second. So those are the scales that we need to keep in mind when we are thinking to store where exactly, and if we store where, does this support this amount of queries or not. So obvious first thing that really comes to mind is basically we just try to store in our regular database that we normally use, store in a relational database. So and normally what we think is store each metric data point as a row in a Postgres. So table might look something like this: ID, metric name, labels, value and timestamp. And now whenever user is trying to query, I can just translate that into SQL something like this, like select time bucket 1 minute timestamp, and from metrics table where metrics is this, and try to filter and gives this. So here the challenge is at 5 million writes per second, Postgres can't really keep up, and that's the problem. The Postgres is not built for a scale of that kind. So this is not the ideal option. So we should choose the other option, which is the ultimate time series database. So here these are the database exclusively designed for use cases of this kind. So here InfluxDB, the timescale DB, or Victoria Metrics, or whatever the database of this kind, so we need to prefer. And so if we choose this time series database and all that stuff, its features really helps us to meet the numbers or the requirements that we have. So it has like append only writes, so data is written in timely order, and never updated. So this allows like append only storage engines with high write throughput, so we can do millions of writes whatever the per second or so. And then time based partitioning, so this is basically naturally chunked by time, so like hourly, daily. So like query for last 6 hours only touch recent chunks. So these are like literally helpful for us when we are trying to showcase charts in our dashboard panels and all stuff. And and then this columnar compression, so timestamps and values they really compress well when stored together. It often can compress from 100 KB to 5 KB or so. And then built-in rollups. So here this automatically compute 1 minute, 1 hour and 1 day aggregates. So this really helps us whenever we are trying to showcase the metrics for the users. So these are the features which really helps us to choose time series database, and that's why we decide to choose this timescale DB or so, and then query service talks to it, and dashboard gets its all data. So this is the second point, like where do we store and why do we store, and why we choose that, and that's the right place to the rollups really helps us, multi resolution rollups. So we'll talk more about what are the and all that as we go deeper into the discussion. So now the third point in our requirement is should be able to define alert rules with thresholds over time windows. So now we need to provide a way for end users to create a rules, so that we know if what threshold is hit, we should try to alert the users and all. So we can allow the users to register rules via an alerting API that we have discussed in our API system interface. So this is whatever user has created, we try to store it in our some simple relational database, can be Postgres, and then our alert evaluator service. So here basically this alert service we try to store in our alerts DB, simple alerts table or so in our Postgres. And once what we do now is basically we can do polling. A simple polling should do, because we have time window of 1 minute, so we keep polling 1 minute or so to our time series DB, and then check against the rules that we have in our DB, and if it meets, then we need to trigger an alert to the users that is this event is breached, and you need to have a look at this. So this is exactly how even Prometheus alert manager works. Alert rules are evaluated, whatever alert rules are evaluated on a fixed interval, like let's say default 1 minute, querying this time series DB that serves the dashboard. And it really works for most of the scenarios and use cases, and this is the approach that we normally stick to, polling periodically and checking against with the queries and checking against all the rules that we have, and if it's a match, then we try to trigger a alert to the users. And now the fourth point is basically they should be able to receive notification when alerts fire. So the first thing that we can normally think is we do have already alert service, and why can't we just call this Slack API and directly and throw in the message in that channel and let them take care of that. But we need to be very, very careful here. How do we really handle notifications? Let's say that if 100 servers or 200 servers are in the same cluster and all breach a same CPU threshold at the same time. Now we don't want to really send 100 separate messages in Slack or any PagerDuty thing. The on-call engineer or whoever is doesn't need their phone buzzing and it creating a panic situation for them, and he, by even looking at the notification, the numbers, he would be very worried. So that's something we need to have dedicated notification service in itself to handle all this, like grouping, deduping, silencing and escalations and all that stuff. So that is why we need a dedicated notification service here to handle all those things that I just mentioned, all this messy real world stuff. So here deduplication, for example, let's say our alert service or our alert evaluator runs every minute and the CPU is still above 90%. it really fires the same alert again. So without deduping, we send again like it has like a new alert to the Slack channel or to on-call engineer. So with this deduping, so we might track alert state, so that each alert either is it resolved or is it firing, and when alert event comes, we first check if it's already firing. If so, we just skip the notification and only notify on like state transitions, like when alert first fires and when it resolves. And that's the way, like, we deal with all this. This service helps us with integrating with this channels, and also maintain all this grouping, deduping, silencing, and escalations, and all that stuff. So that's why we need dedicated notification service. And this is of exactly even the other popular metrics monitoring platform that exists does in a way. So now we do have a basic system flow or design that really supports all our functional requirements. And I think we have like decent flow, or roughly. Now the most important discussions is all the bottlenecks that we have pointed out in our non-functional is something that we need to spend more time on. And let's take one point at a time from them and see what's the deep dive that we can see, and how can we achieve all the points that we laid on. So first point is the dashboard queries that we have should be extremely low latency, and should written in seconds. Like they might be asking for or weeks of data. So how do we handle like queries like show me CPU usage or memory usage for all pods in production over the last 30 days, 60 days. So this really touches billions of data points. And how do we typically deal with the scaling reads and all that pattern that we have? So the approaches, let's see what are the approaches that we can think of. So first thing is query raw data directly. So this is some new solution that we can think of. So what we do is like we'll try to store all metrics at a full resolution, that is 10-second interval. So for every 10-second what happened, so the data points. So we do like query database directly for each dashboard panels, and then we show it directly in each of the panel. So but here the bottleneck is, let's say like we store 10-second intervals resolution in our thing, and 30 days is approximately 250k plus data points per series. So 30 into 24 into 6 multiplied by 6, that is 10 seconds interval. So 60 by 10 is 6, so it's around 250k plus data points per series. So if we have 1k plus pods, that's like 259 million rows to scan, filter, and aggregate. So even if each row is 100 bytes, so 225 GB of data for single dashboard panel. Imagine each dashboard will have like 5 to 6 panels at least. So it's a nightmare, and this is going to take minutes if not seconds to return the results to the dashboards. So definitely this is not the way or the approach that we need to take. So the other approach is basically pre-computed roll-ups at multiple resolutions that we can think of. So here the idea is basically we need to store at multiple resolutions, like time granularities. So meaning how much time each data point covers. So for example, here the parallel comparison can be like, let's say Google Maps, the every zoom in that we do, if we zoom in extreme to the area that we live in, we can see the buildings, flow, roads, and exactly and all. But if we zoom out a bit, then we see only the place name and all this. And again, as you keep scrolling, zooming out, you see only the states and the main cities and all that. Similar way, this is like multiple resolutions. So how much time each data point covers. So row can be like 10-second intervals, 1 minute roll-ups, 1 hour roll-ups, 1 day roll-ups. So ideally nobody so like 10-second intervals, we can just keep it for short period of time, like 2 days, or 1 minute roll-ups can be like for 2 weeks, 1 hour roll-ups can be for 90 days, and 1 day roll-ups can be for 2 years. So here typically why second intervals, short intervals are kept for less time, because nobody comes and asks like show me like every second's metric for 6 months and all. They just need to know if how good the last month was, and how bad the last week was, and all those things. That's why like day roll-ups or 1 hour roll-ups we do store for a longer period of time, and whenever they try to query, we just use these roll-ups and show. So basically when a query arrives, mm, when this query arrives, the query engines will select appropriate roll-ups based on the time range and the requested granularity, and we just return that and accordingly showcase it in our dashboard. So basically most time series database that we just normally discuss, they come up with a default support for this rollups, and we don't have to worry much about this. So if not, then we need to think about like background process to periodically compute them, and need to our query service need to handle queries at different resolution and all that stuff. But like I said, it mostly comes up with the default support in our time series database, and that is taken care. So that's how like at least we can think of to have faster queries for our dashboard. So pre-computed rollups and multiple resolutions, which is like default feature in time series database. But here the thing is rollups are lossy sometimes. So again, so the final approach is caching a layer and query splitting. So here what is the idea here is basically, if you really think, the most queries that we get are covering the same data, like sliding window problem. Queries that are separated by like 10 seconds are covering almost completely overlapping data. Only difference is might be the last 10 seconds or so. So to take advantage of this, we can add a cache here, the Redis layer. So where we store all this pre-computed or partial results. So query splitting can be like something like breaking like let's say like 30-day query into chunks. Recent data, the last 2 hours, we can directly query our time series database for freshness. But historical data, whatever we have, we can just look into the cache and get that thing. So and also mostly the dashboard queries, like popular dashboard queries, are identical and are pre-computed and scheduled. So since they are pre-computed and scheduled and are identified well in advance, so they can be cached with the TTLs aligned to data freshness requirements whatever they have, and whenever they wanted to see the data in the panel, they can straight away query Redis, and which really gives results in sub 100 milliseconds or so. So same thing, that's why we have this caching layer plus query splitting to time series DB for freshness and for historical to cache. And this is how like really helps us to give us the real-time data as well as the historical data, both balanced. So that's the like approach that we ultimately take to meet the latency requirements that we have for our dashboard queries. So fine, and now let's jump on to the second point discussion. So here the alert latency should be like less than the 1 minute window that we normally have in our requirement. So first thing straight away is like increase the polling thing. So I'll just increase polling frequency now. Instead of doing it for every 1 minute, I'll do it like 10 or 15 seconds instead of minute, and then I can just let the users know alert within like 10 to 15 seconds instead of like waiting for 1 minute and then letting them know, because or so mostly it works. But let's say like we have around 10k rules in our db alerts db, and at 15 seconds intervals or 10 seconds intervals, roughly around 700 queries per second. That's okay, decent. But even like 15 seconds or so sometimes can cost significantly for the companies that they can't tolerate. So even 14 seconds of latency is something not tolerable for them. So in that case the other approach is basically streaming the processing for real-time alerts with like stream processing frameworks like Flink. So this, what we do is, here we introduce a real-time alerts Flink as one of the consumers from the Kafka. So it reads metrics from this Kafka, same topic, whatever the ingestion consumer was reading from. So now for each metric series, this Flink, what it does, it maintains in-memory windowed state. For example, a rolling 5-minute buffer of values or so. Now that it maintains that, and whatever the alert rules that we have, they need to be compiled and converted into like Flink operators that continuously evaluates the conditions against this in-memory window that we are trying to store. And whenever a threshold is violated or breached for that configured duration or so, then Flink emits an alert event through our notification service. So this basically helps us like now not just waiting for the polling, but so we straight away as our data arrives, we just let the users know if it's an issue or so. So that's like the thing here is basically we need to add Flink, which really adds operational complexity, and also like alert rules, whatever we were storing in db needs to be translated into streaming operators. And when users update rules, we need to simultaneously update our Flink operators as well. So here also like checkpointing is also very critical, so that we don't really lose track of in progress alert evaluations or so, if some for reason Flink goes down. So checkpoints is also very very important. So yeah, this is like as data arrives, we let the user know if it's something's awire or not. So this is how like like we literally for real-time alerts we rely on this stream processing frameworks like Flink or so. So with this approach, we meet this alert latency both basically in most real situations. They use hybrid, a combination of this polling and then this stream processing. Only for the critical things they try to choose this real-time stream processing using Flink. Else mostly they stick to this polling approach, because engineering standpoint it's easier to maintain as well. And every approach has its own trade-off. So that's the second point that we meet with this approach. And the third point now is high availability. So basically, especially during heavy traffics and spikes, and how do we handle that spikes, traffics and failures. So here this is going to be simple the SREs DevOps real standard servers configurations and scaling stuff, which mostly these days are handled out of the box by K8s or others thing. So here we have two separate paths. One is metrics ingestions. Can we keep collecting and storing data even during failures? And second thing is alerting and notifications. Can we still detect and notify when things are breaking? So these because if the monitoring system goes down during an incident, we are blind and at the exact moment where users are, we need visibility, right? So that's why high availability really matters a lot in systems of this kind. So the first thing is very blindfold approach, so single instance ingestion and alerting. So here what we do, we just run only one ingestion service, one Kafka broker, one time series database node, and one alerting service. So alerts write directly to Slack or PagerDuty. So we know that if we do this way, so that is a classic single point of failure, and we can never rely on systems of this kind. So the second approach is basically redundancy plus durable buffers. So what we do here is, like, we know now each stage. What we try to do, as we know multiple stages, we will try to make each stage as redundant as possible, and add durability wherever we can. So for example, let's see, like, let's take ingestion. So here we can have multiple ingestion service instances behind some load balancer or so. And for Kafka as well, like, we can have replicated partitions with leader election and also. So for storage, same time series database I can have with replication and multiple node writes and all. And alerting, I'll have multiple Flink consumers, not just one alert, a single consumer in a single consumer group. So, and then notifications, we'll have alert service to keep on retrying, and queues failed ones, so that until unless we have one delivery, we do this stuff. So this here is basically key improvement that we see is buffering. So even if the database is slow, Kafka can observe the spike, and even if consumer fails, another consumer in the consumer group can pick up its partitions. And even if the notification provider is down, alert service keeps retrying and queues failures until it recovers. So here we are buying here the buffering, and that's really helps when we really want to guarantee high availability. But still, redundancy, whatever we are talking about, really doesn't eliminate the failure modes that we can think of. So even if Kafka falls behind for too long, the retention can expire, and we really lose data. So, and alerting is delayed, and then we send issues late to the users, and all that stuff still keeps haunting us if we even choose this approach. So now the final approach, at least we can go with, is basically end-to-end high availability for both data and alerts. So here what we do is, here we'll try to keep the design simple but make every step resumable, like, I'm making idempotent and then reconciliation. So here in the ingestion path, so what we do, agents, we know that collectors or agents buffer locally, and we try to retry if the network or ingestion layer is down. And then for Kafka stage, we make sure that it's replicated across zones, so even a broker loss doesn't really drop data. And make sure that writes are idempotent, and so retries don't create duplicate points or so. And that's how we take care in the ingestion path. And the alerting and notification path, we make sure that alert evaluation in our Flink or so is checkpointed. So even if that Flink processor or so crashes, we can resume from the same checkpoint we had maintain that state. And then alert events, also we can try to write it to Kafka before any external notifications, so that they can be retried if something has been missed. And retries delivery to secondary channel and all that stuff. So this way, at every layer, at every stage, and in every path, we need to make sure that all the possibilities of making sure high availability is guaranteed. So this is something how we make sure that high availability is guaranteed. So that's how we made this point that we have high availability. And now let's move on to the next point. So here is handling this cardinality explosion. So here, this is something very important. Here the problem is, here We know that every unique combination of like metric name plus labels creates a new series. Let's take an example like metric, like HTTP request, host, region, endpoint, status code method across like let's say 1,000 hosts, 5 regions, 200 endpoints, 10 status codes. Maybe let's say 5 HTTP methods could at least reasonably produce 50 million unique series in theory. So in practice it's less, but it really grows fast, exponentially and unpredictably. So why this is a problem is basically on the right side, for ingestion service into our storage, each series has overhead in the time series databases, indexes, metadata, in-memory tracking. When series count explodes, write performance into our DB degrades and memory usage spikes. And the read side for our query services, if we wanted to aggregate over a large number of series, let's say like if we wanted the total number of HTTP requests, we need to read and aggregate every series, adding up 50 billion series is going to take a lot of time. I'm just quoting this ballpark number, but huge numbers really is going to take a long time. So that is why this cardinality enforcement is very very important. If we add as a step to our ingestion service. So here what we do, we try to introduce that between metric validation and this Kafka publish. So now it requires two pieces. So we alerts DB, whatever you have, let's say one common database for alerts and policy things. So policy store. So what we do here, we try to map each metric name whatever we have to its allowed label keys. And also the maximum series count and per label value limits. For example, let's say HTTP request might allow labels only like host, region, endpoint, status code method, with a series cap of let's say like 500k. So that's how we try to limit the cardinality explosion. And this cardinality tracker, ideally it's the Redis, also the fast counter that tracks how many unique series exist per metric, and when ingestion service sees a new data point, it first checks the label combination if already exists per metric name. If it's a new series, it checks against the cap whatever we have in our policy DB before accepting this. So this is how to at least think of like rough flow. Data point whatever we have arrives at this ingestion service, and we strip any label keys not in the allow list, and then hash the remaining labels to get the series ID. So now once we have the series ID, I check this Redis to see if this series already exists. So if new, I check against this new metric series cap. If under cap, I just accept and publish it to the Afghan, and then regular consuming and all everything happens. If over cap, and then what I do, I straight away drop and increment this dropped metrics counter in whatever cardinality tracker that we are maintaining, so that at least if whatever the metrics that we are dropping, if we also keep track, we can let the team know like what are we dropping, and let them take care like should that be dropped or should that be considered later. So so that's how we normally brainstorm and think through, and then finally agree on to one approach or solution. So this is how the end system design is going to look like. I know a lot of things are not that clear, but still the intention is always to get the brief idea of how we navigate over situations of this kind. Hope you got something at least from this, and maybe at least you took a couple of points and learned something new. Let's catch up in the next one. Right. Now let's talk about ChatGPT or Claude or Gemini, the similar products that we normally use. So we all know what this ChatGPT is. Basically the conversational AI product where we as a users send prompts in natural language and expect the responses streamed back to us
from the frontier models that they are building. So those are like the core functionality of this product. And then conversations whatever we have with them are saved, and then we can just go back and take a look and then pick up from wherever we left off in that specific conversation. So that's the ideal the core functionality of that product is. So now that what it does and everything is clear, let's try to break down our requirements into separate categories: functional and non-functional. So let's see how we can break them down, and it should be simple and straightforward, because these days everybody is a part and parcel of our work that we normally do, so of consuming these products. So first thing is basically should be able to send a prompt in chat and then receive the AI generated responses back. So that's the first core requirement that we should try to make simple. That's the important trait that we need to take into consideration as a first default priority request. And then the second is basically user should be able to view past chats whatever he had in that platform, and then try to resume that conversation, and also maybe able to attach that chat's prior messages as a context into the prompt whatever he's trying to ask for. So basically it's something that we remember and it's not forgotten whatever you had discussed in this chat conversation thread or so. So those are two primary requirements we will try to focus on, and we can still add other things we normally see now. We have editing of existing messages or branching existing messages, and then not just text input and text output, maybe taking in images, audios, videos, and then sharing chats, collaborating on a chat, and then custom GPTs, tools, function calling, all the web browsing, then the whenever we want to look for all the previous charts that we have, full text search against all whole history of charts and all, those are normally that we normally see in those platforms as we are using every day. But but these are those are add-ons, but these are two core functionalities that we'll try to focus on this. So that should be simple and straightforward. Now let's think about on the non-functional. So this is where most of the discussion or the effort or emphasis has to be laid upon. First is basically low TTFT. So basically time to first token. So whenever user tries to ask something, so what is the time it takes to for us to send a first token or so. So that should be very fast, and it should feel instantaneous for them, so that it's a better user experience on our platform. So that should have upper bound of no more than 500 milliseconds, and that is hard tolerance, and then after we give first token, then the continuous streaming, smooth continuous streaming is something also that we should guarantee. So that is first non-functional requirement. And the second basically is we should try to prioritize availability over consistency. So what does this mean? It's better to return an error or something spinning, loading, degraded experience than to block the old systems on whatever the chart state that has been synchronized in his history or so. So that's why the second priority, preferring just availability over consistency, that's fine. That's the trade-off that we are trying to go with. And the third is basically we know that the inference and all, it's a very expensive operations that needs GPUs at a scale and all. So even at assuming at a scale at which those systems receive traffic, so ideally at the, let's say they have roughly around 200-300 million daily active users. So let's say at peak they receive around 20-30k prompts per second. So that's the thing they need to handle using the GPUs whatever they have with them. So that's the basically the constraints at which they have, and with that they need to handle this traffic. And also the peak traffic is 20k prompts per second. let's say like they have 100k or 200k concurrent in-flight streams. So those are these numbers that I'm trying to lay down, and even during such high constrained situation, that system should scale well and should deal with starvation problem and fair allocation across users. So that's the core non-functional requirements that we'll try to deal with. So still we can come up with more list, maybe all this monitoring, logging, alerting, authentication, then durability of the whatever the token that we have streamed and all everything, though we process the final message in our the relational database. But what about the stream token if something goes haywire in between? So that's like non-functional requirements. So now that requirements are clear after breaking down into functional or non-functional, let's jump on to the code entities. So I think this should be straight and clear. We know the code entities normally in systems of this kind. First is like basically an user is nothing but the account on the platform, free tier or paid tier, which is what the entity is. The chat, then chat is basically single conversation thread which just belongs to one user. Basically it's just a grouping an ordered sequence of messages which has title and timestamps and all that stuff. So that's the second core entity. And third is a message entity, and that is like one turn in a chart, either a user prompt or an assistant response. So that's like normally we see the user prompt or assistant response. So usually what it carries with, like chat ID and then the role, mostly it is user or assistant, the content and the token count that each message is having with. So this it will evolve eventually as we discuss, kind of like generation or so. I'll elaborate more on that. For time being, to begin with, to start with, these are like 3 entities I think should be enough to meet the requirements that we have laid down above. Now that core entities are clear, let's now think about the contract or a system interface and all. The first thing is basically we need to expose an endpoint for an user to create a new chat. So that is going to be simple post endpoint, because what we are doing is just creating a chat entity. So that might look something like this, slash charts, and then body we might take something chart name or title or other stuff, but I'm just leaving it as a black box, or any other metadata that we wanted to collect. So once we take those things, we create and then return the chat ID. So that's one endpoint we can think of just to create a new charts. Then the second endpoint is basically, now that chat is created, the user should be able to start conversation in that thread. So now the endpoint to send a messages. So that is again post endpoint. So it might look something like this: charts, chat ID, messages, and here it will be the actual content that the prompt that is trying to send. And once he sends that, we'll try to send the message like stream of tokens via SSE. We'll talk about how the response and how we generate and all that stuff later. But this is like rough skeleton of the second endpoint, like sending a prompt and the stuff. The third endpoint is basically now he has assumed like he has built a conversations and everything on our platform. Now you want to see a list of all the charts in the sidebar history that we normally see in the platforms. So that's the third endpoint. So able to get the history of the charts that he had in our platform. So this is going to be a chart, so it will be cursor paginated thing. So we'll just take the cursor and limit it by things, and then later return the list of the chart entities. So that's going to be simple third the endpoint. So that's the like get charts. The fourth endpoint is basically, it's going to be again once he sees list of the charts and he wanted to view a specific content part of that chat. So when he clicks on that, now we need to be able to retrieve all the messages turns in that specific chat ID, and then showcase in the chronological order in which he has conversed. So basically sequence by timestamp, getting all the latest and flipping it out so that he'll see whatever he had seen before before while he was trying to converse. So that's this fourth endpoint, getting a chat. So here we'll just try to take in here the chat ID, and it might look something like getting the messages of that chat ID. And again, this also will be cursor paginator because it might have 50 tones, 100 tones in that specific chat. So we just want to limit, and we don't want to get too much of a data at a single request. So this here also will try to follow cursor pagination. So take in a cursor and limit, and then it returns the list of the message entities. So these are core endpoints that we can think of, though the additional things of SSE connections and all that stuff, we will think of the things. And other things, basically taking in all the security related details. Basically user ID will never ever consider in query params or the body. We always take it from the session token or JWT, and the chart ownership, everything will be checked on server side on every request, and make sure that we respect that. So these are 4 core endpoints that we need to deal with. So the APIs or system interface, that's the thing. So now that we are clear of overall contracts that we are supposed to expose, so that it can be consumed in our platform or so, let's take now one functional requirement at a time from our requirements list, and then elaborate more on that. So that's the eye level design. So first thing we have listed down above is basically should be able to send a prompt in chat and receive AI generated response. So what we will do here is basically we will not think about the scale or the numbers or the anything that we have. Let's try to have a clean components, at least to get the initial flow, initial functionality to work. Doesn't matter of user experience and all that stuff. We will elaborate more, but it's better to have a working system than a perfect system which might never be built. So here let's try to break down that thing. So yeah, first thing, I'm just tying it up. So simple, it should be simple and straightforward, because normally every day we use those products. So when a user opens a chat or so, he types a prompt and hits enter. Client sends that prompt to our backend, and eventually somehow we do something in our black box services and send a response back. So let's that's a minimum component. So your first is basically client. So it can be in a browser or mobile app or whatever, wherever the user types, and it tries to read the responses. The other thing is the API gateway. We all know it's an entry point for all our client requests, as a gate to all our services that we have. So this is where we try to handle authentication, routing, rate limiting, and all the stuff. Middleware normally will take care of that stuff. So that's the API gateway. And now this chat service, so keeping it as a stateless. So basically what it does, it just owns the chat and message persistence and orchestrates the calls to the model, where it can be separate inference service, which is the other component. And so that if we keep this as a stateless, it's easy to scale it horizontally, which really matters when we wanted to scale it independently at a peak traffic time and all that stuff. And that is this chat service stateless. And the other thing is basically the persistence layer, the Postgres thing. So here right now we have here 2 tables or so. This just the chats and messages, straightforward. Chat ID created at whenever user tries to create a new chat, and the messages each turn in that chat. So message ID, chat ID, role, content, and other metadata, whatever we wanted to. This is persistence layer that we'll try to have. Either here we can use Postgres or any database that is okay with you. And the other is basically the inference service. So this is where the actual model inferencing, serving token generation from the model happens. So here we'll have cluster of GPU model workers that actually run the frontier model that particular lab owns. So and here we'll not discuss any of that. So we treat this all itself as black box. We just assume that it takes in a prompt and returns a completion for us. So this is basically very expensive part in whole of the system, and that's why we completely separated it from chat service, so that this can itself scale on its own. So yeah, that's now that we have this the all components interconnected. The flow is simple. In the client side, the user types some specific prompt and sends a post request through this API gateway, chats, chat ID, messages also. This API gateway, now what it does, authenticates the request and forwards that to our chat service. So this chat service, what it does, it writes this user message to this messages table whatever we have in this database, and after that it makes a synchronous call to inference service, which runs the prompt through the model and returns the full completion once it's done. So once it gives that full response, we write that message assistant back to messages table, and then we will return to this client. So that's basic system that we're trying to connect all the components and at least have the the overall functionality working. Fine. This is, we know that this is fully synchronous. When a client sends some request, he has to wait 30 seconds blank, staring at our screen to see the full response and all. I know this basically doesn't really meet all our TTFT requirement and all the requirements that we have laid down, but the intent of this is just to lay out the basic flow and the sequence, and we will try to tackle all of these points as we elaborate more into our deep dives. So but this is how we try to meet the first requirements. So now that we have at least for now it just works for our first requirement. So let's take in the second requirement and try to see now how we can elaborate this to meet that. So the second one is basically user should be able to view past chats and resume conversation with the context that we inject into prompt along with the latest message that is trying to send. So that's, I think this is going to be simple just thing. It's just this chat service will try to handle that read path for past chats and also the context injection into prompt, everything on the next one. So this is what chat service itself will try to make it handle that. So simple, we had get/charts, so that basically returns the user chats ordered by recent activity, cursor paginator like we discussed in our system contracts thing, and we'll just try to show in the sidebar. The other thing is trying to get the messages. Again, we had the endpoint chats, chat ID, messages. We'll just try to get the all chats messages for that chat ID and then showcase in that respective opened chat. That's the now first, at least the reading of charts and all that thing. The other thing is now context carryover. So here what we do is basically this chat service whatever we have, it tries to queries this messages table whatever we have in our PostgreSDB. Just we try to get that ordered by creation time, and then we once we retrieve all of the message of that specific chart, we'll try to build the prompt by injecting this context or messages along with exactly role of that message. Is it users one or is it assistant one, followed by the latest user message that is trying to send, and then all that combined prompt is what we'll try to send it to our black box inference service, just like our first one. And then the new assistant message whatever we get, we write it back to our messages table, and again the next one can read it accordingly. So that's how we try to take care of this context carryover. That's the simplest thing that we normally think of as a naive approach or whatever it is. Now we have at least the chart history showcasing, and also the models able to see old conversation every turn. So it behaves it remembers and it has memory and all that stuff. But we know that sending full history every turn as huge problems. So as conversations grows, context window is we have always the limit on context window, so and it gets more expensive because here the build is per input tokens, and so that we'll see like how we can tackle with summarization and prefix caching and all that things. But this is like basic working system meeting our core functional requirements. But the real discussion, the real elaboration is what comes in our deep dives, taking one non-functional requirement at a time, and the things that we normally laid out here, the bottlenecks, we'll try to elaborate more on that. So first, now the deep dives. So first thing is basically streaming tokens back fast to the users. And once we send the first token, and how do we ensure the rest of the tokens we smoothly stream them as well to the users. So we know that our synchronous design above makes the user wait up to 30 seconds or so, whatever, blank screen to and get the full answer and showcase this. That's like very very bad experience that we can provide to the users. So now let's try to see how we can try to mitigate that and provide the better user experience on our platform. So first is, let's try to see first point, time to first token. How do we reduce, or how do we handle that? So the approaches that we can think of is basically first thing is we can think of a straight away is polling for chunks. What do we do here is ideally the client, whatever the mobile or web, it just fires off the prompt, the initial message that user has sent. So then we'll have a polling endpoint that will try to poll every few hundreds of milliseconds, asking if there are any tokens. So then the server tries to answer whatever the tokens that has been generated since that last poll. So this is just the what we do. The tokens produced by this inference service, we try to write it to db, some table here, messages table, and then this chart service tries to read that token from db on like every hundreds or 200s of milliseconds, and once that is received, we send it to a client. So this is the simplest approach that we can think of. But here you see that the latency that we guaranteed in our non-functional requirement, it should be in less than of 500 milliseconds or so. So this is definitely not meeting that, and it's ideally gated by poll interval. So we might decide we have a poll for every 1 second or so. So that is itself like not meeting core requirement, and also it's a very very bad experience, lumpy experience. So because we are not streaming token by token, it's like batch of tokens that we got from the inference service and showcasing it to the user. And also imagine the scale at which we are building the system. So at 400k plus requests per second, 100k of concurrent streams, polling every milliseconds is basically that many of requests hitting our server. So this is something it will all overwhelm our the servers, and it doesn't really serve the need. So this approach is something polling is strictly no for our use case. And let's see what is the other approach. The other approach that we can think of is basically WebSockets. So here now, instead of this client asking again over and over again, so what we do, we try to establish one persistent connection and let the server push tokens the instant the inference service generates. Now what happens is basically we have a full duplex channel that stays open for the lifetime of the generation that inference service takes care. But the problem here is basically we'll talk about the problem. So here basically the chat service, that's fine, we established WebSocket connection between client and chat service, but what about the between inference service and the chat service? So that's where like gRPC kicks in. So it really helps in with the service to service calls, which really runs over HTTP/2, where that's where like it helps in with the binary framing and also like multiplexing, plus like we have typed contract from protocol buffers and all, that's that thing. So that really helps to instead of making every HTTP call, what happens is just we make a single call to the worker, and worker streams back a sequence of messages over that open connection and one token at a time until the full generation is done. So this is how like between HTTP between chat service and the inference service, we try to establish that connection in that way. But now you see here, that's fine, we have at least decent, and this really works fine, and we sorted out the connection between chat service and inference service, and connection between the browser and the chat service. But here if you really observe, it's the two-way bidirectional is not needed. We know WebSocket is bidirectional, basically when client is sending continuously and the server is also sending continuously. Maybe better use case for chatting or other stuff like WhatsApp and other stuff. But here we need only push one way, that is server needs to send only, not the client. So for that use case, we know the best ways to stick to server sent events. So that's the the third approach, and that's the one that we normally stick to. Basically they are purpose built for one-way server to client streaming. So what we do normally, basically the client opens this ordinary request with an event source that we normally have. Then the server holds that response open and keeps writing the events like data events to it as tokens are produced by this the inference service. And once we send that, browser files an event and then it streams the tokens to the users as real time. So that's the thing. And also by default we have like few advantages, like event source API reconnects even when if by chance connection drops. So that is also like something good point that we normally can leverage from. So basically SSE and gRPC really helps us with the time to first token to meet within the latency bounds of like less than 500 milliseconds and all. So that is the how we'll try to design to meet our first requirement. And then let's now break down to the other requirement. The other is basically once we generated or streamed the first time to first token, so now the rest of the tokens in that generation, how do we ensure that stream is smooth? So that's the thing now. Let's see, and make sure that it's not unbroken from the first token to the last. So the first thing that we can normally think of is, so why I'm saying the rest of the tokens needs to be smooth, because if you look at closely, we are just assuming that we have one fixed server that reliably sits between this user and the model for full 30 seconds. In reality, that's not the case, because we know that our chat service is stateless and it's originally scaled behind a load balancer. So it's redeployed all day long, we push some updates and there might be some crashes. So new pod keeps coming up and old pod wins down and all. So the moment we understand and try to think in this direction, so now how does another token actually get from the worker that it produced over to that new chat service instance is creating, and how does it hold its users SSE connection and all those things. So now what happens to the stream that we are normally showcasing to the user when that instance that was tied to users SSE is replaced mid-generation or so. So that's why that is why the separate emphasis on this thing. So let's see, the first thing that we can normally think of is basically we'll try to pin that connection to one server only. So this is exactly what we have currently now. So we'll just assume that this is the chat service instance that owns the entire flow, and it holds the gRPC stream, worker to worker on one side, and then SSE connection on the other. So it's responsible for complete full generation is what we guarantee. But this, if that is the case, it just completely goes against our stateless chat service type. So here now this we assumed in the first place chat service to be stateless so that we can independently scale, but now we are tying up to users SSE connection and then the generation from the model side. So that's like something against our requirement. So this is something that we can not definitely go ahead with. Now the other better approach is basically we can try to decouple with Redis PubSub. So now the thing is we need to decouple it anyway. So what we can do, we'll try to put something in between chat service and the inference service. That is where this Redis PubSub comes in picture. So what do we do is basically we'll try to key it by run ID when the generation starts. So this inference worker will try to publish each token to the channel for that run ID. The key might look something like run ID, and whichever the chat instance is currently holding that SSE connection will try to subscribe to this channel and forwards that token down to the browser. So basically now we introduced a layer in between both of them, Redis PubSub, and inference service publishes to that channel keyed by run ID, and this chat service will subscribe to that run ID and stream whatever tokens has been generated to the client. So that's how, like, we try to take care. Here one thing is basically whenever we try to publish each thing to Redis PubSub, it doesn't publish it as a full text like whatever is generated. We always publish it as a delta so that the memory that we need on our Redis PubSub is minimal, and also now because that's something like let's say like we have like 4000 token answer. We don't want to send 4000 tokens every time whenever we wanted to. We just wanted to append it things. So text delta, and whenever we wanted to read it, we just read that last sequence text delta and then try to stream it to the user. So that's one thing. This is Redis PubSub, but we do have challenges here as well. So what is those problems? So the PubSub, whatever we are discussing, the deltas for Redis PubSub, that is like fire and forget thing. So it delivers messages to the subscribers, to the ones that are connected at that instant, and if by chance assume that our chat service instance it dropped, crashed us due to some memory or CPU issues, or we are rolling out some feature fix or bug fix, and new pod is spinning up, then even in that window we lose that whatever the inference service was publishing to Redis PubSub. So this is something that we need to worry about. So basically user might miss few tokens in between, and that might be something not meaningful whatever user is seeing on the screen. So this is something we need to have something capability of replaying it back. So that is where the other feature in Redis, basically introducing Redis streams and Redis replay instead of the PubSub. So we'll just keep that same decoupling, run ID, key channel and everything, but instead of with PubSub we'll just swap with the Redis stream. So which is Redis stream is simply an append only log that actually remembers it entries. So the worker, whatever it is, will just do x add each token delta to the stream for that run ID, whatever the key that we have. Then this chat service, whatever we have, it reads with a blocking x read starting from the last entry ID, this client has already seen, and forwards the new entries down the SSE connection to the client. So that's how we make sure that now in case of even the reconnect thing is also clean. So even when client drops and reconnects to different chat instance, the instance resumes its X read from the client's last seen ID, replace exactly the entries that were missed during the gap, and then continues live and all those things. So these are reconnects and the pods disconnects and all. We try to take care and make sure that the experience still stays intact and all this stuff. So after considering this Redis streams for smooth streaming, and then the for time to first token, we considered this approach where a server sent events. After combining that, the ideal flow, this is how it looks like. So the chat service, whatever we have, it processes this user message, and it mints a new fresh run ID, returning into the client right away. And then this, now the chat service handles the assembled prompt whatever the client sends along with that run ID, and then that really helps to line up a worker to start generating. So we will think about putting a queue and all that stuff as we elaborate. Now this, once we send it to this client opens a SSE connection for that run ID, and then the load balancer will try to route it to respective chat service instance that it has tied up to. Then this chat service will start reading on this run ID stream from beginning for fresh connection, or from this client's last scene's entry ID on a reconnect or so. Then this inference worker generates tokens and adds onto this run ID stream. This chat service reads new entries, forwards them the SSE connection, browser appends them, and so that's how the flow looks like now, the rough flow after considering the both the requirements components into our design. All right, so that's the first requirement that's how we try to meet. So let's jump on to the second requirement. So second is basically how do we handle routing and scheduling generation requests across GPU workers. So we know that in systems of this kind, GPUs are biggest bottleneck because they are most expensive resources in the system, and even in the shortest supply constraints, how do we route work to them really matters, because the requirements that we guarantee latency and all are going to take a hit if there is a supply constraint. So now, and also the single model that this frontier models are producing, we know they are giant models and they are far too big to fit on a single GPU, and those weights to split across those weights really need bunch of boxes of GPUs to split those weights across of them. So, and also solving 100 case of concurrent streams means that we need to still spin up more thousands of such GPUs and all. So tens of hundreds of thousands of GPUs for one giant model and all that stuff. So that's even if we could save some percentage of utilization or utilize it to its maximum extent, that's real money that we need to think of, and how can we engineer try to come up with more utilization and all. So let's see now approaches that we can think of. The first thing is basically direct synchronous dispatch. So here simple, so nothing, we don't take care of anything, we just keep it as is. The chat service calls an inference worker directly for each request and hopes that our worker has some capacity or so, or GPU workers, and exactly whatever we have. But if we just try to keep it as is at the scale that we're trying to handle, it really doesn't work. And also there's no admission control. Even when traffic spikes to, like, let's say 100k prompts per second, this chat service keeps slamming this inference service workers that are already saturated. So, and also there's no way for us to know, like, does really worker has a room and all that stuff. And also let's say I send biggest prompt, like of 30k, 50k, 70k prompt, and it might take a lot of time to generate, while shorter prompts like hi or shorter things might still be piling up behind it. So here this really throws us a question for us. Utilization is very poor, and also the latency at which we will be delivering to the user is completely unpredictable. So which is really opposite of whatever we have in the bounds of 100 milliseconds. So this direct synchronous dispatch is something that we cannot really go ahead with. The second approach that we can think of is basically introducing queue. So here, queued worker pool. So what we do is basically we'll try to put a request queue between this chat service and then the inference service. So this chat service, now whatever the request it receives, we'll try to enqueue a generation request prompt plus run id, and we'll return that, and workers whatever we have will pull from this queue when they have capacity, and then generate and append tokens to run id stream, and then same as what we discussed in point 1. So this is basically a pull based. So worker, what it does, it only takes new work when it actually can do, basically when it has some capacity to do. So now basically what this queue does is basically it buys us some room between this spiky traffic and fixed rate traffic. So prompts arrives even if they are arriving in a burst, maybe 20k or 30k per second at a peak. The worker pool can manage a request through queue, making it not like not making the whole system go down. But either way, the burst still overwhelms the workers if the prompt length is bigger. And also right now still we have challenges, which is basically the no idea on latencies even now. So because the queue is basically helps really in handling high spikes of traffic, keeping it in queue and all, that's fine. But one thing is, queue is unbounded, so it observes temporary spike, but it really can make user to sit idle for a very long amount of time if we have huge number of prompt requests in a queue piled up. So that's one thing, again falling back to unpredictable latency. And also there's no way for us to tell user we are too occupied, our resources are constrained, and all that stuff, which is again very bad user experience of just showcasing infinite spinner on the platform or so. So this is something really helping one point, but still not at there. So the other approach is basically that really helps us with we'll keep the queue, but additionally what we do, we try to introduce continuous batching and back pressure. So here simple what we do is basically CPUs are best utilized when we do batch running on them. So instead of running one sequence at a time, what we do now, the worker will try to make it generate for many sequences together, advancing every sequence in a batch by one token per forward pass, and it adds and drops sequences from the batch on the fly. So finished generation is immediately replaced by the one in the queue that is waiting for. So keeping this batch full is what really makes that GPU busy, and also we are using it to its fullest potential. So that way, that's like biggest utilization advantage that we are making use of. And also the back pressure that we are trying to add. Now at least even if the system degrades, we can degrade predictably instead of like just melting. So now if what do I mean back pressure is basically we'll try to have on a queue some bounded depth and admission policy. So let's say like now if queue is having like 10 prompt requests waiting, let's say like that's an upper bound, the bound depth that we have. So when is that deep, so we stop pretending that we are handling and all that stuff, and we can straight away start rejecting the end user's request, like, or saying that we are at a full GPU's utilization, so try again some other time. Or else like we can degrade or defer request to low frontier models and all that stuff. So here basically adding this batching guarantees us fullest GPU utilization, and back pressure of this bounds and things really helps us to really predict the system's degradation well, like with proper user experience on those things, on our user UI of that platform. So this is the ideal flow it's going to look like. The chat service enqueues this generation request with its run ID and token cost estimate, and the admission control will first try to check the queue depth, and if we are open over that limit, the request is deferred or shared, and let the user know accordingly. And the GPU worker pulls the request and folds it into its running batch via this continuous batching. Then this worker streams tokens to the run ID stream as the batch generates as usual. And when generation finishes, what we do, we'll just drop that sequence from its batch and pull the next one in the queue. So this is the rough flow of how it's going to look like, and this is how we smartly handle this routing and GPU scheduling and all those things, and handle this back pressuring things and all those things. So that is the second requirement, is how we try to handle this routing and scheduling generation across this GPU workers. So now let's jump on to the third requirement, is basically how do we prevent heavy users from monopolizing GPUs, and also giving paid users a better experience. How do we handle this kind of situation? Basically, because there might be a user who is heavily using our platform and is sending 30Ks 50Ks of prompt requests, and of course those burn a lot of compute, then hundreds of thousands users sending one-liners things. So now how do we guarantee fairness across users, so nobody can starve everyone else? So here we need some business priority across tiers. So basically paid customers get a better experience when things are tight, and how do we deal with this? So let's see. The first approach is basically go with the default standard, so flat global rate limit. So here is basically we'll have global rate limit. So basically we'll say one request per minute cap applied to everyone irrespective of their tier or whatever it is, like 5 requests per minute, 10 requests per minute, and all those things. But here if we choose this, here requests aren't really the cost, tokens are what is the main part that we need to focus on, because that's the thing that's burning our money. So this we are considering request, so that is why this is not the approach that we need to stick with. Then the other approach that we can think of is basically per user limit. So here instead of having that global shared bucket, now what we are doing is basically we are having one bucket per user. So basically per user we are trying to limit it by things. Again here same as before, instead of the global flat bucket, now we are just restricting it by user, so that this user can make 10 requests per minute. We are just storing it in our Redis, rate limiting keyed by user ID. But again this considers the request as the expensive factor, but here the tokens are is what is our burning thing. So to consider tokens, this is where the third approach is what really helps us to meet that. So cost aware quotas with tier priority and graceful degradation. So here basically we should always try to focus on what's scarce, which is a tokens here. That is our like estimated compute, not like number of requests and all those things, because when a generation comes in, we estimate how expensive it will be from this prompt length and also the requested max output that it has. So and then we calculate that and we check against how much of that user's token budget is left, and once if it is within that range, we accept it and proceed, or else we just reject or delay it if they're over. So and then budget refills over time, the way the API quota does and all those things. So now the thing we are counting is what we are actually paying for the tokens, right? So that's how we'll try to introduce this cost aware quotas with the tier priority and thing. So here this priority is basically is what now before we had like a plain queue, so it is not aware on the tiers of the users. So now what we do, priority queue, the paid users usually will try to make them, they'll get the higher number in the queue, and so that they get picked up by the workers before any free requests with a lower priority number. So ideally what we're trying to make is basically paid users will get bigger budgets, higher concurrency limits, and higher priority in this queue that I'm talking about. And now this queue, instead of being the dumbest one of FIFO one, whatever, first in first out, now this becomes the tier where paid requests are pulled ahead of this free request when workers are freed up. And this now basically that's only when we have tight constraints. But under normal load, everyone's are served fast and nobody really notices. And this tires divergence when system is tight, and normal load divergence when system is normal, is what really handles this monopolization of the request, and also fair experience to the people who are actually paying the money to our platform and things. And even let's say we can still make the degradation explicit, like even when demand far exceeds the capacity, even after taking all this admission control and free users and everything whatever we just discussed, we can still throttle free users, maybe defer or downgrade to route to smaller cheaper models which really need less compute than the latest frontier models, so that we can still keep paid users feel the experience same as they normally do on a normal period of normal traffic time too, right? This basically fairness across users and priority access tiers is what really guarantees the no starving for any users. So basically why I'm stressing here is basically fairness across users, no single user starves other, and priority access tiers, paid beats free, are two different goals. And that is what I'm trying to highlight here, is basically this design handles them with two different mechanisms. So per user cost budgets for the first, which is the fairness aware across users, and then the tier awaited queuing for a second. So that is like paid versus free. So cost budgets per user, and then the tier aware periodic queue is what really handles both of them. So this approach is what tries to meet this requirement that we just discussed, preventing heavy users from monopolizing and also giving paid tiers better experience. So and now let's jump on to the last requirement that we'll be discussing. So as conversations get longer and longer, how do we really control this inference cost with context preserved, basically making the users feel that whatever they had messages in the chat is something that we have not forgotten. So let's see, I think this should be because in a single chat user can go up to 1 turn, 2 turn to hundreds of turns, like assuming even if it's like a 500 tokens per turn on an average. So if it's a 50 turn chat, it is 15 to 500 is 25k input tokens that we need to send all at once to inference prompt. But we all know every model comes with its own context length limit. So how are we going to handle is something, going to pressure with something? That's one discussion point. So first straightforward that we normally do is basically truncation. So all we do every time we try to send a request to inference, we try to limit the to most recent end time. So what we do, it will be a simple query. So selecting star from messages, ordering by created at, and let's say I get 5 or 2 or something, and then I'll just flip it so to keep it in the same chronological sequence, and then send that as a context for every new prompt request that user is making. So that's one approach that we can make, truncation. But again, this basically doesn't really meet if a user is keeping in mind the whole list, the chat message that he has asked, and is trying to refer that, because if you are not fetching all of those, that is something doesn't meet. So this truncation is something really doesn't help after a certain number of turns. The other approach is basically, ideally, normally even today every major platform follows, is basically prefix caching and rolling summary. So here we know that across turns in a single conversation, most of the prompt that we see is identical from one turn to the next. Since because the system prompt and everything already said in the chat all repeat, what we do is basically we can cache this model's intermediate stage, that is the KV cache for stable prompt prefix, and then once we cache that, we can reuse it instead of recomputing it from scratch every turn. So only the tail of the prompt, basically the newest message, the actual changes, so that the prefix caching, what it really helps us with is cutting the cost and latency of processing the input, which really helps us our TTFT latency requirement directly. And again, it just sends as usual the conversion turns to a worker, which really has this prefix form whatever we have just discussed. So that's one thing. And this prefix caching really helps in rereading this history as a cheapest possible way. And now this still, even if we follow that, this conversation can still outgrow the context window, no matter how cheaply we can cache it and process it. That's where again the other approach is basically rolling summary. So rolling summary is we normally see is basically what we do. We try to keep the most recent turns, let's say like last 5 messages word to word verbatim as is, and we'll try to compress older history, after previous older than 5 messages in a conversation. Others all, what we'll try to compress that into running summary, and only now the prompt becomes the system prompt, and then summary of all the older turns, and the last few turns will remain the same word for word, and then we try to attach the final user message and send it to our inference engine. So this rolling summary, as conversations grows, as turns grows in a summary, in the background it will be processing and try to do it in this way. And also this maybe we doesn't do it for every turn, but we'll have some threshold, like if it is hitting 85% of a context length or limit, that's when we try to kick in a background process, and then it will take care of these things. So that's how we take care of this contexts even, and make them feel like they can continue in our conversation infinite turns or so. So this is how we try to handle all of these scenarios and situations that we normally see in our day-to-day platforms like Claude, Gemini, or ChatGPT. And also, like, the other thing is basically we can just have a brief mention is whenever we are trying to generate and user wants to cancel that generation, and so that we can reclaim the GPU so that can be used for other sequence that we have in the pipeline. So how does that flow look? Basically what we do, we just make a post request to this run ID cancel, then this chat service whatever we have, it just flips this generation status to cancelled in our metadata DB, and then it publishes that cancel signal on control channel in our Redis keyed by run ID, and then worker will be checking for every token batch this control channel, and once it finds out that, it just stops that generating and all, and then it really doesn't utilize the GPU for that generation. You might think this is something, it's fine, like just a 30-second generation, but even if you use it for 30 seconds, that is purely wasted GPUs, and we know that GPU is scarcest resource and most expensive thing, so it's reclaiming and using it for other requests is also like we are saving some money, and that's the worth mentioning thing, because and also the signal has to exclusively come from the user. He has to press the cancel generation or so. Even if he closes the tab or anything, that is not considered as a cancel generation. So that's the thing, because anyhow we know that it runs in the background. So this is how it's going to look like after considering all the components tying up together. And here this chat service can scale independently, and inference workers can scale independently, and priority queue handles the tiring and the burst of traffic and all that stuff, and then streaming handled by Redis stream and replace. And yeah, this way we can guarantee at least it meets the requirements that we have laid down. And hope at least you got some points from this discussion and few learnings. Yeah, thank you.
All right, now let's discuss about Stripe, basically a payment processing systems. So what do they do at high level? They allow business, mostly they're referred to as merchants in their terms, to accept payment from consumers without having to build their own payment processing infrastructure or so. And once they expose that to customers input their payment details on their merchant's website, and merchant sends the payment details to Stripe, which then processes the payment and returns the result to the merchant. So that's how it does what the high level functionality of the Stripe is. So now we are clear what this payment processing system does. Let's as usual try to break down our requirements into functional and non-functional, and let's see what are the requirements that we are supposed to meet when we are designing systems of this kind. So here first requirement is basically so from two user standpoint, merchants and the users. So from the merchant standpoint, they should be able to initiate payment requests, that is like charge a customer for specific amount, and that's the the what we should provide to the merchant. And second requirement is users should be able to pay for products either with credit, debit cards, or other payment methods that we normally support things. So that is the second requirement. The third is the merchants should be able to view status updates for payments, whatever the customers have paid for, like is it pending, success, failed, or whatever it is. So they should be able to see somewhere in the dashboard or so. So those are three core functional requirements that we'll try to focus on. There are still a lot of things we use Stripe or other payment processing systems
extensively. So we'll see, like, it has features like, customers can save payment methods for future use. They should be able to issue merchants should be able to issue full or partial refunds. Merchants can see transaction history and reports, and supporting alternative payment methods, bank transfers, digital wallets, and handling subscriptions, the recurring payments and payouts to the merchants and all. If we go on talk, it has zillions of features in the that product, because they have thousands of engineers working on the rollout of the features and all that stuff. So these are like core 3 functionalities that we'll try to focus on. And now coming down to this non-functional, first thing is, since it is something we are dealing with fintech, so it should be highly secure. So that's one thing. And then the second non-functional requirement is it should ensure strongest durability and auditability. That is, it is very mandatory that we do not lose any transactions data, and that is something we need to be complied with. And the third requirement is basically it should guarantee transactional safety and financial integrity. So here basically, for example, no double charges or so, such that and we basically work closely inherently with the asynchronous nature of external payment networks like Visa or MasterCard or any bank. So that's very important to adhere to them rather than working against them. And the fourth is basically our system should be able to scale to handle high transaction volume, so 10k plus transactions per second, and also maybe potentially handle bursty traffic patterns during Black Friday sales, or like year-end sales like New Year sales, holiday sales, and all that stuff. We should be able to handle the high number of transactions per second. So that's the thing. And others, we should adhere to financial regulations depending upon the supported region that we're supporting, and easily we should be able to add new payment methods, or so. Those are like always will be in the pipeline of non-functional requirements. At least now we have decent the non-functional and functional points listed down. Let's see how we can evolve with that. But now we have listed down, and we should be able to easily identify the core entities that we'll be trying to deal with. So core entities, so that we can think of is basically the merchant. So here this entity, what it does, it will store information about the businesses using our payment platform, including their identity details, bank account information, API keys, and whatever all the stuffs that we normally need for compliance purposes, and all the things that we need for all the features to support. And the second entity is basically the payment entity, payment intent. So this is basically actual intention of the merchant to collect specific amount from consumer. So it basically tracks this is what we'll be using to track overall payment cycle from creation to completion for particular thing. So this is the state machine, like created, authorized, captured, cancelled, refunded, dispute, and all that stuff. So that's like this is the payment intent. And then the third is basically transaction. So this represents the money movement record linking to above this payment entity. And so types of charges, it can be transaction can be charge, funds that will be coming in, refund, funds flowing out, dispute and potential reversal of this transaction completely, payout, merchants withdrawals, and all of this normally that we see in Stripe and those things. So here the relation is basically one payment intent can be tied up to many transactions. So that's like just the relation between them. And yeah, I think the core entities should be clear at least to begin with. So these are the core entities. Now let's jump on to this system contract API. So first thing is we should provide an option for merchant to initiate a payment intent request. So they should be able to create the new payment intent. So it might be be as simple as this post endpoint. So payment hyphen intent or whatever it is, it can be, and what we written is payment intent ID. The body might look something like this. What is the amount in cents that is, and what is the currency, and the description and all that stuff, other metadata, whatever we wanted to collect, we can just collect. That's one endpoint. And the second endpoint is basically to accept or process transactions. So since now maybe assuming that now we just report credit or debit cards, so we will need an endpoint to accept or process that information stuff. So here that will be post endpoint, so related to payment intents itself, so that will be there, and we'll attach the payment intent ID and the transactions endpoint. So here the type, like I said, charge, dispute, refund and all that stuff, it can be of that kind. And card details, we'll just try to take in all those details. And important here is basically we will never take this raw card details like this. It will always be secured, and we'll see how it will be secured and encrypted, and such that even we'll not be able to see these details of the card and all those things. So that's the second endpoint. The third endpoint is basically able to check the status of the payments that is been made by above endpoint. So here now merchants should be able to somehow check the status of the payment that has been made by customer, whether that went through, or is it a pending state, or is it failed, or what is it about all that. So this will be simple get endpoint payment intents, and they give the payment intent ID, they will receive this payment intent and stuff. This can be something like polling, if we choose polling approach. But if they really want real-time updates, so there will be something like we'll try to post that specific event whenever it happens. So the whatever the merchant has been subscribed to that webhook URL, and we'll emit something like type as payment succeeded, and what's the data like for this payment ID and amount in cents currency, this has been succeeded, so that they can update their internal databases and then do whatever the functionality of their application is, maybe shipping something physically or unlocking some digital content or whatever it is. So that's something. So we'll discuss, this is a black box for time being, so how we'll talk about webhooks and how we provide and how they work, we'll discuss at the end. But these are the core endpoints that we can think of to at least meet the basic requirements that we have listed down. So now let's jump on to the high level design, taking one functional requirement at a time, and see how we can just build up a foundational components interactions, and then elaborate more on our non-functional requirement. So breaking down, the first is by the high level design. So first point is the merchant should be able to initiate the payment request. That's our first requirement. I think it should be simple and straightforward, like normally we just have this separate components listed out, and we'll try to connect them. So simple. So whenever this merchant wants to charge customer, what do? Is they just initiate payment request. So here what we do, we just try to create first the payment intent, and this that's basically merchant's intention to collect specific amount from customer and tracks this life cycle of payment from initiation to completion. So these components, I'll just merchant, API gateway, payment intent service, and database will have this payment intent table with attributes like ID, merchant ID, customer ID, status, amount, product, metadata, and other details that we wanted to have. API gateway, we know it handles routing, authentication, rate limiting, and all this middleware stuff. And this payment intent service, just creating and managing payment intents that we just discussed, as just an interface to with our database to store that. And database can be simple as Postgres also. The flow is simple. The merchant makes an API call to our system that post request to our payment intents with all the details, and once authenticated through the API gateway, the request is routed to the payment intent service, and the payment intent service creates a new entry in our table in a DB, and then it generates unique identifier for that payment intent, and it will just return to the merchant back. So that's the simple flow of meeting the first requirement. They should be able to initiate payment request. That's the thing. So fine, so now we have at least code components tied up. Let's jump on to the second one. User should be able to pay for products. So now here, now that we know in the first step the payment intent is created, the next step is basically we should be able to collect all the payment details from consumer and process the payment. So we know and it's important to acknowledge that the payment processing is inherently asynchronous. That is, it will have series of multi-step processes. So because it has to go through the authorization from external payment networks, and that's the first step, and then that can take maybe minutes or days to fully complete. So that's where, like, we should understand the fact that it is inherently asynchronous, and we should be able to design systems such that it can handle all of this series of steps processing things. So because that's complex, they need to go through fraud checks, chargeback request, and all that stuff. So this we need to handle that, and so to handle that, what we do, we introduce a new service here called transaction service. So this dedicated microservice, what it does, it will receive card details from the merchant's server, managing this transaction records throughout this payments lifecycle, and this will interface with external payment networks like Visa, MasterCard, banking systems, or whatever it is. So this is basically this is external to our system, and we are not responsible for that, but it's a crucial part of our payment flow. So this basically, what do? They are the ones who authorize and process the financial transactions. So the flow is basically how it looks is this. Now the customer here, they enter credit card information into the payment form on the merchant's website. The merchant collects this data and sends to our this transaction service along with the original payment intent ID. Then this transaction service, what it does, it creates a transaction record in our transaction table. So this will have attributes like ID, payment ID, the amount type, status, network, metadata, and all that stuff, with status as pending. So now this transaction service will handle this payment network interaction. So that will be responsible just to connect to appropriate payment network. So it can be anyone, Visa, MasterCard, depending on the card details that they have sent, and we'll send an authorization request. So once we send authorization request, we receive the initial response from this external payment, whether it is an approved or declined. So and then accordingly we'll update the transaction record with the initial status as approved or declined, and we'll keep continuing listening to any callbacks from this network payment networks over some secure private connection. So when again we receive some additional status changes like settlement, chargeback, etc., we receive those callbacks and we'll update the records accordingly. And then this transaction service will finally update this payment intent status as transaction progresses through its payment life cycle. So that's how, like, rough the flow is what it's going to look like. And I'm not going into details of, like, how they talk to external payment service and all, because those are something the payment process, whatever we are building, they must establish dedicated connections through like specialized hardware security modules, HSMs, and secure data centers. That should meet some standards like payment card industry data security standard requirements, and all those private networks basically they follow proprietary protocols with specific message formats, and they require formal certification process and all those. Like, they're not like REST APIs. So those connections often involves binary protocols, leased lines, VPN tunnels with mutual TLS authentication and all stuff. So that in itself is the biggest discussions and the stuff. So that is why it's a black box for us. So the second requirement is this is how we meet the second requirement. So let's go to the third requirement. Here the merchant should be able to view status updates for payments. So I think this should be simple. So after payment is initiated and processed, the merchants, they somehow need a reliable way to know what is its status. So because that's very important for merchants, because due to after which the status is known, only they will trigger some fulfillment actions. It can be shipping physical products, granting access to digital content, or confirming some reservations, or whatever the domain that the business is operating in. So they need to know, like, when payments fail and when payments succeed, so that they can notify customers or attempt alternate payment methods. So what that responsibility is something we will delegate it to payment intent service itself, because it's simple, because we have this endpoint payment intents payment ID to retrieve the current status from this payment intent table. And this API gateway, what it does basically, whenever merchant tries to request, it just tries to validate a merchant's authenticity and routes request to payment service, and this queries the database for the current state of that payment intent, including its status, any error messages, and any details, transaction details that it is tied up to in that table. And this returns this information to the merchant in proper response format that they expect. And this simple, what they do, either they can maybe since it's like actively pulling, so they simple polling mechanism is something merchants can implement to programmatically check for like every few seconds or so, and like they will at least know statuses like is it succeeded, failed, processing, or created, and all that stuff. So this polling will think about other approaches like webhooks and all for real-time updates, but we'll talk about that. But this is like in a simple way, at least we're able to provide a way for merchants to get the what they want, although it might be not real time, but that's fine. So like these are the how we try to meet the core functional requirements. Now let's jump on to the deep dives. So this is where we try to pick up one non-functional requirement at a time, and since this discussion is more of like an infrastructure related system design, so this is where most of our time and the efforts or emphasis should be there, and try to dig as much deeper as we can and try to understand like critical functionalities of core components, and how we can think of all scenarios and how do we address those all edge cases is something really important, and that really cracks our thinking process too. The first requirement is basically we should be highly secure. That's the thing. So what do you mean by here security, highly secure, guaranteeing security system? So two scenarios, whatever the person or the business or the merchant making the payment request, are they really who they are? So basically how do we verify them? So that's one thing, so that we know that whoever are entering our system, we know about them, and they are like legit people or legit businesses and all. So the other thing is basically all the the personal data that customer is sharing with us, their card details and other addresses and all that stuff, we should earn their trust by protecting their data such that it's not exposed anywhere on the internet and it cannot be stolen or compromised. So these are the two things from two standpoints that we need to think of, and how do we deal with situations of this kind. So let's take first scenario, verifying merchants, and let's see what are the approaches that we can think of. How do we tighten the securities for this scenario? So verifying merchants, the first approach is basically basic API authentication. So what we do is basically whenever merchant tries to onboard to our payment platform, what do we do in onboarding flow itself? We generate a unique API key, something it can be like something like this, so like PK Live or something like this. That's what Stripe or other platforms does, and we store this in our database associated with that merchant's account. So now every API request that merchant makes, we the merchant includes that this API key in authorization, like bearer API key, or in custom header like X API key, that API key. So now when our API gateway receives that request, we extract that API key and we look up that in the database and identify the corresponding merchant, whether it's a tallying or not. If it's so, we'll let the request through and then authenticate and process that. That is the simple stuff. But here this is something basically this is vulnerable to interception through network or sniffing, especially if it transported over insecure connections and all. And so this is something we cannot completely rely on. So other grade is basically the improvement on previous one. So we'll try to enhance that key management with request signing. So this is what ideally we see in Stripe also. What do we do is basically here we'll have not just the public key, but it's a combination of public key along with the private secret keys. So same, during onboarding we provide two keys, public API key for identification and the private secret key that will be securely stored on merchant server, never in our client in their client side code or so. So those keys will be used for authenticating the merchant server with our payment system, so which is separate from how we handle customer card details and all those stuff. So it might look something like this. So what happens, so example request with signature here. Now for every API request, this merchant server generates a digital signature by hashing the request details, so method, endpoint, parameters, body, along with the timestamp and unique nouns, so using whatever the secret key that is stored on their server. So this signature proves the request authenticity and prevents any tampering that we can make or any users can make. So this way, even if replayed, we would know that the timestamp was outside our acceptable window and that nouns was already used, so we will completely reject that request. So that's what. So here it might look something like this. So when our API gateway receives a request, the payload might look something like this. So it will retrieve first, once it receives this payload, the API gateway, it retrieves this merchant secret key based on the provided API key, the public API key from our system. So once it retrieves that secret key, it recreates that HMAC signature using the same algorithm, so SHA-256, secret key and request data. And once it recreates that, it compares that the signature with the one provided in our headers. So and it compares with this, and if it matches, then we know it's a legit. And then once it is matches, we also validate this timestamp. So is it within the acceptable time window? Ideally it will be like 5 to 10 minutes or 15 minutes or so. And after that, when we check the nouns, so is this nouns has been used or not been used before within this window or not, by checking this maybe cache or DB. So this way, this HMAC, hash based message authenticated code with a shared secret key, that is a private secret key, we ensure that both authenticity, the request came from the merchant with the valid secret, and the integrity, the request data hasn't been tampered with. So this is how we take care and we verify merchant very strictly using this public key and private key and HMAC way and all. I think this should be clear. And now the other viewpoint, which is protecting customer personal identified informations. So how do we handle this? What are the approaches? So first is basically the server side payment data collection. So what do we do here? We allow the merchants itself collect and process card data on their own servers before sending it to our payment system infra that we are building. Then the customer, what he does, he enters those card details on their merchant's website, and then those card details are forwarded to merchant's server or HTTPS, where they encrypt and transmit the data to our payment service. So this now the authorization responses from external payment networks merchant server receives, not us. So this basically this is completely against the requirement of PCI DSS, and it should never be even implemented, because those details or anything should never touch merchant servers and all. So this approach is something completely off. And the other approach is basically client side iframe isolation. So here is basically the private data which we were talking about. The card numbers should never hit merchant servers. So what do we do? This credit card details or any debit card information, we try to transmit directly this from the client to our servers over HTTPS, bypassing merchant systems completely. So ideally, to accomplish this, how do they do is basically whatever the SDK that we normally expose, just the wrappers around APIs, like and that loads iframes directly on merchant's client. Our SDK, what it does, it tries to create a secure iframe here on merchant's web page that loads directly from our domain, actually our UI, and all that stuff. And when customers they enter card information, it goes straight to our servers without even touching their merchant systems and all. So this basically this iframe creates a security boundary. So this browser's same origin policy prevents the merchant's code from accessing data inside the iframe and all. So this way we completely ignore these merchants. But here with this again, we are relying completely on this browser security policies, and also it really limits any customization options and can maybe also cause usability issues on mobile browsers and all. So ultimately the final approach that we would stick to is this just the iframe plus encryption. So here we'll just try to add an additional layer of encryption. So here that's what multiple layers of security. Our payment system, what it does, it generates and manages encryption key pairs along with the iframe, our SDK, which was providing in our previous approach. So now this SDK will utilize the public key or whatever has been shared with them for encryption. So how it works is basically whenever customer enters their card details in our iframe, our SDK will immediately encrypt that data using that public key before even it leaves the device. So this means that card data never exists in unencrypted form outside their customer's browser. Even if a merchant site is compromised, the attacker would get the encrypted data which they cannot really decrypt because they don't have the private key. So this encrypted data that is then transmitted over HTTPS to our servers. And there we use the private key which is stored in our hardware security modules to decrypt it, and this HTTPS again provide additional transport security. So it's now it's protecting already encrypted data. So that's the additional layer of protection. So this multi-layered approach ensures that nowhere this PII is compromised, and it's always secured, encrypted, and it's hard for anyone, even if they get an access, to decrypt too. So that's how we ensure this encryption and security of PII stuff. So that's how we handle our first non-functional requirement. So now let's go to our second non-functional requirement. So strongest durability. So basically provide auditability, making sure we don't lose any transactions data even in case of failures. So how do we do that? So let's see the approaches. First is we doesn't care about anything. We'll do simple single database with current state, and we not maintain series of events that led to that particular state. So what we do is simple and straightforward. Normally in our relation database, we just update that status of particular row in a table, like updating payment intents table and setting that status to captured and all that stuff. So we just maintain only current state. So if we maintain that, we are completely throwing away history of all series of events that led to final state, and it really becomes hard for our compliance, auditing, and everything. So this is something never accepted in financial related transactions and all. So this is big no for our approach. The other thing is basically we'll try to maintain separate audit tables. So it might look something like this. So we'll have main table, payments. We will same update same as the previous approach, but here we will try to maintain separate payment audit log. So here it will be just insert only, so like it will be purely append only table, and whenever any event change is happening or entry is happening, any event change is happening to our main table, we also insert audit record into this payments audit log. And this way if anything we need later to replay or to check anything, this is where we try to query and get the data payment audit log. But here the problem is here now we are relying on application code to implement those operations whenever we try to perform. So there's an high chance that we might forgot a developer whenever is trying to create some new feature or so. So this is also something we don't want to even strain our main the operational database. That's like that should be like solely responsible to handle that specific transactions per second, whatever it is mainly supposed to deal with merchants and all. So it should not worry about our internal stuff, auditing and all, compliance and all stuff. It's for our internal needs, and it's for our backlog for financial the records and all those stuffs. So that's something we cannot go with. So final approach is this is the what really helps us to deal with all of this. So database plus CDC, change data capture, and then event stream. So this is like standard patterns in any of the applications of this kind. So how it works is basically it will have operational database, the ones that I just mentioned. So that main responsibility would be handling this merchants API request, whatever the users, in our case merchants, their pure operational data models is what we'll be having. So here the change data capture, what it does is basically it monitors this database write ahead log, WAL log that we'll have. So capturing every committed change as an event. So this happens at the database level, not at application level. So which really guarantees that we never miss changes. So that is the CDC, and that CDC, what it does, it publishes all changes to our event stream. So it can be Kafka or any other the stream that we are using. So this whatever all the events that we are publishing to Kafka, we will create that append only log of every state transition, and then events maybe mostly are keyed by payment intent ID and include like full state like before and after. So that will have, and that event stream will be consumed by specific consumers. So it can be any internal services or anything that we'll have, and that will be consuming. So ideally that's how a flow looks like to handle that. So the flow is simple as this. So it change data capture, Kafka event stream, and we will restore it in our S3 for durability and all that stuff. So here the consumers for this event stream can be audit service, analytics service, reconciliation, webhook delivery, and all that stuff. We'll talk about that. But ideally this is how we really handle this durability and also transactional logs, and no transactional data is lost and all, and how we offload the individual responsibilities completely and all that stuff. So this is very important pattern, CDC, event stream, and then the consumers, and that's how we normally try to break down our system. So this and for durability and all that stuff, Kafka provides us a configuration, a replication thing, maybe 3 times across multiple brokers and availability zones, and then we can retain those events even for a month or so on a disk, and this can be flushed to this S3 for long-term durability and auditability and all that stuff. So and now merchants get their sub 10 milliseconds IP request purely from this operational database, and while every other change that is needed for auditing and all that stuff is captured in event stream, and other consumers will consume without affecting our things. So operational database will easily handle that 10k transactions per second what we just laid down, and the other event consumers handle auditing, analysis, reconciliations and all those, like without really competing for our resources. So this basically satisfies the compliance requirements, and also really provides the foundation for our advanced capabilities like reconciliation, webhook delivery, which we will discuss in the next points. So that is how we meet this the hybrid approach. And here again there might be many discussion points. So what if this CDC isn't a single point of failure, and how do we handle if that fails and all? So maybe we can bring up, like, we'll try to run multiple independent CDC instances reading from same database and writing to different Kafka clusters, and also we might have implemented monitoring system that alerts within seconds even if CDC lag increases, and we try to maintain some recovery procedures to replay missed events from the database logs if needed. And also even if that fails, we can have application level fallbacks itself that directly write to Kafka instead of relying on CDC. So that's how, like, we can at least try to see how can we mitigate even of that situations, the worst scenarios that we can really think of. So this is how we meet this second non-functional requirement that we have, and that's the approach that we'll stick to. Now the third non-functional requirement. So now we should guarantee the transactional safety in financial integrity, that is no double charges, and how do we support this asynchronous nature of external payment networks instead of complaining that's how they are and how legacy their system is. Instead of going against them, how can we build a system such that it supports the existing way that they function? So let's see the approaches, how it's we can think of here. So the first is we'll assume this timeouts mean failure. So here, what do I mean here? Asynchronous reality with the payment networks. So let's say in our merchant's website also, me or any customer clicks on pay for, let's say, some $100 purchase or whatever it is. So what do we do now? We wait for bank's response, and the merchant we wait for, let's say, like few seconds, 30 seconds, 50 seconds and all. If we don't receive anything, we retry, and then the customer sees like two charges on this statement. Even we can later refund one, but that will be like significant hit on their trust and on our platform. So this is what, like, this asynchronous behavior from the external payment networks. They might be sending it right away, or there might be network delays, or the packet might get lost, or so whatever it might be happening. So how do we handle all of those scenarios is something that the discussion should be on. So first is assuming timeouts mean failure. So here what we do, usually I just treat the network communication as just straight away as internal service cost that we normally do. So let's say typical timeout like 30 to 60 seconds, we treat that as a failure, payment has failed, and if you don't receive that response within that time window, we update our status as a failed, and this lets us give the merchants feedbacks immediately, or right away. and all. But this is like, a very very bad approach, basically, because network timeouts doesn't really tell us nothing about what happened to the payment. So like I said again, simple challenge is, we send maybe some $100 charge request to customer's bank. The bank approves and debits the customer's account. The response packet gets delayed or lost in network congestion or whatever. So our 30-second timeout might trigger and we mark the payment as failed, but actually that really has been charged. So, and the merchant, whatever, he displays the payment failed, please try again, customer retries, and he now creates a second the $100 charge. Now customer has like, paid $200 for the same $100 purchase. So that's something, this assuring timeouts mean failure is blind, completely blind, and that's something that we should not go with. The other is basically pending states with manual reconciliation. So what do we do here is basically, we instead of now considering the timeouts as a failure, we introduce a new status, like something pending verification, especially for these timeouts. So we might create separate table to track every attempt we make to charge payment network, regarding like what we sent, when we sent it, what a reference ID that network assigned. So now when a timeout occurs, we mark this payment as pending verification rather than as failed, and we'll have some background service that periodically queries this payment network using this reference ID that we have stored, to really understand what actually happened with that payment. So this verification process will try to make it run independently of the merchant facing API. So this basically really helps us like gradually to resolve these certain unknown states and to known states what really happens. So this is something we can proceed with again, but this introduces a significant manual reconciliation burden. So again, our financial team or whatever the team is should review pending payments daily, check them against the bank files, update statuses manually, and especially during busy periods like Black Friday and year-end sales, on any festival sales, holiday sales, there might be thousands of payments stuck pending states, and it might be a big burden for manual verification. So this is something we cannot really rely on. Then the best approach is basically event driven safety with reconciliation. So here in our above discussion, we lay the foundation, the CDC and event stream infrastructure for durability, and treating this asynchronous payment networks as like first class citizens in our architecture. So here what do we do now? This is how the flow will try to record the attempt. So before calling any payment network, we write an attempt record to a database with the network name, reference ID, and what we are trying to accomplish. So this, what it does, it will trigger a CDC event capturing our intention. So once we do that, then we try to call this payment network. So we send the actual charge request with our configured timeout. So once we send to that payment network, we'll try to handle this response based on whatever the outcome that payment network gives us. So if it is success, straight away we update the status to succeeded in our database, and which will trigger another CDC with a successful outcome. Then that might be one scenario. The other scenario might be timeout. Again, we'll update the status to timeout in our database. We'll again trigger a CDC event that now will be picked by our separate reconciliation service. That will be job of it to periodically keep checking this timeout related events with the payment networks, and if it's explicit failure, we'll just mark that as a failure with failure reason and let the merchant know. And this fourth step is automated reconciliation. Like I said, the dedicated the reconciliation service now will consume this timeout events, whatever have been there in our event stream, and it will proactively now queries the payment network using that reference ID to determine what really actually happened, and then accordingly update. So this is how the flow looks like. So this what really helps us basically creates a complete audit trail where every step is captured as an immutable event, and we'll know like whether call succeeded, failed, or timeout and all. So this is where this reconciliation thing and all that stuff. So it looks something like this. So if I yeah here this reconciliation worker will take in this event from this event stream, and we using that id, it will query this external payment and know what really happened, and depending again on the conditions of all the three success, timeout or failure and all, it will try to write the updates to our database. So this way this reconciliation really making direct API queries to this external payments, and then making sure we batch all of this reconciliation request, and we have all of these ways of retrying and proper auditing what happened, and all those events is what really makes this system this system as transactionally safer, and we maintain this financial integrity and respect that asynchronous nature with our external payment networks, and there will be no double charges or so this basically what I'm trying to say is basically it respects that payment networks are asynchronous partners and not synchronous services, and by tracking every attempt and its outcome through events, we build a system that handles uncertainty gradually, gracefully, rather than fighting against their system or so that's how this reconciliation worker and the flow that I just described really helps us with this. So ideally that's how it will be taken care, and now the fourth point is scaling to 10k plus transactions per second. Before this, the transaction processing usually in production systems like Stripe, it will be two-phase event model, like transaction created event, transaction completed event. So that transaction created event is basically will be emitted when the transaction service begins processing, so before even database write is complete. So if this event fails to emit, the transaction enters the logged or failed state and can be retried later. The other event is transaction completed event. So what this will be emitted after database write has successfully completed. So if this event fails to emit, the transaction again enters the logged or failed state, where further updates are blocked until this completion event is successfully emitted. So this two-phase approach, what really makes the system is to compare the created event data with the actual database state during retries. If the database write already occurred, the system now what needs is basically only needs to re-emit the completion event instead of retrying the entire transaction. So this pattern guarantees about the data consistency between transaction service and downstream consumers, whoever it is are consuming from our event stream and all that stuff. So this is all very important, so that will be learned with the actual failures that we see in our production systems and all that stuff. So now let's discuss the fourth one, scaling to 10k plus transactions per second. And I think this should be now mostly discussed, but let's start. We have few core components that we have in our system is servers. So here each of our services, we know it's stateless, so obviously straight away we'll just try to scale horizontally with the load balancers in front of them, distributing the load, and and that's how we try to take care of servers. And Kafka, we know that we are expecting around like 10k transactions per second. Ideally Kafka supports millions of messages per second at a cluster level. So now each individual partition typically can handle around 5k or 10k messages per second under normal traffic. So to comfortably support our 10k plus transactions per second, we might multiply that by 3 times or 5 times to ensure that both throughput and fault tolerance. So now the question is, how do we partition? So we just partition the our Kafka topics by our payment intent ID, which ensures that all events for that given payment ID are processed in order while allowing parallel processing across different payment intents and all that stuff. So that's way we try to handle that. And for redundancy, we just by default configure the replication factor of 3 or so, and in such that each partition now has 3 copies distributed across different brokers. So this really helps us providing fault tolerance even if broker fails. And also now we'll set up consumer groups for each of our services, allowing us to scale even the consumers independently horizontally while maintaining exactly one processing semantics. So this basically what I'm trying to say is leverage the default capabilities that Kafka comes up with and configure the right things that we normally need. And the database, so here again we are like, let's say 10k transactions per second, so that is 10k writes per second. So here assume we are using a Postgres instance. So let's see how much, let's just do a rough estimation. So assuming each row entry that into our table is 500 bytes, that means 10,000 records multiplied by 500 bytes, it's around 5 MB of data per second. Like in a day we have around 86k seconds, so let's round off to 100k. So 5 MB multiplied 100k, it is 500 GB of data a day. So per year multiplied by 365, it is around 180 TB of data a year. So that is like significant storage growth that we will require careful planning of data retention and archiving strategies. So what do we do ideally for transactions older than certain period, like let's say 3-6 months old, we can just move them to cold storage like S3 or S3 compatible Google Cloud storage or Azure blob storage, whatever it is. So this would be still be accessible for compliances, auditing purposes and all, which really doesn't impact our operational database performances and all those things. So to really happen this, we might implement simple schedule job to identify, export and purge old records according to whatever retention policy we have configured. And for reading, we'll just implement read replicas of our database. Most read operations like checking payment status, generating reports and all, they will now have multiple read replicas. And even during at a scale of this kind, they can just rely on this read replicas and should be able to easily serve the read queries. Even additionally, we can introduce a caching layer using Redis or so for frequently accessed data like recent payment status and all that stuff. So that way each individual component will try to handle the scale and how do we independently scale it and make sure that it can support the numbers that we are trying to talk. And the final thing that I was mentioning is how do we expand our design to support webhooks. So by default we have currently polling based status endpoints. So here but ideally in real world they need real-time updates. Basically they will be relying on it completely to trigger business process, like I said, order fulfillments or access provisioning to digital stuff and all. So that is where this concept comes in, webhooks. So this, what it does, it allows our system to proactively notify merchants about events as they occur in our system. So this basically we need two additional information from merchants: the callback URL. So that is the URL that we will post updates to whenever we have them, and then the list of the subscribed events that we need to take from the merchants. Like for which event, if it happens, they need to know like for which event they wanted to subscribe to, so that we can notify them whenever that event happens at that callback URL. So at a high level, the flow is something, it looks like this. We'll have your webhook consumer, so basically let me just try to describe. So we have this transaction payment intent service and all. They do normal operational databases as payment progresses life cycle, like created, authorized, captured and all, and to our database. So this CDC whatever, it automatically captures all these database changes and publishes them to our Kafka event stream. So now these CDC events includes this payment statuses like changes, transaction completions and other state transitions, whatever is happening in our system. So now this webhook service or webhook consumer, whatever we have, this tries to consume from this same this event stream. So here it consumes from this event stream as additional now new specialized consumer. So whenever service the receives the CDC event, it checks now if that this if that merchant has configured any webhook endpoint, and for that event type, or like if that merchant has a webhook endpoint and has he subscribed to that specific event. If that is so, what do? We try to prepare webhook payload with relevant event details, and we try to sign that payload, and with whatever the shared secret to really enable verification, and we'll try to attempt that deliveries to merchant's endpoint like this. So now we'll try to post this one to callback URL this way. So that way we make sure that now the events as they happen on our system, we try to real time convey to our merchants through this callback URL. So this again, for each webhook the delivery attempt will be recorded with its status. So if even if that delivery fails, that this webhook service, we need to implement all our retry mechanisms, like with exponential back off, like every multiplied, like let's say 5 seconds, 25 seconds, 125 seconds. So exponentially, like till we might have some threshold like 1 hour or so. And now that's how we send on. Now on the merchant side, they need to now configure this publicly accessible HTTP endpoint to receive this webhook. Somehow they need to have listening to this callback URL, and now they should verify the signature of this incoming webhooks using the shared secret, whatever has been shared between this payment service and their internal server, to ensure that it is authenticated. And after verification, they would process whatever the payload that we have sent in webhook, and then they update their internal database records and then process with whatever the actual functionality it is. So that's how, like, we will usually try to introduce this webhook way of again as event occurs, if that merchant has a webhook callback URL and event that is subscribed to, this webhook consumer does all of the functionalities that I just described, and this basically gets this callback URL subscribed to events by calling this merchants table, and does accordingly whatever it needs to. So this is how it looks at a high level to meet at least the basic minimal functionalities that we have listed down in our functional non-functional section. Hope at least we got some gist, or at least the rough the intent and the rough flow, high level flow, and how the various components interact with each other, and how do we actually need to think about whenever we are designing a system at this scale or to meet specific requirement.
Now let's discuss about distributed cache. We all know what cache is, so it helps us to simply store key value pairs. Unlike single node cache, where we store everything in a single machine, but here the distributed cache is something that we need to scale horizontally across many nodes, machines, to handle the massive workloads that we are going to get for our servers. So that's what distributed cache is. And let's see, like, now how we can break down the requirements into functional and non-functional, and then keep elaborating from there and discuss how can we evolve this system. So breaking down the requirements, the functional ones, so it is going to be simple and straightforward, the things that we normally use day to day. So first thing is we should be able to set and get and delete the key value page. So that's the core functionality of any cache that we'll normally use. So set, get and delete key value pairs, and that's the first requirement. The second one is basically we need to configure the expiration time for specific key value pairs that we'll be storing. So that's the second requirements. The third requirement is basically the eviction. So of course every cache will have its limited size and all. So how are we going to decide which one to evict and all? So there should be some policy. So assuming that we prefer least recently used policy, so they should be able to evict as per this LRU policy. So those are like, 3 core functional requirements that we should try to meet when we are designing systems of this kind. And later also we can even add like, a user should be able to configure the cache size and other stuff, but that's fine. So now jumping onto this non-functional requirements, here we should give high preference to the availability and eventual consistency is fine. So just we need to make sure that we're always available whenever user tries to perform a specific operation on our cache. The second thing is basically low latency. So whenever they're trying to get a specific value for a key, or they are trying to update or set a value for specific key, the latency, the turnaround time should be in the bounds of like tens of milliseconds, so that it gives performance experience to the users. Then the third one is basically we should be able to scale to support and store data of size 1 terabyte, so 1024 GB, and also throughput we should be able to support 100k plus requests per second that are hitting our cluster or servers or whatever it is. So those are the the core non-functional requirements that we need to keep in mind whenever we are designing the system. And other things can be like durability, like data persistence across restarts, and then strong consistency, make sure that everything is synced up. And then how do we handle complex querying capabilities and the transaction support and all. We can just good to discussion points is something that we can add, but they're also something we can also keep into consideration when we are designing the system. All right, so now it's clear the requirements of the distributed cache, functional, non-functional. Since it's more of like infrastructure related question, so there'll be very less emphasis on the core entities and API. So I'll just roughly mention them but not discuss any much detail. So we know core entities, as we saw in our requirements, it's going to be our case and values. So those are like core entities, and APIs is basically to set a key, get a key, and delete a key. Those are the things that we normally need to have. So I'll just first is basically setting a key. So what are the key? It will be post endpoint and value that we want to set for that specific key. And then the second is basically getting a key value pair. So once the user has set, he just tries to retrieve that value for that key, and that's an endpoint that we need to expose. The third is just to delete that key value pair, and that's the like 3 core endpoints that we can think of straight away. And like I said, for infrastructure related questions, mostly these are the things like lightly emphasized, and just a quick walkthrough should be fine. So now let's jump on to high level design of picking up each functional requirements that we have drafted above. So first thing is basically should be able to set, get, and delete key value pairs. So these are like basics responsibilities of any cache. So assuming just trying to get working cache, don't even think of like distributed cache and all those things, assuming like we are doing it in single machine and all. So how it just looks, and so we all know like cache is basically simple hash table. So every programming language has one. So Python has dictionaries, Go has map, and so and also like they really help us big of one lookups and also for inserts. So the simple pseudocode might look something like this: cache, and this is the simple hash table data. To get a key, we just try to retrieve that key and return to the users. To set a key value, so at that key we set this value, and for deleting a key you just delete this. So this is like basic pseudocode to get this decent get, set, delete functionality working, and all operations are big of one, right? So yeah, this is how it's going to look like. Single server, when user makes a request, get, set, or delete, we'll pass the request and then call the appropriate method that I just showcased in the class, and we return a appropriate response. So this is how it's going to look like. So I know this is aren't at all what we need, but it's a good starting point. So now that is at least a simple flow is present, so let's pick up the second point. The second is basically should be able to configure expiration time for key value pairs that we have. So in above we just added basic retrieving, setting and deleting. Now we need to add expiration. So basically expiration, we need to somewhere store a timestamp along with whatever the value that we are storing, and then try to check during retrievals or like during read times and all. So the pseudocode, again, it's going to look something like this. Same simple hash table. Now whenever we are trying to get assuming we are storing value and along with the timestamp, kind of a tuple that we are trying to store. So I try to get that value at expiry, and I check the expiry, and then current time whatever we have is greater than the expiry. Then we know that key has expired, then we just try to delete and then not return anything. Else if it's within the expired time, then we return the value. And here while we are setting, we try to set the expiry time for that. So simple expiry time like current time, and if TTL we assume we take it as an input and add it, and then set the value and expiry for that key, and delete is going to remain the same. So this is a simple way of like taking care of able to configure the expiration time and make sure that whenever we are trying to retrieve, it's in that bounds. So this basically handles basic TTL functionality that we have just listed down. But here's the things that we need to take care of is basically as of now, if you see above, they are only cleaned up whenever they are accessed like get function. But there's a chance that our cache might fill up with expired entries and all, and nobody's requesting. So to handle that, we need to have somewhere like cleanup process, like background cleanup process. This basically what it does, periodically scans for our cache and then removes any expired entries. So it might look as simple as this. So we'll try to find all the expired keys and delete. So simple, we just try to iterate the hash table that we have and get the value.expiry and current time. If it's greater than the value.expiry, we delete that. So this way, like periodically running for every couple of minutes or so, we make sure that cache is taken care of, getting rid of all that expired keys that we have. So this is how it might look after considering the above point. So same as like as usual, we store value along with timestamps. Here, yeah, we just need to add the timestamps. I just forgot there, and then clean up process or janitor, which runs every n minutes to remove expired key value pairs. So that's how we are going to meet these requirements. Now let's jump on to the third one. This one is should be able to evict according to LRU policy that I said, least recently used policy. So here we might choose different policies like least frequently used, LRU and FIFO and other policies, but mostly used one is LRU. So so whatever the policy that we wanted to use, stick to that and try to implement that. So now here the policy, the data structure whatever we were using, they were helping for lookups, setting, getting and then deleting. But now to track access order, we basically we don't have an history of which items were used when. So that's where like we try to use doubly linked list, and that's the data structure that really helps us to track access order. So together combining this hash map and then this doubly linked list, it becomes really easy to implement an efficient LRU cache. So that really helps us to implement this LRU policy. So here it's simple. Whenever we try to add an access item, we create a node object containing that key value and expiry time, and we add an entry to our hash table mapping that key. Now the value is going to be the node data type instead of the normal tuple or value. So now once we store it in our hash table, we insert that node at front of our doubly linked list, like right before our
the dummy node. So now if we are at capacity, meaning our cache is full, we remove the least recently used item from the hash table and the linked list. In the W linked list, we store at the end, so just before the tail node. So that's how, like, that is how we try to maintain most accessible or most accessed node at the head of the linked list and least accessed node or at the tail of the linked list, so that it really helps us to perform this additions and deletions in order of big of one time. So simple. So this is how the pseudocode something kind of looks like. The class node, it will have key, value, and timestamp and other stuff, whatever the attributes that we want to do, have it in this object. And the cache, now getting key is basically we try to get the node from hash table, so as usual. So now the value is of type node, so now we try to check if the entry has expired. So if it's we have that expiry attribute, and if the current time is greater than expiry, so we know that it has expired. So we need to now get rid of this expired node both from our hash table and the linked list, correct? So for deleting from the hash table, it's straightforward. I just delete data of key, and then we need to delete the node and return null. So once we do that, now we need to move the node. So basically if it is expired, and this is how we exit. If it's not, we know that that is the most accessed node. So we know that we try to maintain most accessed node at the front of the list. So now we need to have this logic to move the node to the front of our list, and then return that. So this is how, like, we make sure that we maintain this most accessed ones at the head and then least accessed one at the tail. So basically that really helps us to perform operations like I just mentioned. The setting is also simple. We receive key, value, and time to live. Expiry will just add the current time with the TTL that we receive, and if it's already there in our hash map, we just need to update that. So we just try to get that and update the value and expiry, and then since it is the recently updated one, we need to move this to front. Else if it's a new one, we just try to add new node and then add it to our the hash map. And this add node function takes care of adding it at the front of our linked list. And if it's over capacity, once we add, we again check after adding, did that exceed our capacity. If so, we just get the the last node before our tail dummy node that we have, and then we just try to delete that, and same thing we try to delete in our hash map as well. So that way now we with the doubly linked list and hash map, we try to cleanly implement LRU policy and make sure that whatever the requirement that we have listed down, we just take care of it. So cleanup also is similar. So we try to scan from LRU and like from the tail of the doubly linked list, and so basically tail dot previous is current one, and then till we try to iterate to the front of the linked list. We keep on checking the expiry and the current time, and whichever has expired, we just try to add it to this array and then move on. And once we collect or reach the head, and we now have the keys which are expired, and then we just try to get that node from the hash map and then delete that from both the linked list and the hash map. So that's how, like, this is like rough pseudocode that the approach that we have. So this is ideally it's going to look like. So hash map for the lookups and the linked list for or tracking the access order, and make sure that the eviction policies whatever we have discussed is implemented cleanly, and then lookups is also within the bounds of a big of order of 1 times. So yeah, simple as that. I think this should be simple and straightforward, and that's what it is. So now we have like basic components tied up together and meeting the all basic functionalities that we are listed down in functional requirements. So that's like straightforward discussion. Now the main discussion when it comes to infrastructure related system designs mostly happens in our deep dives. So because that's where like we really see how we are going to manage operational complexity and then handle all this infra related stuffs and all. So let's now jump on to the deep dives one thing at a time. So the first point is how do we make sure that our cache, whatever we are designing, it's highly available and fault tolerant, and then eventual consistency is fine. So let's see like what are the approaches that we have. So basically here the key challenge is to make it highly available. I know single node really doesn't really work for the scale that we are supposed to handle. So if that node fails, and how are I going to make that cache available and all. So here we know that we need to add more nodes, but the key challenge here is the data replication. So we need like multiple copies of the same data spread across different nodes. But this really throws us a lot of questions to think about, like how many copies should we keep, and which nodes should store the copies, how do we sync the copies, and what happens if node fails or if we can't communicate to that. So those are the problems that we need to keep in mind, and then discuss the approaches that we have. So first thing is a straightforward and simple approach, synchronous replication. So here is basically what I try to do is we'll try to maintain a few replicas of our each shard whatever we have. So when a write comes in from the client, we update all the replicas whatever you have synchronously. So and only respond once all replicas have acknowledged the write has happened across all the things, and then return to the client that it is confirmed. This is fine whenever a system needs a stronger consistency, like guarantees that every write is present in each replica. But we have listed down above that eventual consistency is fine. So that's why like this is something not preferable to us. So and also the main drawbacks is basically, since now write operations must be acknowledged by every replica, so it significantly adds latency for the writes that we are going to do. And also like as we add more replicas and all, these problems whatever we are just discussing really compound with each new replica that we are going to add. So this is something, it's not our choice, and it's not going to scale for the requirements that we have in for the system. So this second approach is basically the asynchronous replication. So here is basically what we do. We try to maintain one primary copy, basically kind of like leader cache. So that's where like writes will be updated here, and then the changes whatever we have, it will be eventually propagated to all the replicas that we have in our system. So now only if leader acknowledges, that is enough for the client, and this really aligns with our eventual consistency that we have. And ideally even this Redis follows this approach currently as well. So this basically now make sure that the write performance is better, since we don't need to wait for each and every replica acknowledgement, and also higher availability guarantees, because even if replicas goes down, we can still proceed, and it doesn't really affect us. So this is like something the thing that we can take thing to follow the approach. But now here the challenges for this is failure recovery. Like let's say like one replica is failed, so now to bring that back becomes really complex because we need to understand like which updates may have been missed from that replica and what needs to be something that we need to sync back, and all those things basically adds more operational overhead. But again, it comes with a trade-off with reducing the write latencies and all. So that's something that we need to think of, like is it a good trade-off to go ahead with or not. So now let's think of the final approach. Basically it's a peer-to-peer replication. So here it is simple. So what we do, this approach, we try to give equal priorities to each and replica that we have for both writes and reads. So here we can write to any of the nodes. So we can write it to replica 1, replica 2, or replica 3, whatever we have. And then the changes that we can propagate to other replica using some protocols like gossip protocols, where nodes these nodes periodically exchange information about the state with whatever the peers that they're connected with. This way we make sure that the changes are propagated to each of its peer that's they are connected. So this really provides the scalability that we are looking for, and also the availability, as there is no single point of failure, because we have multiple nodes that we can talk to, any node that we can talk to. So that is why this is something preferable mostly, and we can decide to choose asynchronous the one or this peer-to-peer replication. So whichever suits better, it's something that we can go ahead with. So that's how now we decide to stick to meet the first non-functional requirements that we have. So now let's jump on to the second requirements. So how do we make sure that our cache is scalable? So we know that first we designed a single node cache. That's a good start, but it really won't meet our non-functional requirements of handling 1 terabytes of data and throughputs of 100k requests per second. So given these numbers, we definitely need to spread the load across multiple machines to maintain this low latency and high availability as we really grow with the data and the requests. So that's where now we need to think of the scaling strategies. So here the scaling strategy here is basically shard. We need to split, that is called sharding. So our key value pairs across multiple nodes is something that we really split, and if that is done well and taken care, now each node will basically hold a manageable portion of the data set of key value pairs, allowing us to easily scale horizontally by simply adding more machines. So let's try to calculate the numbers like we have. So this is the number. So assuming ideally decent machines on either AWS, GCP, or Azure, whatever the cloud that we are preferring, they come assume 20k requests is something that we can handle. So since now we need to handle 100k requests per second, so 100k by 20k is something 5 nodes that we need. So to have a slighter edge on buffer and unusual higher traffic and all, we can add more 3 or 4 nodes. So to handle that throughput, we ideally need 8 or no nodes to eventually have. That's to handle throughput. But let's try to consider the storage that we normally need to support. 1 TB storage, something that we need to support. So ideally each decent instance on any cloud provider, let's say that it has 32 GB RAM. So given deducting all system overheads and all, we'll have around 20 GB or 24 GB RAM that we can use for our cache. So since now we need to store 1 terabytes, which is 1024 GB, so 1024 by 24. So how many instances something we need? So around 45 plus or something. So just adding again buffer and all, we need approximately 50 nodes. So again, this number can significantly vary based on the instance type and then the caching, memory usage, and CPU specifications and all that we have. But roughly this is the ballpark number that we normally need to have. So since now you see the nodes ideally now we need to maintain is around 50 nodes to meet both the throughputs and then the storage that we have. So this way we need to estimate, and based on these several factors we need to make sure that we have the right instances numbers that we are going to think, and make sure how we are going to scale. So that's how like we try to scale using this sharding. Now we have this 50 nodes or whatever it is, but the bigger question is now how do we know like which node a given key value pair should be stored on. So that's the thing. Now the next point of discussion, so we need to ensure that even distribution of keys across all our 50 nodes whatever we have here. So the answer for that is the consistent hashing. So ideally if we don't have consistent hashing, how do we normally store is basically we try to follow simple modulo operation. Let's say like I have like 10 nodes, then if key value pair comes in with some particular key, like let's say a build, so hash of that build gives me some particular value and modulus of that number of nodes that I have, so modulus of 10. So whatever the number of the node that I get, so I use that node number and try to store the key that we have. So this way we try to store, but here the question is the nodes are not fixed, because we know that traffic is going to be higher and we need to make sure we are highly available and scalable. So there's always situation of adding a new nodes and removing a new nodes. So whenever that happens, we need to make sure that the distribution keys is something that we don't have to redo our work. So that's where like consistent hashing really helps us. So this basically so basically what is this is simple technique which helps us to distribute keys across our cache nodes, while trying to minimize the movement of keys that needs to be like remapped whenever we add a new node or remove existing one. So now instead of simply using modulo arithmetic to find the right node, this consistent hashing is basically uses a function called something like murmur hash to get a position on the circle. So ideally how, assuming they will be arranged in a circular way, so this is just for representation. So let's say like I send a one key hash of like build, so it gave me some number of like 26. Then what we do, we try to find the 26 on the hash ring that we have. So it comes here somewhere this. So what we do, we try to walk clockwise until we hit the next node in that clockwise direction. So once we find that, so that's the node where we need to store the this key value thing. So this way we make sure that keys are evenly distributed. So now if nodes are added or removed, let's say like this node is removed, so whatever the values that were in this range, only this has to be moved to this node. So basically only this the nodes the keys or values which are in that range, only those has to be remapped, not like no need to worry about all the remaining things that we have. So this is how it really helps us in minimizing mitigating the moment of remapping of lots of keys and all. That's what like consistent hashing really helps us with evenly distributing keys. Now let's talk about hotkeys. Of course, everywhere, wherever we go in whatever the system that we design, there will always be scenarios of hot keys, either of reading related thing or writing related thing. So let's first try to worry about the heart rates. So basically heart rates is something that the key that receives like extremely high volume of read requests. It can be something like, let's say viral tweet or related data, or like viral video that people are trying to view and all. So let's see how we are going to handle this hot reads and all. So simple approach is basically vertical scaling of all nodes. So simple, this is I think the standard way that we normally try to do it in the first curve. Like we try to scale up the hardware of all nodes, like increasing CPU, memory and network capacity across the nodes whatever we have. And this is an expensive, and we know this really doesn't scale well, and also everything will have its limit, and we are going to definitely hit that, and it's going to be bottleneck more. And also here irrespective of that being hot or not, we are increasing all the nodes, and it's going to linearly add up more cost for our, and this is going to be really unsustainable whenever there are more nodes in our cluster. So this is something big no that we cannot go ahead with. And the other approach is basically having a dedicated odd key cache. So this strategy, what it really, like, to put in the simple words, we'll try to have some monitoring solution that tries to identify which are odd keys and all, and then it will try to help us partition into dedicated odd key caches, so that it really doesn't affect our main cache. So the other normal keys will try to hit this caches and get the values, but the hard cache is something that we try to separate it and make sure that the overall stability of the system is not affected. And that's how we try to maintain. So once we identify particular key is hard, we promote that to our hard key and all. So again here for hard key cache, since we know it's the people are trying to view more often, then we can have some powerful hardware, more RAM and all that stuff, so that it can significantly deal with that traffic that we are hitting. But here the challenges here is basically we need to maintain consistency between the main cache and the hard cache, and we need to again come up with very decent sophisticated monitoring to identify which are hard keys and all that stuff. So anywhere any approach that we decide, there will always be an additional operational overhead in maintaining separate caching infrastructure and all that things. Again, it comes off with a trade-off, and we need to deal with that. So this is one thing, dedicated hotkey cache. And now the other, basically anywhere whenever we talk about high availability and with replication, this is always we try to create copies of the same data across different nodes, just to make it easy to distribute read requests across the replicas, and that's how these things come in. But here again it really improves our overhead in terms of storage cost, network bandwidth, and since because entire nodes needs to be replicated irrespective of they're hot or not, and this is also something that we really don't want to go ahead with. So ultimate the final solution is basically trying to create a copies of just the hotkeys irrespective of all the keys and all. So here this is how it really works. So first, like I said, we'll have some decent monitoring solution to identify key access patterns, and then identify which are out keys that are frequently read. So when we identify particular keys hard, so instead of we having just one copy, let's say key 1 is key 1 1 to 3 or something, the system, what we'll try to do now, we'll try to create multiple copies with different suffixes. Let's say key 1 is to key 1 #1, and then here key 1 #2 and all. So this node A stores this and node B stores this. So now these copies are getting distributed across the shards, so via this consistent hashing that we just mentioned. So now for reads, whenever a client can just randomly choose any suffix, and then this will try to spread the read load across the multiple shards of the node that we have in our ring. So but here we are optimizing read, and of course it's going to have an write. So for writes, the system must try to update all the copies to maintain consistency. So yeah, so let's say we have some offer big billion days or some flash sale is happening on big e-commerce platforms for iPhones or other things. So product iPhone, assume it became hotkey with 100k requests per second, but only one write. So with now with copies, 4 copies, each shard can handle 25k reads per second, and write needs to update all 4 copies. So but without copy, single shard has to deal with the 100k requests per second that we ideally need to handle whenever client tries to make a request. So that's how we try to get rid of the load on a single shard and try to distribute across the multiple shards and so on. So that's the trade-off that we normally try to always think in terms of to deal with, and what is it something that we can afford to have, and what is it that we cannot afford to have. So these are like the approaches that we can stick to, but ultimately just we try to choose the ones which really yield maximum benefits for the resources or the constraints that we have at our stake. Right. Now the next point is, so now how do we handle, what happens like if now we talked about reading a thing. So now what if that hotkey is being written to a lot? So here is basically, let's say like viral video or viral tweet, we need to keep updating the views count or likes count on other things, right? So viral things, so how do we make sure that, so ultimately whenever it comes to reducing writes, the first thing that should really strike our thinking is basically batching them writes. So here by instead of doing every write for an operation, we try to collect multiple write operation for some short window time. It can be like maybe few hundreds of milliseconds or seconds, and then we try to consolidate them into single operation, and then try to update in our DB. So this basically is mostly best for counters, metrics, and where just the total count matters really at the end. So like I said, video is one example, tweet is one example, and search for likes count and all those things. So that's one way. And also again, this if we do, there might be little delay and write visibility for the ones that we are trying to further read stuff, but that's fine. And in these the other way approach is basically sharding hotkey with suffixes. So here now what is this basically is to handle the hard writes, we try to split hotkey again into multiple subkeys. We try to distribute across different nodes. So now let's say let's say we have for views video 1 to 3. So we try to split into multiple shards, like video views video 1 to 3, and had extra suffix like 1, and till through 10, the number like views video 1 to 3 colon 10, like that from 1 to 10. So now when a write arrives, the system randomly selects one of the shards to update, and this basically effectively distributes writes load across multiple nodes in a cluster. And let's say we have 10,000 writes per second. Now we have distributed across 10 shards, so now each shard will be easily able to accept 1,000 operations per second, and that's how we try to handle hard writes that we have. Again, here now we are handling writes things. So whenever reads happens, so again we need to recompose from all the 10 shards and try to give the final number or so. That's again the trade of decomposing and recomposing that we need to keep in mind whenever we're trying to optimize writes, and then take care of reads. Whenever we optimize writes, take care of writes. That's how we always have to deal with. And finally, this is how it's going to look like. Make sure the ultimate thing is basically we need to make sure that our cache is performant. So we have taken care of all the points. Basically we discussed about consistent hashing, and also discussed about how do we handle hotkey writes, hotkey reads, and also taken care of the scalability nodes and all every stuff. So basically as we scale, the question is not going to be about how fast hash table runs in a memory and all. It's going to be about how quickly the clients and the nodes can connect with each other, because it's as we keep adding more nodes, there'll be a lot of network instability, and network round trip time is something that's going to add up. So that's the number that we need to really focus on, and make sure that the tail latencies that we normally see, like P95 and P99 response times really are in the bounds and all those things. So constantly trying to keep an eye on those things is what really matters. And assuming we have now finalized like asynchronous replication for high availability and handling odd key reads, and consistent hashing for sharding and routing, and random suffixes for distributing hard key writes across nodes, and then write batching and connection pooling for decreasing network latency are overhead, assuming we have chosen all those points. So this is how it's going to look like, asynchronous replication, and then batch writes with connection pooling to avoid network latency and all that stuff. So this is how the normal navigation or the discussion to meet the requirements of a system like distributed cache really evolves, and hope at least you got maybe a couple of points as a takeaway from this video and learned a bit. I assume you at least got some gist and the overall flow that we should really think through and navigate, I guess. Alright, that's it for this one. Let's catch up in the new one. Now let's discuss about a system like Uber or Lyft or Ola or other similar platforms. So we all know what is at the high level what Uber does. So it's a ride sharing platform that helps us to connect the passengers, that is riders, with drivers who offer transportation services in their own personal vehicles and all. So users can book rides on demand from their phones, and then that helps to match the drivers who are available nearby, and then they will take to the respective desired destination. So that's what, like at a high level, Uber does, the core functionality of what they do. So now that we know what it does at high level, let's try to break down the requirements that we need to accomplish into functional and non-functional. So looking at the functional requirements first, so the first usual requirement that we should meet when we are trying to design a system of this kind is to provide an option to riders to input the start location that they are trying to start from, and the destination to which they wanted to reach, and get a fare estimate. So that's the basic functionality that we should try to provide. So input a start location and also add a destination, and then try to first get the fare estimates so that they can decide whether to take a ride or not. So that's the first requirement that we should meet. And the second requirement is they should be able to request a ride based on whatever the fare that we have given in the previous requirement. So if the fare is in within their budget, then they will just proceed to request a ride, else they will just look for the alternate options. That's the second requirement. The third requirement is, upon we receive ride request, then that specific rider should be matched with a driver who is nearby and available. So that's the third requirement. So whoever is available nearby in the proximity range, we should try to match with them, and just try to link that driver to that specific rider. So that's the third requirement. The fourth one is basically once we match with the driver, then the drivers should be able to either accept or decline a request, and accordingly if they accept, we should also help them to navigate to pick up location and also the drop off location once they pick up the rider. So those are like key requirements that we should meet. So since the functional requirements are clear, let's try to move on to non-functional. Still there can be more functional requirements that we can even discuss, like a rider should be able to read the ride, and the driver as well post trip, so and vice versa. And then also rider should be able to schedule their rides in advance, and they should be able to select different categories of like XL, comfort, and then other categories which are like premiums, and all those additional functionalities that we can add. But now we'll just try to stick to basic core functionality of the system that we are trying to design. So jumping onto the non-functional requirements, so here basically
we'll try to keep as simple as possible. So whenever we're trying to match the rider with the driver, so the matching should be very very fast, that is low latency, might be just kept under 1 minute or so, so that we provide best user experience for the users on the platform. Then the second is the strong consistency in ride matching for a driver. So here we should make sure that we don't send multiple simultaneous requests to the driver, so that so that the duplicacy of the ride request is not sent to the driver, and we should make sure that it's taken care in our system. So yeah, simple. We just need to prevent any driver from being assigned multiple rides simultaneously. So that's the second non-functional requirement that we should take care. And the third is basically we need to make sure that our system is very scalable, reliable, and can handle high throughput, especially during peak hours. It can be during office hours, or like any festivals or any event or any the things, special events. So it can be like we receive in 100 of requests from the same location and all that stuff. So keeping all those things in mind, we should design our system such that it will handle. And rest it can be others non-functional. We can think of like having a proper CI/CD, so that changes that we make is pushed in a less span of time, and then monitoring systems logs, and then fault tolerance and all those things. Those are like always will be part of any system that we'll normally design. Right now functional and non-functional are clear. So let's go to our next discussion, which is the core entities that are involved in this system. So first core entity is a rider. So basically this is any user who uses the platform like to request rides. And this includes personal information such as like a name, contact details, their preferred payment methods for ride transactions, and so on. So that is this entity. And the second entity is the driver. So again, this whoever are registered as the drivers on our platform, and they provide the transportation services. So again, this has a personal details about them and vehicle information like model, year, make, and other preferences, availability status, and all those details that we normally need in our system. So that is this entity. And the third entity is a fare. So this basically represents the estimated fare for a ride. So it includes like what was the pickup location and the destination locations, estimated fare, and what is the ETA, estimated time of arrival. So this could also be part of this ride object, but for now we just keep this as separate entity so that it's better for us to maintain as well. So the fourth entity is a ride. So this basically represents what the individual ride from a moment a ride confirms a fare estimate and a request a ride all the way until its completion. So it records basically all details of a ride, including the identities of the rider and the driver, vehicle details, state, the planned route, actual fare charged at the end of the trip, timestamps marking the pickup and the drop off, and all those details basically throughout the journey of from the pickup to the drop. That's what this entity does. And the next entity is basically location. So this helps us to store the real-time location of drivers. So it includes maybe latitude, longitude, coordinates, as well as the timestamps of the last update of specific driver or so. This is very crucial for matching riders with the nearby drivers, and helping us to track the progress of a ride. So these are 5 main entities that we can straight away think of when we are trying to design systems of this kind. So now that these core entities are clear, let's jump to the APIs or system interface or contracts that we need to expose. So first is fare estimate, straightforward. So here this is a post endpoint. So basically here just takes in user's current location, that is a pickup location, and desired destination, and then we return a fare object that I just described above, what it all contains and the stuff. So the second endpoint is requesting a ride. Again, this is going to be a post endpoint. So this, once the user is satisfied with the fare that we have estimated above, and once he chooses that, we pass in the fare ID and then return the ride object. So this is the process to request a ride. Then the third endpoint is basically to update driver's location thing. So this is going to be also the post endpoint, driver's location. So we take in here the latitude and longitude, and along with that, in session cookie or JWT, we'll have driver ID, and then update our location DB or whatever we have, so that we'll know exact driver's locations that we have. Alright, so that's the third endpoint, which helps us to update driver's location. And the fourth endpoint is like patch endpoint, to accept or deny a ride request for the drivers. So once we send a ride request to the driver, they can either accept or deny, and that's this endpoint that we normally update our status in our DB. So these are like, core endpoints that we might need, and if we need additional things, we will add in as we evolve into our deeper discussion. So now let's take one point at a time from our functional requirements and try to elaborate more and discuss possible approaches that we can think of to meet the requirements. So the first requirement is basically we should be able to input start location and a destination, and get a fare estimate for that specific user. So this is going to be as simple as the design, straightforward thing. So I'll just try to keep it as simple and faster. So here, this is how the flow it might look, the components that we have. So the core components that we have here is basically the rider, the primary it can be iOS or Android device, where the client really interacts with our system's backend services, and also an API gateway, the standard things which helps us with auth routing, or rate limiting and other stuffs. And then we have the ride service. In our first point for this case, this is simple microservice which helps us managing ride state, starting the with fare estimates, and it interacts with third-party mapping service. It can be Google Maps or Apple's Maps or other third-party mapping APIs to determine the distance and travel time between locations, and applies all our internal company's business logic, pricing model to generate a fare estimate. So we abstract all of that stuff, and that's not like discussion point for us for this system. And and the database, so it can be Postgres DB or DynamoDB or whatever, that just works fine. So here we have fare entity, so it can have fields like ID, user ID, source, destination, price, estimated time of arrival, and others metadata that we wanted to keep. So this is the rough flow. So if we briefly try to walk through the flow, how it looks like. So here this rider enters their pickup location and desired destination, and they sends a post request to our endpoint, that is can be like /fare or whatever it is thing, through our API gateway. So now this API gateway receives a request and handles all necessary authentication and rate limiting before we forward it to our ride service that we have. So now once we receive to our ride service, it makes a post or request to the third-party mapping API to calculate the distance and travel time between the pickup and destination locations, and applying a company's pricing model to generate actual fare estimate. So once we have that fare estimate, we create a new fare entity in our database with details about the estimated fare, and then we return this whatever the fare estimate that we have stored to the user and showcase it in our platform. So that's the rough flow it's going to look like, and this is how we are going to meet our first functional requirement. So now the second functional requirement is they should be able to request ride based on estimated fare. So this again it's also straightforward, so there's no additional service needed. We'll just have this ride service itself handle that ride creation. So simple, the user confirms their ride request in the client app, whatever the fare estimate that we sent, and then once they confirm, we send a post request to our the ride service with the ID of the fare they are accepting. Then the API gateway, whatever it just performs its regular functionality of authentication, rate limiting before forwarding it to our ride service. Then this ride service receives the request and creates a new entry in our DB. So ride object, ride table can be like ride ID, rider ID, driver ID, fare ID, source, destination, the status, and all that stuff we store. And once we store this thing, and then we need to trigger matching flow so that we can assign a driver to the ride. So that is the next requirement. So here should be matched with a driver who is nearby and available. So now here we introduce some new components. So new components here is the driver, so they'll have their own interface like separate app or so. So here this driver client, which is the like interface for drivers to receive ride requests and provide location updates. So this driver component, it interacts with our location service. So this basically helps us to manage real-time location of the drivers. So it receives the basically location updates from this drivers and stores this information in our database. So here we try to keep constant latest driver locations things, so that really helps us to find the drivers who are nearby and in the proximity range. And then new other component is ride matching service. So this basically handles from the ride service the request to match the rider with the driver. So yeah, with the best drivers available based on proximity, availability, driver rating, and other relevant factors and all that stuff things. So it tries to talk to this DB and get the details that we need. So yeah, the rough sequence is simple. So the user confirms the ride request in the client app, which sends a post request to our backend system with the ID of the fare they are accepting, that is the ride service. Then the API gateway does all the job. Once this ride service creates a ride object in our DB, then we need to now forward that request to our this ride matching service, which now triggers this matching workflow. So we'll discuss a way like how do we match, make this robust later, and also and all such things. So now once we trigger this matching, at all the times we'll have this location service receiving the current location or latest location updates from this driver clients, and we are updating our DB with the latest latitude and longitude, so we know where they are. Then this matching workflow uses these updated locations in our DB to query the closest available drivers in an attempt to find the optimal match and provide the driver to the rider. So this is how it's going to look like, rough flow. I know it's basically high level, and that's the intention as well. So that's the third requirements. Now the fourth requirement, as a follow-up, is now they should be able to accept or decline a request and navigate to pick up or drop off accordingly. So here we need additional new service to support that. So we have this here, this notification service. So basically this is what responsible for dispatching real-time notifications to drivers when a new ride request is matched to them. So basically once we find a suitable driver using this ride matching service, we should somehow let them know that they have a ride request or so. So that is where this notification service comes into the picture. So it ensures basically drivers are proactively, promptly informed so that they can accept a ride request in a timely manner, thus maintaining fluid user experience and all. So usually notifications sent via this API, Apple's push notifications, or for iOS or for, FCM, Firebase Cloud messaging for Android's devices respectively. So this sends notifications to the driver's interfaces to accept or decline, right? So now the flow is basically this after this finds the suitable driver, it sends a notification to drop top driver on the list via this APNs or FCM. Then this driver, whoever is the one, receives a notification that new ride request is available. So they open this client app and accept the ride request, which sends the patch request to our backend system through our API gateway with the ride ID. And so that is like if they accept. If they decline the ride, then system will send a notification to the next driver that we had in our list based on the proximity that we got. So and it receives that and routes through API gateway to our ride service. Then this ride service receives the request and updates the status of the ride to accepted or denied, or so accordingly, and then it returns the pickup location coordinates to this driver, so that he knows where to go to pick up the rider and where to drop the rider. So this is once he receives the coordinates, he'll use on client GPS to navigate the pickup location and so this is how we try to meet this accept or decline a request and navigate to pick up or drop off location accordingly. So now that we are clear and on basic rough flow of all the functional requirements, let's take a few additional points in our non-functional and then few add-ons to see how we can meet those requirements as well. So first, deep dives is basically how do we handle frequent driver location updates and efficient proximity searches based on the location data. So here there are two main problems with our current design. If you see, if you have closely observed in the above flow, basically high frequency of rides, given we have around let's say a few millions of drivers, let's say 10 million or 20 million drivers, so sending locations roughly every 5 seconds, that's about if we assume 10 million drivers, we have 2 million updates a second. Whatever the DB we choose, it can be DynamoDB or PostgreSQL, either one would fail under this heavy load. So definitely we need to think how can we reduce these write-ups or scale up so that it handles this. And also now that was with respect to writes, and with even respect to query efficiency, to even query table based on lat long, we would need a full tables scan calculating the distance between each driver's location and the rider's location. That would be extremely inefficient. So especially even with indexing on lat or long columns, the traditional B-tree indexes that we normally use in our relational databases are not well suited for multi-dimensional data here geographical coordinates, so leading to inefficient query performances and also. So these are two main problems that we should keep in mind and see how we can evolve or to solve those problems. So let's see what are the approaches that we can see. So here, direct database writes and proximity queries. So here as we simply described above, we just straight away choose some relational database and write each driver's location update to database as it comes in, and then we perform proximity searches on its raw data. It's a very bad approach, and it doesn't really scale well with high volume of updates from millions of drivers, and even proximity searches are inefficient and slow as I described above. So this approach is basically not suitable for us to pick. And the others is basically whenever we wanted to reduce the writes, the first thing that triggers our mind is basically batch processing, so that we can at least reduce the writes and also try to use specialized geospatial database. So now the first point is, instead of writing each driver's location update directly to database, we aggregate over a short interval or time window and then batch process. So this basically helps us to reduce the number of write operations. And when it comes to now for proximity searches, we can try to lean towards specialized geospatial database, which really comes with appropriate indexing, which really helps us to efficiently query nearby drivers. So for a specialized database, that has like a specialized data structure called like quad trees, to index driver locations, which allows for faster execution of in this searches whatever we do. So that's what, like, they are exclusively designed for this two-dimensional spatial data like geographical coordinates, as they partition the space into quadrants recursively, so which can significantly speed up the process of finding a drivers in that specific quadrant within certain area after around a ride request. So that is why we need to lean towards this data structure. And even if you choose the Postgres, it has a plugin called PostGIS that allows us to use geospatial data types and functions without needing the additional database. So this is how we can think towards of reducing this the writes, and also the making queries efficiency proximity searches. So but still here it introduces batch writes, delay and all that stuff, which means the location data which we have in our database might not really reflect the current location of the driver. So this can lead to even the suboptimal outdated proximity searches and all. So that's why we even don't want to choose this. So the ultimate approach that we lean towards is real-time in-memory geospatial data store. So here we can address all of the previous problems that we have noted using the in-memory data store, the Redis. So here what we do, it by default it has like comes up with geospatial data types and commands. So that really helps us to handle location updates and private proximity searches with high throughput and low latency, which is what we need. So it uses geohashing to encode whatever the latitude and longitude coordinates into a 52-bit integer score within a sorted set, where each member, example it can be driver ID, is associated with that geohash score. So this allows for the efficient storage as well as querying of the geospatial data for proximity searches. So it has a commands like geo add for adding location data, and geo search for querying nearby locations within a given radius or a bounding box that we need to search. So these commands really helps for highly optimized data that we really need, and helps us to handle real-time driver location updates. And also, so that's what, like, now we no longer have to need for batch processing, since Redis can handle this high volume in real time. And also since each geo add command overrides the previous location for a given driver, we always have the most recent position, so there's no delay or such. And there can be scenario we need to handle stale data when our drivers go offline. We can run a periodic cleanup process that removes drivers whose last updated timestamp exceeds a threshold of, let's say, like 30 seconds or so. So this approach can be like to maintain companion sorted key keyed by timestamp, and periodically remove entries older than that threshold, can be like 30 seconds or 1 minute. And so like this we can have timestamp set and geo set and handle those cases that I just described above. So this is how we try to handle the first requirement, that is like frequent driver location updates, and make sure that we have efficient proximity searches and all those things. So ultimately relying on this location DB, Redis, and the commands that it comes up with, geo add and geo search, and then maintaining timestamp set and geo set respectively. So others thing, even we can even complain about what about durability. So since Redis is an in-memory store, there's a risk of like data loss in case of system crash or power failure. So this can be mitigated in a few possible ways, and that's the problem we even don't have to think about. So Redis persistence, so we could enable that persistent mechanisms like Redis database or append only file to periodically save whatever we have in our in-memory to our disk. Or we can even go with the Redis Sentinel, which really guarantees high availability. So it provides automatic failover if master node goes down, the another replica is promoted to master. So this is how we handle this proximity searches and location frequent updates and all. So now let's go on to the second non-functional requirement. So how do we handle system overload from frequent driver location updates while ensuring location accuracy? So this basically we know that we are receiving driver location updates very frequently, and a lot of rides even for that every 5 seconds or so, like the ping. So even given the volume of the drivers that we have in our system, how do we make sure the system is still stable? So here that's where we can think of like adaptive location update intervals. So here we need to dynamically adjust the frequency of the location updates based on like some external or contextual factors, such as like speed of the driver or the direction of the travel of the and the proximity to pending ride request and driver status. So here that based on those factors we can reduce the number of location updates while maintaining accuracy. So here simple, we know that drivers have the mobile device, uses on device sensors and algorithms to determine the optimal interval for sending location updates. For example, let's say what do I really mean here adaptive location update intervals? If driver is stationary or moving slowly, then updates can be less frequent, because we know that he is coming on the same route, and then even if updates is in 10 seconds or so, we get the accurate location since he's moving slow. But if driver is moving quickly or changing directions often, then we need to know immediately its location. So that's when we can increase the frequency of updates that are being sent to a system. That way, based on all of these factors and leveraging clients sensors and algorithms that comes in built on devices of iOS and Android, this way we can try to reduce the frequent updates and manage system overload within our capacity. So that's the second requirement that we try to meet. This third requirement is basically strong consistency, like basically preventing multiple ride requests from being sent to the same driver simultaneously. So how do we handle this? So let's see, like this is I think should be simple and straightforward. So let's see what are the approaches that we can brainstorm. So first is basically we can think of is application level locking with the manual timeout checks. So here the key intuition is that we need to lock drivers to prevent multiple ride requests from being sent to them simultaneously, right? So here what we do is when the each instance of the ride matching service that marks a ride request, we try to lock when it is sent to the driver. It then starts a timer for that lock duration. If the driver doesn't accept the ride within that period, the instance manually releases the lock and makes the request available to other drivers that we have in our list. So but still, if we choose this, there are a lot of problems with this lack of coordination. So with multiple instances of ride matching service that we have in our system, there's no centralized coordination, so it can lead to potential race conditions where two instances might attempt to lock the same ride request simultaneously. So that's the one problem. And then inconsistent lock state. So if one instance sets a lock but fails before releasing it due to crash or some other network issue or whatever it is, other instance has no knowledge of this lock, which can leave the ride request in infinite lock state, and it might lead to very very bad user experience, and user is waiting infinitely. Then the scalability concerns. So as the system scales, the number of instances we know they drastically increase as well. So now the problem of coordinating logs across instances becomes more bottleneck for us, and it's not something we cannot tolerate. So that's why this approach is something we cannot go with. And the other approach, better approach on top of the previous one we can think of is database status update with timeout handling. Now instead of relying on in-memory logs, so whenever we send a request to driver, we could update the status of that driver to like outstanding request or so into our DB. So so that we know that the driver is still yet to accept. So if the driver accepts the request, we update the status to accepted, and if they deny it, we update the status back to available. So we then use a simple timeout mechanism within this whatever the write service that we had in our system, to ensure that lock is released if the driver does not respond within that 10-second window. So that's how, like, we try to shift from in memory to combination of this db plus in memory timeout window that we have. While we solve this coordination issue here now with the status update in our db, we still run into issues whenever you try to rely on in memory timeout to handle unlocking if the driver does not respond. So that is, if ride service itself crashes, a timeout will be lost, right? So now again the lock will remain indefinitely. So that's a problem again we are still dealing with. So to solve all of that is the approach that we need to go with is distributed lock with TTL. So here simple, to solve this timeout issues, we can use a distributed lock in an in-memory data store like Redis. So when a write request is basically sent to this driver, we can create a lock with an unique ID. Here basically it can be driver ID, and the TTL can be set to the acceptance window duration, so of like 10 seconds or 1 minute. So now this write matching service, whatever we have, so it tries to now use this distributed lock, that is Redis, to acquire a lock on driver ID. So if the lock is successfully acquired, it means no other service instance can send a write request to the same driver until that lock expires, which automatically TTL takes care of that. And once if the driver accepts the request within that TTL window, the write matching service, whatever we have, it updates the write status to accepted in the database, and lock is released in the Redis. So if the driver does not accept the write, then the lock in Redis expires automatically, so we don't have to do that. And this way the challenges that we described about coordination and in memory lost and all those things is taken care by this distributed lock, and with automatic TTL expiring and all that stuff. So that's how we try to take care of this requirement of making sure that we don't send multiple write requests to the same driver simultaneously. So here distributed lock with it Redis is what is our savior. So now let's move on to the next requirement. So here, how do we ensure that no write requests are dropped during peak hours? This is very, very important. So it can be like whenever the office time, or it can be like festivals times or any special events time. So let's see how do we make sure whatever the write requests that are coming to a platform, we never drop even single of them. So the approach is basically, let's see, like here first is basically what we have currently here is first come first serve with no queue. Here basically we try to process requests as they come in without any queuing system. So that is what is there currently in our system. And here the main issue that comes is it really does not scale well with high demands periods. So as the number of incoming requests increases, the system may become overwhelmed and it start dropping requests, leading to poor user experience. And we can still scale our write matching service horizontally to handle more requests, but with sudden surges in demand, we may still not be able to scale quickly enough to prevent those dropped requests. So that is why whatever we have in our current design, that's not acceptable. So we need to think of the other approach. So the other is basically we need to introduce a queue with dynamic scaling that comes up with. So here basically we need to introduce a queuing system. When a write request comes in, we should try to add it to our queue. So maybe it can be match queue or whatever it is like first come first served manner. So if the queue grows too large, we can scale the services, that is ride matching services, horizontally by adding more instances of them, so that it can pick up whatever the request that we have in our queue. So this basically introducing a queue system and dynamically scaling based on the queue sizes and all. We ensure that no requests are dropped, and also we can even partition the queue based on geographical regions and to further improve efficiency. So we can use here something called like distributed message queue system like Kafka, even which allows us to commit the offset of a message in the queue only after we have successfully found a match in our ride matching service. So this way, even if ride matching service goes down, the match request would still be in the queue and a new instance would still be available to pick it up. So this way we make sure that we doesn't drop any ride request and all that stuff that comes into our system even during any peak demand hours or any rush hours or so. So now let's go on to the next requirements. So the next requirement is what happens like if a driver fails to respond in a timely manner. So here basically our system right now works great whenever driver either accepts or denies request. But what if they doesn't act on either options? They just drop their phone in passenger seat or somewhere in the car. So how do we ensure that ride request continues to be processed so that we can send it to our next driver in our list or so? So that approach is basically the delayed queue. So let's see here. This is where like multi-step processes is very important. So what one approach that we can think of is delayed queue. So here we can implement to automatically retry ride request with the next available driver if that current driver doesn't respond within the timeout period. So when a ride request is sent to a driver, we simultaneously what we do schedule a delayed message in our queue. Let's say we are using Amazon's SQS, so we schedule a delayed message with a time of after the like 10-second timeout period. So the delayed message, what it ideally contains is the ride request details and the driver who was originally contacted. So when the delayed message is processed, the system checks if the ride is still unassigned. So if so, it automatically moves to the next driver in the ranked list and sends them the ride request, while again scheduling another delayed message with the details of that driver and the ride details, so that again later it can check if it's still unassigned or so, and pick up the new driver in our ranked list that we have. So this basically ensures that ride requests continue to be processed even if drivers don't respond, maintaining system resilience and improving user experience by reducing wait times. But the main challenge here with this is basically multiple delayed messages, that's like complexity rises. So ensuring like how do we they are properly cancelled when a driver accepts the ride. So if first driver accepts the ride, so how do we properly cancel the next delayed message that we have already put into our queue? So these like multiple additional complexity, something really makes us not to pick this approach. So other ultimate approach is basically go choose durable execution frameworks like temporal, which I exclusively extensively use at our work as well as in personal projects. So or we can choose for AWS step functions. So those systems are built specifically for this kind of scenarios, which comes up with built-in support for timeouts, retries and state management in a way that it survives even services crashes and restarts. So here for example, for our use case here, the temporal workflow might look something like this. So we try to send a request to the first driver and set a 10-second timeout, and if the driver accepts, we just complete the workflow and that's done. So but if the driver declines or times out, we automatically move to the next driver and continue this process until driver is found or all drivers are exhausted. So this is how the temporal workflow looks like, and temporal takes care by default retries and state management and all that stuff. So this is how we make sure that it is tolerant and can handle service failures, network issues, and other disruptions, without really losing any state or dropping ride requests. So that's how we take care of this, if even driver doesn't respond in timely manner, to go for next driver, and so then the last requirement is, how do we even further scale our system, to reduce the latency and improve throughput? That's what, everyone always tries to think, to make sure that their system performs well no matter the situation. The first thing normally we think of is scaling, vertically scaling. So where we increase the capacity of every services, servers, whatever we have, by adding more CPU, memory, or storage. That is a quick and easy way to increase capacity, but it has several limitations. So we all know, this definitely sucks. First is, it's expensive and it requires downtime to upgrade the servers, and second, it's not infinitely scalable, and at some point we'll hit the limits of vertical scaling and need to scale horizontally. And and also a single point of failure. What if it goes down? Whole system goes down. So that's why this is never the approach solution in a systems of this scale. So the other approach is basically geo sharding with read replicas. So here is basically what we do. We try to scale horizontally, of course, to add more servers, and we can do this basically by sharding our data geographically. And also using read replicas to improve our read queries or read throughputs. This applies to all services that we have in our system. So this indirectly helps us to reduce latency and improve throughput. So that way we can make sure that we handle the throughputs, the numbers that we're supposed to meet, and also less latency. So the only time that we need to scatter together like across multiple shards is geographically, whatever we are split, is whenever we are doing for a proximity search on the boundaries. Like if a user is in like boundaries of like particular country or other country, then we need to look for that shard as well as this shard. So then we need to combine this both of them together, which is like rare of such situation, and that can be handled and in our system if you even try to geographically shard and with more read replicas. So this is how final system design is going to look like. I know we rushed a lot, and we at least tried to cover more of a situations and scenarios and use cases at a high level and rough flow, and how can we navigate, and I hope you got at least a few points from this and learned a few new things or so. And let's catch up in the new one. Now let's discuss about a system problem on Zerodha or Groww. So we all know what those platforms do, and ideally what are their main functionality. So they are simple commission-free trading platforms for stocks, ETFs, options, and besides similar platforms, they also do cryptocurrencies and all that stuff. So they provide us with real-time market data and help us with basic order management and all that stuff. So that is what like Zerodha or Groww does. And just to be on the common ground, they aren't an exchange by themselves, but rather a stockbroker. So they route trades through market makers, which is exchanges. In our case, it is like BSE, Bombay Stock Exchange, and NSE. And if it's like US or something, it can be like NYSE, New York Stock Exchange, and other stuff. So that is what these two main platforms does. And now before we start this, we need to have a simple idea of simple terms in the financial markets. One is a symbol. Symbol, we know, like the stocks that we trade, that is like used as a unique identifier for a particular stock. So it can be a Reliance, or it can be like Apple, if it's a US market or so. They are like unique identifier, and with that symbol is what they will be traded on a market that is being publicly traded. And the second jargon is order, a simple the way to buy or sell a stock. So it can be market order or limit order. So here the market order is nothing but the immediate purchase or sale of a stock at whatever the price that it is trading currently in the market, and that's what like market order is. And limit order is basically we try to make an order either to purchase or sell at a specified price. So if that price is hit, then the order will be executed. So that is what like limit order is. So now we know the basic jargon of at least we'll know when if we are trying to address it as a symbol order, market order or limit order, we'll know what those really is. Fine. So since I mentioned this are like pure stockbrokers, so we of course assume that we have an interface with an external entities which really gives us the order processing related APIs to place order or cancel orders via the request response APIs, and the endpoints are so for trade feed basically helps us to subscribe to their trade feed for symbols, which helps us get the data to our clients or customers and all those things. So these are like we assume that we get from market makers, and that's the assumption that we will try to proceed to discuss with. So now that we know at least the basic idea, let's drive to our functional requirements. So requirements, as we all know, we try to break down always into functional, non-functional requirements. So first here the functional requirements, I think they will be straightforward and simple. So let's see what are they. So here the functional requirements is we should be able to see live prices of a stock. So that's the first functional requirement that we need to meet when we are trying to design a system of this kind. And second functionality is we should be able to manage orders for stocks. So these are the key functionalities that we should try to support in our system that we are going to design. And others we can even had like trading outside of market hours. So regular, like I think 9 to 4 or something that at which market starts. So besides that, if user tries to execute an order, then we need to have in our own system of scheduling the order the next day when it starts trading, to execute that order on behalf of the user, and all that infra on the system design that we need to, we can also add that point to design. But just I'm trying to keep it as simple as possible, and not just the stocks, we can also elaborate that to support like ETFs, options, crypto and other stuff, and also maybe be able to see complete history of the order book in real time and all those things. But those are like good to have, but I'm just adding that so that we can know that we can extend to those functionality as well. So now coming down to non-functional. So these are very important when we are trying to design here time sensitive platforms like this. So first thing is high consistency for order management. So it's really essential for users to see like up-to-date order information when they are really making trades and all. So that's the first point that we should try to meet, a consistency for order management. And second point is highly scalable for live price updates. So this really should support high traffic, maybe assume like millions of daily active users. It can be 50M or 100 million daily active users, and each user we assume like they might make 5 or 10 trades per day on average, and thousands of symbols like that are being traded on the market and all those things. So those bigger numbers we should keep in mind and design system such that it supports that, and it doesn't
crash during high traffic or so. That's the second point that we need to keep into consideration, and we should meet that. And the third point is very important: low latency for price updates and orders. So it should be in the bound of less than 200 milliseconds. So when we are trying to reflect simple price updates and when placing orders, it should be instantaneous and live feel for the users that they are using that whoever are executing or using our platform. So that's the very important thing that we need to meet. And here the next is minimize connections to external exchange API. I think this one is irrelevant. I'll just edit this. Fine. And the last point is minimizing connections to external exchange API. So here whatever the exchange data feeds or client connections are typically expensive when we are trying to directly connect to those exchange related servers or so we should try to minimize them and see how we can come up with a workaround so that heavy load will be on our system rather than them. And that's the thing how we are going to come up with things. So these are 4 points that we need to come up with and focus on this. So now that our requirements functional and non-functional are clear, so ignore this fourth point, my bad, and clear, so it really helps us to drive the conversation, the flow, the direction in which we need to come up with the evolution of the system that we'll be trying to design. So next is we need to identify the core entities that will be involved while we are trying to design the system, and I think this is going to be pretty simple and straightforward. The core entities is going to be simple, straightforward. So the user of the system, symbol, a stock that is being traded, that's the unique identifier for particular stock, and order for a buy or sell created by user. So these are core entities that we need to at least keep in mind as a foundation. As we go as we dive deeper further, we can think of more specific fields or columns and all those things, but this really helps us to at least have a high level idea or brief view of how it's going to be. So next is public API interface or system interface that we need to come up with. At least the immediate endpoints or something that we can think of is the endpoint to get a symbol which given the name that we give, it should help us give details and price data and all that details. So this is the endpoint that we need to have at least in our system. And the second endpoint is to create an order. So whenever the user tries to execute an order, we should try to take in some a request body might look something like this. Position, is it a buy or sell? Symbol, is it for which stock that they're trying to execute an order? So it can be a unique symbol that they have an identifier. And price in rupees, so it can be whatever the amount that they have and the number of shares and all. And in response we give the order object. So this is the second endpoint that we need to create an order. And the third is just the opposite of it, to cancel an order. So here simple, the endpoint we just receive an order ID and then we delete that order, and the response can be simple, okay, true or false or something like that. And the fourth thing is just to list an orders for a user in their feed or so. We just have get orders endpoint, and we return the list of the orders object, so and paginated responses and all those. So these are immediate endpoints that we can think of, and later these endpoints might change, and if any additional endpoints are needed, we will just discuss there and try to add in then and there. So now that we know at least the API or system interface that we need to come up with, let's take one functional requirement at a time in our high level design and see how we can elaborate more on top of that. So first discussion point is should be able to see live prices of stocks. So this is the first requirement that we need to meet. So users can can see many stocks, live stocks prices at once in their platform, in their feed UI that we provide in our platform. So how are we going to achieve this? So let's think of the multiple approaches. So first approach we can think of is like polling exchange directly. So I think this is the most straightforward approach that we can think of. So what we do is basically we just there will be client and we poll the exchange directly to get a price for per symbol and showcase it to the user. So the client might poll every few seconds per symbol and update the price shown to the user based on the response. But there are critical challenges if we try to go with this solution. One is we unnecessarily make redundant exchange calls. There might not be any price changes, but still we keep making polling request to them and just trying to bombard their exchange server, which is not reliable if more clients are trying to do it concurrently, requesting the exchange API. So that's one point that we cannot go with. And second is, of course, it's not real time, so slow updates and outdated, and we promise that SLA is under 200 milliseconds. So this definitely does not meet this, and this is the solution that we can not really go with the thing. So this polling exchange directly is something that it's not in our favor. So the second approach that we can think of is polling internal cache. So this solution still keeps polling for price information, but now we are trying to poll a symbol service that kind of let's here, which is like internal to us. So basically we are shifting the load from exchange to our internal service. That's one of the point in our requirements as well, right? So now we are polling this symbol service, which really performs key value lookup on an internal cache. So here we might maintain a symbol cache. Something can be Redis or so key will be symbol and value will be all list of values in the form of JSON or so. That is kept up to date by symbol price processor, which really will be maybe getting data from this exchange, and this gets updated, and this will update our cache, and then our client now will just rely on this cache to get the price related info, and then that is what we'll be using to showcase to end users. So this is something additional introduction of the symbol cache into our system, and then help them reduce the connections to our exchange API. But this is an improvement considering the previous approach, but again here we have a polling and still unnecessary, and it really doesn't meet whatever the 200 milliseconds and live or related info that we need to provide. So the final and best approach that we need to stick to is basically SSE price updates, so server sent events price updates. So here we know that SSE is simple persistent connection similar to WebSockets, but it is unidirectional and goes over HTTP instead of like separate protocol. So here we don't want WebSockets because client isn't sending any data. So that's why SSS is superior choice, where we are just trying to get the data from exchange thing. So that is why this approach really helps. So now if you see here, since we are trying to get the data from exchange or so, we need something called an endpoint or so, have like subscribe or get request. So this is something additional endpoint that we can add it to our abode list. So that with query param like containing the symbols we want to subscribe to and all those things. So it's very simple. Our backend now can set up a SSE connection between this client and the symbol service, and send the client the list of the prices that we get from this symbol price processor. So this is how it is going to be and it's going to look like. But the only thing is here we need to be very careful of maintaining connection between client and server. So here we need to have some configuration in the load balancer itself to support like sticky sessions, so that user and server can maintain a connection to promote data transfer and all those stuff. But ultimately this is the approach that we will try to take to meet our first functional requirements, which is to see live prices of stocks. So now let's try to jump onto the second requirement. So you should be able to manage orders for stocks. So here we need to allow users to manage orders, and they should be able to create an orders. It can be limit or market, and cancel outstanding orders, and list user orders, and all those stuff. So let's also here try to break down into multiple approaches that we can think of. So the first thing is sending orders directly to exchange. So here again it involves direct interacting with the exchange to submit orders. So any orders issued by this client are directly submitted to this exchange. So it can be post or delete of creating or canceling an order. But there are like serious challenges that comes up with this approach. So first is like it leads to large number of exchange clients and concurrent requests. So again with direct connection, it's anytime is a bad approach, because we need to minimize the client connections to exchange. And the second point is it makes the client responsible for order management, meaning we don't have anywhere in our system if something goes wrong to come up with the order related info or something. So everything might be stored in their mobile's internal storage and all that stuff. So what if the user deletes an app or changes the device and all those things, and all those info is lost, and now when he tries to use our platform in a new mobile app or so, he sees anything related to order info. So something it's completely delegated to order itself, and it's not in our control. So whenever if it's not in our control, then it's definitely bad system design that we have come up with. So these are like core challenges that it comes up with if we choose this approach. So now the second approach can be sending orders to dispatch service via queue. So this is a better improvement to the previous approach. So this, what it does is, instead of directly sending it to exchange, we introduce an order service, so which is responsible for handling, creating an order and canceling order that that we have. And now what it does, it tries to queue the order. It can be cancel or create one, and that will be picked by order dispatch service. So whatever the queue gets entered, and then we pick one at a time by order dispatch service, and that is responsible to execute order creations or cancels on exchange thing. So this is like the approach that we have introduced, additionally new service, so that we have a track of what are being created or cancelled. But this also has its own caveats. So first is, it really does not meet this 200 milliseconds thing. So like maybe why I'm saying is this, if we consider like high traffic scenarios, like high queue load, like sometimes they get stuck in a queue, and that needs to be picked up by order dispatch service. It doesn't really feel instantaneous, and users have to be waiting on our platform, and they're are not quite sure what's really happening. So again, it's not meeting 200 milliseconds. So that's why this queuing and this getting picked up by order dispatch service and all those things doesn't really add up to our requirements. So the final approach that we can finally stick to is order gateway. So here it's simple as the previous one. It's in here, the only thing is we'll try to send our orders directly to our order dispatch gateway, and there would be no queue or stuff. So here this gateway, what it does is it would really enable the communication with the exchange via this order service. So the gateway, if we think of in terms of AWS, so it can be AWS NAT gateway. The unique functionality of that is it would really allow for our order services, whatever here, to make requests to the exchange but then appear under small number of IPs, like elastic IPs and all those things. So it really makes it look like as if they are originating from small set of IPs. So that really helps as gateways managing outbound requests. So this really makes it as instantaneous, and this service will have its own business logic to manage orders and will scale up and down as necessary given order volume. And this order gateway will make it as instantaneous. So this is the final approach to meet our second functional requirement. So I'm just trying to cover at a high level, and now only the thing is, now order service that we have, it should do more to manage orders, meaning it will be need to handle both for client interaction, and it should also be designed in such a way that it's efficient for exchange interaction, potentially maybe batching orders together and all that stuff. So now that we know that how we will dispatch orders to the exchange, so now we need to really think of how we will be showcase the list of orders to users on our platform and all that stuff. So that is where we need to think of databases for orders and all that stuff. So we need to store orders somewhere on our side for purpose of them showing it to the users and all those stuff. So in order to track orders, we can simply think of here orders DB. It can be simple as any Postgres database, which really any database which supports ACID properties and all that stuff. So this will orders DB might contain info order ID, user ID, external order ID, symbol, shares, price and state. It can be pending, submitted, filed, partially filed, pending, cancelled or failed, and execution data and other metadata, whatever you wanted to store. So this really helps us to showcase the list of the orders for users on our platform, and anything that we wanted to update and all those things. And the other thing is the trade processor. So here we kind of now so this what this trade processor does, it ideally in real systems, it would be a fleet of machines that are connected to this exchange to receive price updates. So it would be basically in the form of a webhooks or so endpoint, which that it is registered with the exchanges, and any exchange would call this our webhook whenever it had any updates and all those things. And then trade processor will update any order related info into our orders DB. So this is kind of black box, and we will try to discuss more on it later as we dive deeper, but ideally now we also have this orders DB and meets showcasing list of orders. So this is how we can meet our the managing orders for stocks thing. So now let's take one point at a time from non-functional requirements and see how can we even try to meet those non-functional requirements. So first thing is the live price updates. So how first how can we scale up so that live price updates correctly and all those things. So the important point that we need to solve here is how do we really route symbol price updates to symbol price service servers connected to users who really care about those prices and all those things. So this is per each symbol we need to get the real price, live price, and also so the to achieve that level of functionality in a scalable way, we can think of is something called Redis pops up. So to publish or subscribe to price updates. So simple. So here users can subscribe to price updates via this symbol service, and the symbol service can ensure it is
subscribe to this symbol price processor, which really gives us the price updates and all that stuff. So it is how it is going to look like. So let's see the rough flow how it's going to look like. So user subscribes to this symbol service, and here we track basically for symbol who are the list of the user IDs that have subscribed to. So it adds an entry for each symbol if the user is subscribed to. Now this symbol service server is managing subscriptions to this Redis pub sub for channels corresponding to each symbol. So this really ensures it has an active subscription for each symbol that user is really concerned about, and if it lacks a subscription, it just adds a new one. So when any symbol symbol changes prices, the price update whatever that we need to make is processed by this symbol price processor. That is what publishes the updates to our Redis PubSub, and this the symbol service is subscribed to. So this consumes whatever the updates this Redis PubSub gets. The symbol service then sends all the updates that we have to those list of the users that we have. So that's how we scale live price updates. And the what if the scenario, if user unsubscribes from symbols or disconnects, so we might detect that via some heartbeat mechanism. The symbol service server whatever we have will go through each symbol they were subscribed to and removes them from this list of set of user IDs. So if the symbol server has no longer any users that has subscribed to, we just remove the subscription to Redis PubSub as well, because we don't need to really monitor that symbol anymore. So that's how we try to manage this live price updates using Redis PubSub and symbol service and symbol price processor. So these are very important components that we added into our system to achieve this non-functional requirements. So let's go on to the second non-functional requirements. Second is low latency for price updates and orders. So here we discussed about price updates above, so let's focus more on this order updates. So here basically here the caveat is, how will we ensure that our orders DB is updated as orders are updated on the exchange? So here in our previous discussion, it's not really clear from our design how the trade processor, that the black box that I mentioned, reflects updates in our orders DB if any trade happens on the exchange. So there's really no way for us to look up a trade via the external order ID to update a row in our actual order table that we have in our system. So now, but one thing we know is the table is partitioned by user ID. So we know that it is partitioned by user ID. It's something now we can try to think of to create a new key value lookup or DB or something like that. So and introduce something called external order metadata DB. It can be something like rocks DB or so. This we try to store in the form of external order ID. So that is the order ID that is executed on the exchange, and that key is mapped to order ID in our database and user ID with which it is associated with. So now this really enables this trade processor to quickly determine whether the trade involved on the exchange is a part of our system or not. And subsequently, once it figures out it is part of our system, it looks up the order go to shard via the user ID and look up the order using this order ID to update any order details that we need to know in our system. So that's how we track order updates and all that stuff. So we introduce additional external order metadata and create a mapping of external order ID to order ID and user ID, and so that now there is a proper linkage of whatever is happening on the exchange and what needs to be known into our system, into our orders table. So there's a
synchronization, that if there is something goes wrong. So this is how the new system might look if we add this, and help us meet this order updates and all that we have. So the final point is consistency for order management. So order consistency is extremely important, and it's the main discussion point that we need to spend some time on, because whatever the orders that are being stored in our system, and orders that are being managed on exchange side should be really synced, and that is something that we cannot compromise on. So here let's see, like, what is the flow, how it's going to look like when order is created, and which and all components it touches. So when an order is created, so here post or delete or get orders. When an order is created, so we send that through our API gateway to our order service, and we store it in our order database with the status as pending or so that we have a record of a client has created an order. So if we don't store this, then client could create an order on the exchange, and that system could fail, and then our system has no way of knowing whether there is an outstanding order or something has failed or not. So now once we have it stored in our orders DB, we submit the order through order dispatch gateway to an exchange, and get back the external order ID. So, and when we get that external order ID, we use that to create a key value entry in our external order metadata DB, and update the order in our order database with this status as like submitted, and also store external order ID as the ID received from the DB. And then once we receive that, we respond to the client that order was successful. So that's how we maintain. So this is like rough flow when user is trying to create an order. So now let's think of all the possible failure scenarios that it might come up with. So I think this should be straightforward. So first thing is ability to failing to store order. So if there is a failure when we are trying to store an order in our system itself, we can straight away respond to the client that it failed and stop the workflow. That's the easiest failure that we can see in the first place. The second is the failure might happen when we are trying to submit a request to our exchange. So if there is a failure while submitting an order to the exchange, we can simply do mark the order in our DB as failed and respond to the client accordingly, it failed. So that is also one scenario that the failure might happen. The other thing is when exchange we send a order, but while receiving external order ID there is a failure. So maybe after exchange submission, so we didn't receive external ID, and then how are we going to handle? So that's when we need to think of how can we clean up a job that deals with such scenarios, like pending orders in our database and those things. So here we need to introduce something called order cleanup job. So this occasionally what it does is basically looks up all the orders in our orders DB with a pending status. And also the most exchange APIs, what they do is they offer APIs with the client order ID metadata when submitting an order. So the cleanup job, what it can do is query the exchange to see if the order went through via the client order ID that exchange API provides, and accordingly it can do one of the two things. So it can record the external order ID if the order went through successfully in our exchange and create a lookup and then update our orders DB accordingly. If not, what this order cleanup job does, it just marks the order as failed in our system and as if the order didn't go through, and let the user know accordingly. So that's how the failures situation that is how we are supposed to handle and will be handling. So that was the flow of creating an order. So let's think of the rough flow of canceling an order. So I think that's going to be simple, straightforward, except the status changes in our orders DB. So whenever user tries to cancel an order, we just update order status to pending cancel. We do this first, and then submit the order cancellation request to this exchange, and again record the order cancellation in our database, and we just respond back to the client saying that cancellation was successful. And here also again we'll see some kind of same situations of failures. So first things, updating status to pending cancel might fail. So then if it failed, we just straight away respond to the client it failed and failure cancelling order. So if there is a failure while cancelling order via the exchange, we can respond with the failure to the client, and then again we rely exclusively on our cleanup job that we have to scan all pending cancel orders and make sure they are done what they are supposed to be done. And final thing is failure storing cancelled status in our DB. So again if that is also the case, we rely again on order cleanup job. So those are like rough failure scenarios that we can really think of in the process of creating an order and the process of cancelling an order. And finally this is how our system would look like of considering all the functional or non-functional requirements and making sure that we meet every point that we discussed and introduced all this additional order cleanup and all those job. So this is how at a high level the overall discussion looks like. I know this is very very high level, but the idea or the intent is also the similar, just to get a rough overview on how to navigate our thought process and think through and so on. So once we know at least the basic flow, how we need to think through, later as we dig into each and every component into deeper, when we are trying to really implement, then that is again more or less a very detailed discussion in each of the component. Hope at least you got the gist of what I was trying to convey, at least the brief overview. Yeah, and let's catch up in the next system discussion. Now let's discuss on Google Docs. So we all know what Google Docs is. It's a simple browser-based collaborative document editor where we can just create rich text documents and collaborate with others in real time. So that's what like basically it does at a high level. So though it has like tons of features, because it has like hundreds, thousands of engineers working on that product at Google. So just like at least at a high level, that's what it does. So now it's clear what it does at a high level. Let's try to break down the requirements into functional, non-functional, and see like what are the things that we need to at least meet when we are trying to design system of this kind. So the first the requirement functional one is basically we should be able to create a new documents. That's like simple and straightforward way creating a new documents. The second requirement is basically should be able to allow multiple users to edit that same document concurrently. So that's the second that we need to meet. And the third is basically whatever the changes each other are making in that specific document, they should be able to see those each other's changes in real time. So that's the third requirement that we are supposed to meet. The fourth one is basically they should see the cursor position and presence of other users in that specific document, so that they don't try to override others user work. So this cursor's position and then presence really helps them to see like where they can concentrate on specific part of the document. So these are like a basic four core requirements, or at least the points that we'll try to discuss. Still we can add like how can we still discuss more on sophisticated document structure instead of like simple text editor. And also we can even add like permissions, collaboration levels, like who has access to which document, and document history and versioning. But again, those are good to have and add-ons, but these are four functional core requirements. I will try to discuss the non-functional things now. So here first thing is basically the documents whatever we users are creating, that's fine. Like if we have eventual consistency, that is like they should see the exact same document state at the end, not like each user is saying different state. And that's something that we need to keep in mind, such that end state of the document is always the same for all the users. And the second non-functional requirement is basically the updates whatever each user is making should reflect in each other's view in less than 100 milliseconds. So that's like latency that we need to guarantee for this updates. The third requirement is basically it should be very highly scalable. So basically it should scale to millions of concurrent users across like assume like Google at a scale, they have billions of customers, so across like billions of documents it should be able to scale. So that's like keeping those numbers is something that we need to try to design a system. And the other constraint is basically no more than 100 concurrent editors per document, because we normally see that only like few people is what will be editing, and most of the other users will be just the viewers. Even in any organization of at any scale, only few people will try to collaborate and then edit that, and others all are going to be just viewers. So I think 100 is itself a very big number. That's fine. So no more than 100 people is something should be editors on that specific document concurrently. And then the last one is basically it should be durable. Basically we should persist whatever the user is trying to make an edit, even if they went offline or so. Later we need to somehow sync the state, and it should even be available even if server crashes or restarts, something like that. So those are like core functional non-functional requirements that we should try to meet, and try to come up with a system and components interaction such that it meets them. Now that we have this functional non-functional requirements clear, let's try to identify the core entities that we'll be trying to deal in this discussion. So jumping onto this core entities, the first thing is basically the editor. So it's basically the person who is updating the document, so user editing the document and all that stuff. So that's one core entity that we can identify. The other is basically the document itself. This is all the collection of the text managed by this editor, the above the user who is updating the document. Then the other entity is edit. It's basically a change that is made to the document by an editor. So every change that is made by an editor is something that we treat as a separate entity, so that we can even reconstruct the final state cleanly. So that's one entity. And the other is basically the cursor, the position of the editor's cursor in the document, and also the presence of that user in that document is something we can track. And that's one entity that we immediately can identify looking at the requirements that we listed above. So now that at least we have these requirements, this might elaborate as we discuss more, but at least this is the base to start with. So fine, the core entities are fine. Now let's jump on to this contracts system interface that we'll have. The first thing is we need an endpoint for an users to create a doc. So that will be simple as a post endpoint / docs, and it might have a body input of title and other metadata, whatever it is, and we just written this doc id. So that's the first endpoint. We'll just try to create a doc, and then this post endpoint, and that's just the way to start editing the document. So that's like creating a doc. The second endpoint is basically updating a doc. So here we know that REST endpoints is needed for just the CRUD ops that I like for creating a doc and all. But here to make an updates to document, we are going to be needing lots of bidirectional communication between each editor and the document. They're collectively editing and all those things. So here we are assuming that we have some WebSocket based approach for this editor experience. So what we do here, we'll try to define few of the messages types or so that we'll be sending over the wire. So it might be as simple something like this. So WebSocket connection, let's say for this doc id. So the type might be like inserting, use like new line or something, inserting, and the other thing is can be updating the cursor of the specific editor, and then the type to delete the specific content in the document, and the type to update, like this. So like this we'll have various types that we'll be trying to send over a WebSocket connection, and as a bidirectional communication between the editor and the document, and across all the editors or the viewers who are viewing the document. So that's something we can think of. More message types, but at least I laid down simple types or operations that we'll be trying to make on the document. All right. So fine. So now at least we have laid down functional requirements, non-functional requirements, entities, and the contract. Let's now take one functional requirement at a time and try to elaborate more on that, just to get the basic system running and the core components tying up and how they interact with each other. And then as we evolve, we'll try to discuss on more deep dives on non-functional requirements. The first point is basically should be able to create new documents. I think this should be simple and straightforward, and I think so I'll just keep it as short as possible here. So the core entities, I think, should be the user, the API gateway, and then this document metadata service that we have, and some document metadata DB. The document entity will have an ID or title. So simple. What we do, we just make a user makes a post API call /docs through API gateway, and this metadata service just creates an entry in this our DB, which document table. So just simple components interactions. So I will not elaborate more on this. I think just to getting the base system, laying the foundation. The second one is basically should be able to allow multiple users to edit same document concurrently. So here we have to deal with first writing to the document itself, which we know that we need to think about consistency and scaling related problems, and that's where like now more discussions point comes. So basically in a collaborative editor, multiple users we know will be making high frequency edits to the same document at the same time, and now that's where like consistency problems and contention and all those things. So let's not worry about the scaling concerns right now or right away. We'll keep it for our deep dives later. And so now let's focus on consistency. So let's try to break down this collaborative edits. So here, because to be clear, achieving consistency in collaborative related environments is not that easy. So let's try to see how we can come up or build up a more correct one. The first one is basically let's see sending snapshots. So let's just assume that pretend on each edit the users send their entire document, like entire document state, over to a document service. So here I assume like I introduce this document service. We'll try to write an entire document. This what it does, document service will store that document in some blob storage, S3 compatible like storage, anything in any cloud. So assume like this is what we send. We assume like this is simple and that should be fine. But this is completely inefficient, because if you take a step back and have a look at this, we are transferring entire document over that wire for every edit. for a fast typer, let's say, is doing 100 words per minute or whatever it is, that could mean like hundreds of kbs of data per keystroke. So that really piles up the size of the document that we are trying to send over a wire. So let's just assume here, okay, so let's say, like, I'll just give a simple example. User A and user B are editing the same document, and then document has something like, hello thing, and user A tries to add hello space world or something like that, and user B tries to delete that hello or some word and things. So now both submit their edits at the same time. Now the actual document that gets stored to our blob storage is, we are completely relying on which request arrives last, right? So if users A's edit arrives last, the document will be like hello world, and if user B's edit arrives last, the document will be something like hell or whatever if he has deleted one word in that word. So that's something now the problem, right? So let's see now, like, second, like sending snapshots or edits, like let's see, we'll try to solve the problems here. Now instead of, we saw the problem, if what happens if we send the whole document over the wire, and what is the thing that I just explained with simple example. So let's assume that we can just transmit the edits themselves, like, let's say, like, hello is the word, okay, user A adds word, I said. So what we do, we have some operation like insert at that cursor position, like let's say 5, I insert word, so this is what it will be. And if user B tries to delete maybe this exclamatory mark at the end, so he just sends the delete position of this is at 6th, so that is 6. So now at least we solved at least one problem, that is like we're no longer transmitting the entire document. Now at least we are trying to send only the edits with exact cursor marks and what operation it is it insert or delete and things. So now we don't have to worry about, like, transferring hundreds of kbs of data on every keystroke now. But we are having more problem here. Let's say user B's deletion assumes that character at position 6 is an exclamation mark, but if users A's edit arrives, that is hello world arrives after users B's deletion, we will end up with hello world. But if user B's edit arrives after users A edit, what do we do now? Instead of deleting exclamatory mark, we would have deleted space. So that's something now we need to think about this. What are the approaches? So, like, collaborative editing approaches. So the critical missing piece is that for us to understand is the edit whatever we are making is contextual. So contextual in the meaning here is the edit should be based on the specific state of the document, whatever it is. So this dealing with this stream of edits concurrently presents this consistency things. So now we need to think of the couple of approaches how we can solve this problem. So the first thing is operational transformation. So that's one approach. So here the approach is basically we'll try to adjust the user's edit based on the edits that came before it. So what we do ideally here in this case is operational transform. I'll just try to take one example and see here. Assume here user B All right. So user B, fine. Yep, fine. So here's the example. So initial text, assume like it's a build exclamatory mark. Okay, and this, the left side is what I'm without operational transformation, and the right side is basically with operational transformation. So here user A, what first operation we is this is the scenario that both users have done the operation at the same time. So user A has done first the inserting the comma ecosystem at this location from cursor 5 onwards, and after this one he has received the user B's operation of deleting the 6. So here how it looks is basically build ecosystem is what first it gets constructed, and then this delete 6. So delete 6 was this comma, so comma gets deleted. So this is how it's going to look like without operational transform. And user B scenario, let's assume first is trying to delete and later is receiving whatever the user A as was trying to do, insert. So here what it looks like, first he deleted 6, which was this exclamatory mark, so it will be build, and later we are inserting comma ecosystem, and it looks like this. So now you see at the end of the document state is completely different in user C screen and users B screen. So this basically definitely is not the way that we wanted it to work. So that is where we need to think of something like central server that knows the exact sequence of the operation that it is receiving, and such that we can make sure that the end state in both of the users interface is ending up same. So that is where now this operational transfer comes in. So let's assume this this operational transform. What do we do here ideally is the idea with operational transform is basically we try to collect all of the edits to the document in a single central server. That is like core of this operational transform. So from there now we can in batches transform each edit, based on the edits that came before it. So this is something at a high level the gist of operational transform is. On a high level it's a topic of its own discussion, but just at least this should give decent intuition. And now here with a user here we insert this ecosystem, and now the transform if we introduce this operational transform, now instead of sending this delete 6, what we do, because we are maintaining single server and there it has like the transformation batch of operation that's happening based on previous edits and all. Now instead of sending the 6th location whatever this user B has ideally typed, but now we are considering the last position. So basically whatever was initial, but after this edit of this, the keeping it as equivalent of what user B was actually trying to do. So this way this transformed operation in single server really helps us to maintain the state in both of the echo state as same. So here it is just the same as this one. I just have not edited that, but this way it makes sure that it deletes this exclamation mark, and we'll end up with the build ecosystem and all that stuff. So I just have not updated here, but that's the intent. So the only challenge is, like I said, it requires a central server. That's the thing, but in a scale this might become bottleneck, but ultimately this is what is being used exclusively by Google Docs or others, and that's the preferred one. But we have other things as well that we can discuss as well here. This conflict free replicated data types and CRDTs. So here this approach is basically we YJS, the open source implementation we have, and that is being exclusively used for collaborative applications like Google Docs, Figma, and all that stuff as an open source alternative. But here again, this idea is the now the idea here is basically the alternative to reinterpreting every edit is to make every edit cumulative or able to be applied in any order. So that is the actual approach that is taken by these CRDTs. So what it really helps us is basically it tries to represent these edits as a set of operations that can be applied in any order and end up producing the same exact output. So let's take an example here. I know this is a pretty complex topic, but just trying to give a simple intuition, but at least we'll have an idea, because this is a very complex topic even to understand in first place. So I have it here on example. It basically idea is whatever the positions it has of each characters, it represents that positions using this unique identifiers that can be like real numbers, very big real numbers with the 4.399 and with lot of precision numbers subdivided like that with variable length numbers that I just mentioned, the precision numbers. So these positions will never change even in light of insertion by other users. So even now, since each position is having unique identifier, whenever multiple users are making edits at the same time, they get unique identifiers like this thing. And once we have this we try to have this merge combined mechanism such that it will always be ordered by the unique identifiers that it has helped us to identify with. So combined, it looks like this, so that the end state in both of the screens is always preserved and taken care. So here even for deleted text, it keeps a tombstone. So basically the text is never actually removed from the document, but we actually remember that it is deleted before displaying that document to the users and all. So that's what we just don't want to jump too deep anything, just want to buy some intuition on how this works. So and this is basically easier to adopt for cases of an online where there's no network adoption or such that. So this really works significantly well in such cases. And like I said, a popular open source implementation is YJS, which is used extensively for lightweight collaborative applications and all those things. So I don't want to talk much about here because this is something very complex topic in itself, but that's how it's going to look like now if we consider those approaches. So we consider now not CRDs but transform ops. So this document service will have this transform ops batching of whatever the edits that we will be trying to get here, just edits, and then maintain this operations in our document operations DB with the timestamp, document ID, and the data that we'll be receiving. So if we consider that point, this is how it's going to look like. WebSocket edits that we'll be having, and we just write edits, and then there'll be transform ops and such that the end state of document in every one screen, and then anybody's edits is not overwritten, and the operations in the sequence are taken care and such that. So that's the second requirement. And now the third requirement is basically we should be able to view each other's changes in real time. So here okay, now that we have the right path figured out, let's talk about now read things. So when a document is just created or hasn't been viewed in a while, we need to be able to first load the document from our database and transfer it to all our connected editors. And next, basically, when another editor makes an edit, we need to get notified so that our document stays up to date. So first scenario, so when the document is loaded, so this is the first scenario. So here what happens is, when user first connects, they need to first get the latest version of the document state. So in this case, when this WebSocket connection is initially established for the document, here what we can do is basically we can push so basically first on initialization, whenever user is trying to load the document, we'll try to read all ops that we have stored in this operations table with that document ID, and that is the initial state that user gets. And once that is established for that user, then we can send push that to the whoever users are connecting to that same server. So this assumes that the all connections are starting from the same place. So like, whatever the applied ops that we have on connect, we try to send to our gateway, and then it will be broadcasted to all the connectors who are connected to that same server. So that's the loading the scenario. Now the when updates happen scenario. So when an edit is made successfully by another collaborator, another user, so now every remaining connected editor needs to receive that updates, right? Since all of our editors are connected to the same server, that should be straightforward. So what we do is basically after we record the operation in our database entry, we can send all the applied ops to sorry, my bad, not this one. So here, so and we just write all the edits back to the user. In this way, other client also receives the same version of whatever has been updated. So I think this is a bit of like hard discussion. We'll have some confusion points, but bear with me. I know I'm not being clear, but that should be fine, and that's how it's going to be. So now yeah, so that's how we try to send. Now on the client, let's say on the client, we also have to perform this operational transformation. Let's talk what this is about. So when a user makes edit to their own document, they expect to see the changes immediately. In some sense, the changes are always applied first to their local document and then shipped off to the server to convey that to same the state to other users who are connected. So but what happens if another user lands an edit on the server after we have applied our local change, but before it can be recorded to server? You get the point, right? So now this operational transform gives us a way of handling out of order edits as well. So if you remember, the OT takes a sequence of edits in an arbitrary order and rewrites them so that they consistently return the same final state of the document. So what we can do the same thing here as well. So here let's say like if user A, I'm just hypothetically giving simple example. So if user A submits like AB to the server, and user B submits like AC to the server, which arrives after AB. So the perceived order of operation from each side. So from server side, I receive AB and AC in the order, and user A will see it as like AB and AC, but user B will see it as like from his site, it will be like AC and comma AB, whatever. So regardless of the ordering, what we can do by applying this OT to the operations, we can guarantee that each user sees the same document. So here the operational transform that I mentioned, so this really helps us to preserve this same state by doing it in a batch, such that at the end eventually the state is going to be same in all of the users screen or sites they will be listening on. I know this is a bit of chaos here and there, but at least the intent is to give you an idea, at least a rough high level tie-ups between components. And the next requirement is basically should be able to see cursor position and presence of other users. So here this why do we need it in the first place is basically, first thing, like I said, it helps to avoid situations where we are trying to simultaneously edit the same position, like same content, and also we don't want really want this to be ephemeral, meaning we only care about where our collaborators cursor is now, not like where it was like an hour ago or so. So basically we're not worried about like storing it in somewhere in which we can persist. So then or anything we don't want in our database or document data itself. So what we can do instead, we can have users report changes their cursor position to document service, where we can store it in our memory and broadcast it to all other users via the same WebSocket connection that we have established. So when a new user connects, the document service can read the properties of other users out of memory and send them to the connecting user. Finally, the document service will help us to keep track of this socket hangups or disconnects and remove those users from the list, sending a broadcast whenever it happens to any remaining users. So with that, like at least we'll have at least decent tie up or like the high level design or systems. Let's now try to jump on to deep dives. The first thing is, how do we scale to millions of WebSocket connections? So millions of concurrent users, billions of documents. So here first thing we assumed was we'll be able to serve everyone from a single document service. That definitely won't scale to millions of concurrent users, and it's introducing single point of failure straight away. And also we need to scale the number of document service servers to concurrent connections, whatever we have. Now the discussion is, let's say whenever I connect to document service, I either need to be co-located with all other users connected to the same document service, or know where all other users are connected. So those are like two questions that we need to think of now. So basically here the solution is, we will try to horizontally scale the document service at this and use a consistent hash ring to distribute these connections across servers. So now that consistent hash ring, maybe we can use something like Zookeeper, which so now since every server in our system joins the hash ring, so that server becomes responsible for all the range of hash values. So this way we will know that which server is responsible for which document, and all connections go there. So this is how, like now if we consider that, we'll introduce a Zookeeper to maintain this hash ring configuration and coordinate between servers. So now the flow is basically, when a client connects to needs to connect, they can initially open this HTTP connection to any of our document servers. mostly via round robin with document ID requested. Then this document service will check the hash ring configuration for that given document ID, and if it's not responsible for that hash range, it will what it does now, it will redirect to the correct server's address. So this way client will eventually connect directly to the right server without an intermediary. And once that correct document service is found, here we are just showcasing it as a one service, but horizontal scale assume like multiple document services we have. So once that correct one is found, then this the whatever the HTTP connection was used to find out that right document service will now be upgraded to WebSocket connection. Now this socket server maintains a map from that document ID to the corresponding WebSocket for use later. So, and then once WebSocket connection is established, and the normal loading all stored ops from our documents operations and are ready to process the operations happens as usual, like we discussed. So since now all users of a document are connecting to the same document service, because they are like distributed in a ring, consistent hashing, so they always hit the same document service, and whenever updates happen we can simply pass them to all connected clients. So that is like actually the beauty of consistent hashing. And even when we add or remove servers, only small portion of connections need to be redistributed. So this basically, the servers, what they do, periodically they check this zookeeper for any ring changes and can initiate connection transfers whenever needed. So this way, by introducing this horizontally scaling and then this consistent hashing, we try to take care of this scaling and concurrent users at that number. And now the second requirement is basically trying to keep storage under control. So now we know that we have billions of documents, and we need to be very, very careful how we manage that storage. So by choosing OT or CRDTs, we can already reduce the amount of storage we need by factor. So assume if each document is 50 KB, so we are looking at a rough ballpark number of around 50 terabytes of storage. So that is, again, it's going to be worse if each document has millions of operations. Each of those operations will need to be transformed and applied to each client that joins a document. So this all active documents need to be held in memory in our document service and all those things. So now these are all the things that we need to see how we can optimize the way we store. So first thing is basically, first approach is offline snapshot or compacting. So here the idea is basically we try to introduce a new service here. So here this compaction service, what this service responsibility is basically, it periodically reads operations out of this document operations DB, and it writes a snapshot back to the DB, basically back to the DB, trying to merge those operations into one single operation. So and this way we might make look large documents as smaller and compact them. And this also doesn't really change the operations and any document state, and we need to we just need to make sure that we are not impacting the live document where users are making, where still operations are coming in. So this is something that's where we need to think a bit, like how do we handle that transaction, and also for document operations DB, we might think of using Cassandra for since we now have only row level transactions to work with. So to ensure even document level atomicity, we can introduce this new attribute called document version ID. So to this document metadata DB and this document operations DB. So the idea here is basically whenever we wanted to change these operations and merge that, we can write new operations and store it with the new document version id. And whenever a live document is no longer being edited by the users, we can flip that document id version id with the latest the one that we normally used to compact and all such that. So even when we are trying to load the ops that we need to load and all, it will be lesser, and it will something that the storage also is something that we are trying to save. So that way this compact service can now really helps us flip this document version, compact, and help us in the document storage overall. So this basically it reads the document operations for a given document this out of this operations db, compacts those into few operations as we can, probably mostly single insert operation, and then it writes that resulting operations to this new document version id. And then the later whenever that specific document is idle, it tells the document service to flip that document version id from an old version to the new version, and then that updates our document metadata db. So that's how at least this really helps us to take care of the storage. And this is one approach. And the other approach is basically online snapshot or compact operations. So it's what we do here is will not have separate compaction service. The idea is basically this document service itself, we can make it periodically snapshot or compact operations instead of having a separate compaction service. Since this document service has exclusive ownership of that specific document, whatever when we are not scaling up that cluster, we can safely compact that operations without even worrying about coordinating or consistency. So it's basically again simple, not having separate compaction service, and whenever document is idle and no connections, that is something document service will know. And we also know all of the existing document operations, and also we have it in memory at that time, and we don't have to even do db calls. So again, which really makes our job easier. So that's how we delegated to document service itself to take care of that compaction whenever the idle, and still the ops will be in memory, and then we can use it. The query turnaround time to db is also ignored. So whenever now the last client disconnects, what we can do now is basically all the existing operations we will take them and offload to separate maybe process for compaction, and then we write that all resulting operations to db under a new document version id. And then we try to flip this document version id in our document metadata db. So that's how it's going to be. And I know there is a slight not proper update, but this is the reference. So assume like this is the thing, but just remove this compaction service, and the rest will be taken care by this document service itself. So that's one way of dealing with the storage, and how we try to normally compact the series of operations into single insert operation and reduce drastically the operations that has been done by multiple users on a single document. So yeah, I know this is not at all a great discussion, but at least hope it might have given you a decent intuition or rough flow of, or at least the approaches that we can think of, and then you can do offline elaboration on the specific approaches that I just mentioned.
Now let's discuss about Instagram. So we all know what Instagram is. It's a just social media platform primarily focused on allowing users to share photos, videos. Along with that, it has bunch of other features like live streaming, stories, status, and all that stuff. But primarily it's just the photo sharing and video sharing with the followers. That's what the core functionality of Instagram is. So now it's clear what it does. Let's try to break down its requirements into functional and non-functional as usual. So when it comes to functional requirements, the first requirement is basically users should be able to create a post with a media and add any caption to that post. So media can be here photos or videos, so anything. So for that is the first functionality that we should try to support when we are trying to design a system here. And the second functionality is basically they should be able to follow other users so that they can see whatever the other users post on this platform. So that is the second requirement. And third is the one which I just elaborated, is basically now the feed, whatever the users see whenever they open our platform, they should see feed from the users that they are following. So that's the third requirement. So simple and straightforward. So able to create a post with media and add a caption. The second is to follow other users, and third is to see the feed from the users that they follow. So those are core functional requirements that we should try to meet. So we can still add more and more, they should be able to like, comment and post and search for users, hashtags or locations, or again create and view stories, which is like ephemeral, just stays like for 24 hours or so, and then go live like video streaming and all those things. But they're all good to have, and it's like we can add if we have a time to discuss more of such requirements. Right. So now let's go to non-functional requirements. So here the non-functional is, the first is basically we should give high priority to our availability, meaning whatever the photos or videos that they upload, make sure that we don't get it lost somewhere in the process. And so that is something that it's not compromisable to the users. Over consistency, basically it's okay even if we take some time, maybe a couple minutes more, to showcase whatever the media or photo in their feed or so, whatever, that's fine. But we should not lose that whatever the media that they are uploading. So that's the first point. So basically giving preference for high availability. And now the second is basically latency. So when it comes to users tries to see the feed content, whatever the media or photos that we are trying to showcase should be very fast, just in the bounds of milliseconds, so less than 500 milliseconds. So that should be for feed loading. The other so feed can it loads like metadata, content, caption, other stuff like photo or whatever it might be. But the again the media rendering is something again different. So when they open also particular post or video or whatever the stuff, that latency also should be very super duper fast, so that they get the best experience on our platform. So ideally it should be less than 200 milliseconds, so giving instant result for them and the feel, so that they stay on our platform. So that's the third requirement. The fourth is basically they should be able to scale to support high number of daily active users. So I have just added here ballpark number is 500 million daily active users, so it can go up to billions of users and also. So that's important to keep in mind whenever we are trying to design system of this scale. So these are very important that we need to meet, especially non-functional requirements. So now that our requirements functional and non-functional are clear, let's try to identify core entities that we need to deal with, and then elaborate from there to system contracts and all that stuff. So here the core entities is going to be simple and straightforward. First is basically the user. This basically that's where we stored information like username, profile details, and other details, metadata, whatever we wanted to know about that specific user. The second entity is basically the post. So this basically will have a reference, maybe in this case can be S3 link to our photo or video, and a caption and user who created it, and all those things will be handled by this entity. So I'm for time being I'll consider that this is going to handle both photos and videos. So that's how it, and media here basically represents like actual bytes of media file, like like S3 and all that, any metadata that we wanted to keep. So this is going to deal with those stuff. And the follow is again just the mapping, who is following, basically mapping between follower id and follow id, so the relationship between two users, and that is this entity's responsibility. So these are the four core entities that we'll be dealing with whenever we are discussing this system that we are trying to elaborate on. So now that entities are clear and simple and straightforward, let's jump onto our system interface, the contracts that we'll be exposing to the public. So first, we need an endpoint for users to create a post, so that will be simple post endpoint. So here it is. So assuming, so it's going to be simple body type is going to be something like media, so it can be a photo or video and a caption. So here basically it will be ideally S3 link or so. We'll talk about how we are going to handle that uploading of a media into our servers and all that stuff, and then the caption, and then this is the body that is going to be along with their cookies and authentication details in JWT or that stuff, and then we return the post ID. So that's the first endpoint. So just to create a post, and we'll try to handle of creating a content into our platform. So now the second endpoint is basically they need to follow other users. So basically we need a endpoint where we can create a relationship between a users. So this is a endpoint. So I'm just trying to be as simple as possible. So post endpoint / follows, and the body is going to be the follow the ID, so whom he wants to follow, that's the ID that we get. And here my bad. So basically there'll be nothing written type, so I just haven't not updated, so that's fine. So yeah, this is going to be simple follow endpoint. So the follows ID, whoever it is, it will be extracted, like I said, from authentication token. So that is the session or JWT. So we don't need to specify exclusively in body or so that will be there for us. Then the final endpoint is the feed. So this is the endpoint. So basically that it will be used to see that respective user's feed whenever they open our platform. So here we'll try to use an cursor for pagination, and the limit to control the page size that we'll try to showcase through one request and all. So here I'm just trying to be vague and such, so we are not listing down exact fields and attributes that is going to be part of a particular entity, but just to give us the high level flow, the rough contract that we'll be having or dealing with. So these are the core endpoints that we need, at least for this system, to meet the requirements that we have at least laid down above. All right, so now the contract is also well established. So let's now take one functional requirement at a time from our list that I drafted above, and discuss the overall flow and high level design, how it's going to be. So that's the normal discussion that it's going to be usually. So now first thing is should be able to create post. So that's the first point. So with the media and the caption. So here whenever user is active on our platform or so, they should see somewhere an option like either button or something like that to create a post. So basically trying to click on that opens either a new page or a model, so where they can upload a drag and drop media and add a caption which triggers our endpoints. So that's the a rough the high level picture that I can see for myself. So this is how it's going to look like basically. So here this client, so the components here I'll just try to, so this will be basically the users either on their Android or iOS, so tries to interact with our system through API gateway. So this is a standard way of handling all of our authentication, routing, rate limiting, other stuff, whatever the middleware thing that we wanted to handle. This API gateway will take care of that. And here now we have a post service. So here this is assuming this is going to be our first microservice, which is responsible for handling post creation request. So basically what it does is it just receives the media and the caption, and we try to store that post metadata in the database. So it can be DynamoDB or Postgres or whatever we are comfortable with, and and then we return a post ID to the client. So here the post entity that we discussed above, so it can have attributes like an ID, user ID, media S3 link, caption, created at, and other details like updated at and vagera stuff, whatever that we need. So I'm just listing down the core attributes, main attributes that we need. So here so the blob S3 storage, so that's where like we try to store actual bytes of the media, so like store photos and videos. So the flow is simple. The client makes a post request to the API gateway with the media and the caption. The API gateway, whatever it is, it tries to route to the right service. In this case it is a post service. So now the post service receives the media and the caption, and we try to store metadata in our post table in our database, and the actual bytes in our the blob store, and then this post service returns a post ID to the client. So that's the easiest flow. So just trying to establish the components and the interaction between them, and then we'll see how can we elaborate further as we navigate through more discussion points. So jumping on to the second point, so here we should be able to follow other users. So we know it's a social interaction platform. So here this is a unidirectional relationship. So basically let's say I follow X, and but he doesn't follow me back, then I'll see his post in my feed, but he won't see mine. So that's we should make sure that the feed who is following, who is not, and all is taken care. So now let's see how we can model this relationship. So like I said, we'll try to have a junction table kind of thing, like follow or stable, so which will have follower ID and follower ID. So and then every time we receive a new post request, that is like not post request or /follows endpoint, we'll insert a new row into that follows table. So let's what do I mean here is basically here introducing a new follower service. So users send a post request with the ID that they want to follow, and then we try to update our DB with a new row in this followers table. So just linking the follower ID and follower ID so that we know who is following who. So that's the simpler way to introduce new additional service and the responsibilities, and that's how we delegate this thing. Fine. So that's the second point, how we meet them. So now let's go to the third point. So basically third point is now they created a post, they followed users, and now they need to see the post of those users in their feed. So this is sequential the pattern that we're trying to observe here. So now here we have let's try to start with simplest approach, then we'll see what are the problems and all that stuff. So what do we ideally do? So we try to first get the followers. So what we do, so we try to query this followers table to get all of the user IDs that the current user follows, and once we grab the user ID, we try to get the posts of all that users. So here we get the post here, so and all the post IDs and the post that we get. So once we get all of that, we try to merge and sort them, and then once we sort by created at and all whatever the sequence that we wanted to show to the user, once we get that, and we try to return to this end user. So that's the that ideal flow, at least that we think of naturally whenever we want to do achieve that functionality. So assuming now I'm just assuming this post service is going to handle all of that stuff, but like we see straight away all the problems that we have just tried to describe. So we know that we are first trying to identify the user IDs and then get the posts of all that user IDs and all. We know that these queries would be incredibly slow, because every followers row for every user, then search through every post to row and all that. Basically lot of table scans and all. I know we can avoid full table scans if we had a few indexes to our database and all that stuff. So but still that doesn't really optimize for the scale that we are trying to discuss here. So here, assuming that I choose DynamoDB or PostgreSQL, so let's say that we go with the DynamoDB. So if we choose the DynamoDB, we'll need to add first, like, let's focus on what and all the fields that we can add indexes to avoid like full table scans. So for the followers table, you see here follower ID is a primary key, will partition key, and then this follow ID is the sort key. So this basically what it does, it allows us to efficiently query for all users that a given user follows. And now when it comes to the post table, we'll make a partition key the user ID, and also since most of our queries will be to get the post for a given user, we can make ID or created at as the sort key. So this is how at least we think of first trying to make the queries optimized by indexing, and then we need to think of other way to optimize it. So this simple flow again, basically we make a GET request to this API gateway with the cursor and limit whatever the endpoint that we described above, and this API gateway routes to our post service. We are assuming right now this is the service that will be handling even the field request. So this post service, what it does, it queries this follows table to get the followed users of current user using the index that we just added, and it will be a little bit faster. And once it gets that, so it queries again the post table for each followed user to get their recent post, and then it combines and then sorts the post and returns to the client based on the cursor and the limit that we have passed in our request. So that's how at least basic functionality and the flow that we are listed down in functional requirements, we are going to meet in that way. So now that at least we have rough flow picture in our view how it's going to look like, now let's focus on deep dives of the core non-functional requirements. How are we going to meet the load latency issues, and also the scalability of for that many users and all, making sure highly available and all that stuff. So deep dive thing. So first point, let's focus on how can we deliver the feed or whatever the content that the users need to see in their thing of all the users that they follow. Feed generation. So basically what are we doing currently is basically a fan out on read approach, but that's not going to scale to the daily active users that we are listed out. It's 500 million or 1 billion, whatever it is. So let's understand why this doesn't really work. So let's see, for assume a user following he's following 10,000 plus accounts or users. So we need to make that 10,000 plus queries to post table to get the posts from each of their followed accounts. So this we clearly see the problems like read amplification. Every time user refreshes the feed, we need to make that many number of queries, and also repeated work. So if the two users follow the same accounts, we are doing again separately for each user's feed. And also it's unpredictable performance, meaning it really varies depending upon the number of the accounts that I follow. If the user with more followers, of course, is going to experience very bad experience on a platform. So it's not consistent. So we are amplifying it and repeated work and all that thing. So that is why this is something, whatever the current approach that we have listed down above, it is not going to work at all, especially during peak usage, like post work, after work, evening hours, like whoever, it can be anyone. So daily day-to-day job, whoever is working, when they get back to home, they try to relax and try to use it, or so whatever. So peak usage, evenings, major events and all, like given the amount of the refresh and the active users that they will be trying to hit peak traffic, this is definitely not going to work. And with the given numbers that I just gave an example for 10,000 posts, it's something that we need to rethink what are the approaches that we can rely on. So let's see how we can improve on first approach. Let's see, like here, simple caching. So basically what is we are trying to do is, so whenever we want to do again improve latencies, we always think of like caching, so that whatever has been accessed before, we try to get it from the cache and then make it look like it's faster than whatever it was for the first time they tried to ask. So here what do I do is, basically I try to add the cache layer in front of whatever the post table that we have, so the database, that thing. So here it is simple, like I said, before querying this database of users followed users post, we check this cache and we try to maintain here mapping from user ID to post. So it can be something like key can be feed, user ID and the cursor, and the list of all the post IDs that we have. And if there is a hit, we try to return from this cache instead of going through database. So that's how, like we try to make it look a little bit faster, and like trying to improve latency. But this doesn't really fundamentally solve our scalability challenges. To handle the amount of the scale that we have, this needs to be massive to achieve like even at least meaningful iterate for whatever the user is asking for. And we still perform like expensive fan outs for the first time or so whenever there is a miss. So this is something again throws back to the same bucket of the problems that we had before. So this is something that we cannot rely on. So let's see what is the other approach that we can. So again, whenever it's all about improvements, we always see if we can pre-compute some feeds, like it's basically opposite of fan out on read, it's a fan out on write. So here is basically what is the idea is when instead of generating the feed whenever the user requests, we will generate it whenever user posts. That is like we try to fan out on write. So here's how it works. So what do I do ideally is, when a user tries to create a new a post through our post service, we try to query this follows table to get all the users who follow the posting user, and we get all the IDs that we have, and then once we get that, we for each follower that we have, we try to prepend the new post ID, basically whatever the user is trying to post, to their pre-computed feed. So this something can be stored in our Redis, like it can be like a dedicated feeds table or so whatever it is. So basically here what we do, we try to store each user's feed as like sorted set, like Z set that we have in Redis. So here the members are basically the post IDs, and the scores here are timestamps, like our post IDs, if they are like sortable. So it can be simple as something like this. So the model that I was talking about for pre-computed feed, so key can be like feed user ID, and the type is going to be sorted set, and members it's going to be all the list of the post IDs, and scores timestamp or post ID. So that's how like we try to switch from fan out on read to fan out on write. But now here the problem, so let's see, like whenever try to request the feed now, we try to read top and post from this the feed or whatever we have set in our Redis, which is like single and fast operation. But still we need to iterate the post based on this post IDs that we have stored in our the Redis. So to do that, how are we going to get the actual content of the posts, because we just stored ID. So now for each post ID that we have in our cache, we fetch the metadata from this posts table, and then query that additional, basically even though we are hitting cache, we need to make additional query to database, and then showcase that feed to the user. So that's one way. Or else, rather than caching the post ID, we could cache the entire post metadata in Redis, and this way the additional query that we were trying to make to the database, we'll try to avoid it now, and this is much faster. But again, the trade-off here is we need more storage in our Redis, which is quite expensive, and also like there will definitely be data consistency challenges. Now the third approach is basically going with the hybrid, like combination of 1 and 2. So here what do I do is basically I'll try to focus on instead of one Redis data structure, we'll try to maintain two. One for feeds post IDs jet set, another for like short-lived post metadata, like caching the hash of the whole post metadata that we have. So now when we need to iterate a post, we'll try to first get all the post metadata from this Redis post cache that we have, and for any cache misses, we batch fetch from this DB using batch get item or whatever, if it's a DynamoDB, and other ways if we do it through Postgres. Then once we get that, we try to update our post cache that I was like mentioning of hashing the whole post metadata with the whatever we fetch from DB, and then we try to return that combined results to our client. So that's like hybrid approach. Basically what we do gives us a balance of like performance as well as the resource usage of memory, as well as the query turnarounds that we have. And here again for post cache, we can try to tune the time to leave and all that whatever we have. But the yeah, I think now at least you got the gist of whatever I was trying to at least give you a high level idea. But now here even the challenge is here, this fan out on write whatever we're trying to discuss, it definitely improves the read performance, making like field retrieval fast, single Redis query plus metadata lookup sometimes, and all. But if you see, we have traded here read time complexity for write time complexity, and significantly increased storage. So here now there was a read application before, now we have made that as write application. So that's basically what if users, basically the users who has significant amount of followers, it's going to be very very big problem, kind of like what we see popular celebrities or the well-known personalities and influencers, whatever it is, it's going to be bottleneck for them. So how are we going to handle for those things? So straightforward. So that's a simple that we can anyhow think is hybrid approach. So trying to stick to fan out on read for popular fellows, and for normal accounts like let's say like less than 10,000, so that's the third approach. So let's try to discuss that. So here these pre-compute plus real time, so it's simple and straightforward. So let's say like we try to define some particular threshold. Let's say like for 100k or 200k followers, for users with less than that threshold number, we pre-compute their followers feed, just like fan out on write whatever that we just discussed, like but for the users more than that threshold, like 200k or whatever, again here again we need to crack our heads, like how are we going to decide that threshold number and all that stuff. But that's again a different problem to worry about. So so if for the users greater than that threshold, we don't necessarily pre-compute that post into follower feeds. So instead what we do, whenever that user post, we add that post to our post table as usual, and do not trigger any asynchronous feed update to their followers and all. So whenever user requests their feed, we fetch the pre-computed portion of their feed, whatever we have from Redis, like post from users who are their following is having less than that threshold. So we get it from the pre-compute feed, whatever we have. Additionally, we also query the post table for recent posts from the accounts above that threshold that they follow. Then we merge the pre-computed feed with the recent post that we got from post table, and chronologically try to return the merged feed into their UI or whatever it is. So that's what, like, mix of like fan out on read and fan out on write. So that's how, like, we try to balance of such scenarios. And here normally for users with less than that threshold, we try to queue them, and this takes care of, like, fan out to all users whatever that we need to update the feed and all those things because we need to update the post table and all that stuff. I think you got the gist of the first point, whatever, like how we make sure that the latency is taken care and it's in the bounds of like few hundreds of milliseconds, and it's what it is. So fine. Now let's discuss on the second point. The second point here is basically low latency of less than 200 milliseconds for media rendering. So we know that whenever we show feed, it can be photo, media, or video, whatever it is. So the rendering of that photo or video should be very instantaneous. Supporting photos can be of up to like few hundreds of megabytes, or videos up to few hundreds of gigabytes. So there are two key challenges that we need to really deal with here. So first is basically upload efficiency. How can we make sure that the intake is also instantaneous, and the other point is vice versa, so downloading or viewing latency. So these are like, we should try to deal with whenever we try to see large media files and all. So let's see, like, one at a time. And for uploading, what do we do? Ideally, basically, whenever we see large files uploading, we think of like chunking. So this is basically, we know that in at least the hard payload size constraint that we have for single HTTP request is less than like, or 2 GB or so. Thus, in order to support like few hundreds or few GBs of video, we would need to send at least like 2 or more requests to complete that single thing. So here what we do, a common standard that we do is basically we try to use AWS S3's multi-part upload API ideally. So how does that work is, first we try to call this post whatever the endpoint to create a post metadata and get a post ID as before. But now it will also what it does, return a pre-signed URL, so that that can be used by the client or the user to upload the media. So this basically, that pre-signed URL will be valid for like limited time, maybe an hour or so, and allows the user to upload that file directly to this to the S3, so without having to go through our servers and all. So I'll just show that piece. And now the client side will use that multi-part upload API to upload the file in chunks and all that stuff to whatever the pre-signed URL that we have. And this S3 or whatever similar like in Azure or GCP will handle that reassembling the chunks and store the final file in S3. So that's how, like, we try to handle at least the uploading part when it comes to handling the large media files and all. Fine. So So that's how, like, we make sure that it gets uploaded and all, and maintain the metadata in our post table, and then change the status to pending to completed and all those things. So but here, once the how do we let the our post metadata table to know that whether the upload is completed, and how do we change the pending to completed and maintain S3 link in our post metadata. So there are two main ways to handle that update in our thing in after completion. So first is the client driven approach itself. So here what we do, we rely on it to send a patch request to update the post metadata with the actual S3 object key or S3 link, whatever we need to construct this media URL, so that we can use that to render or wherever we wanted to use, and then set the media upload status to complete, and that's how, like, first approach, like client driven approach. The second approach is basically server driven approach. So what we do here, whatever the S3 compatible storage that we are using, we configure the event notifications to trigger something like Lambda function or background job when the multi-part upload completes. So this, what it does, it tries to send a notification through that Lambda job or function, whatever I was just mentioning, and updates the post metadata automatically. So basically here, this second approach is server driven approach, is more reliable for us, and because we really can't trust clients to properly report upload completion and all that stuff. So that's why, though it's a bit complex to configure this S3 notification and all that stuff, but it's more reliable, and that's what really makes us to deliver quality media or experience to the users, and we stick to the second approach. So that's how, like, at least we take care of uploading part, the first problem that we just discussed thing. So here we directly through client upload via pre-signed URL what we have, and to S3, and then the metadata updates through S3 notification and all. So that's the first problem. So uploading is something, it's handled through this client side uploading through with the file multi-part upload API, and then metadata update through S3 notifications and all chunking and all that stuff we discussed. Now let's go to our the other problem, which is the rendering part. So let's see, like, now let's see how we can think of and what are the approaches that we normally have to solve these problems. The first approach is basically, let's straightforward, so directly S3 serving. So here what I do is basically, whatever the media that we have in our that S3, I try to download that through our S3 link, that whatever we have for the media file, and then whatever the client it is, it downloads it from the S3, and they can see the media or video, whatever it is, but it really doesn't scale for the amount of the traffic, the users that will be active on our platform. So because whoever are users far from the actual region of that S3 buckets region that we have, of course they are going to see a lot of latency, and it's not meeting our less than 500 or 200 milliseconds that we have set. So since it's like globally distributed application, though, so this is something if people from different regions, like especially if it's hosted somewhere in US, people from Asia or other regions, Europe or so, will see more latency experience than the people who are in that specific region. So that's why this first approach, whatever we have, it's something that we cannot choose to go ahead with. The second is basically we'll try to introduce a global CDN distribution. So here the idea is basically just to put a CDN in front of our S3 bucket, whatever we have. So here we try to put this CDN. So this CDN, what it does, we know that at least it maintains a global network of edge locations that can help us to cache our media files closer to users. So whenever user requests a media, they're automatically, what we do, they're routed to nearest edge location. If the media isn't cached there, it tries to fetch it from the S3 whatever we have are using, and then it caches in at edge locations for future requests and all. So this way now the people from other regions who are waiting for a longer time to load an image, now they can load it from a server which like in a region closest to them, and it is going to be very faster than what is to be from the direct S3 link download and all. So yeah, and how do we configure the CDN to cache files and all? It can be based on the type and the popularity. For example, what we might do, we might cache images for 24 hours at edge locations that we have, since they rarely change when once uploaded. But same way like that, we can understand the pattern for videos and all that stuff. So this reduces latency and the load on our actual S3 bucket and all that stuff. So this is the thing, but still the challenge here is we serve the same files to all users. What do I mean here is basically, irrespective of the resolution screens that they're viewing, whether it is a mobile, iPad, tablet, or like laptop, or desktop or monitor, whatever it is, we're still giving them the same image irrespective of that. So again, that is something it's where we can really still work on and try to improve on. So that's the like final ultimate approach that we'll try to stick with. So here we try to have this CDN with a dynamic media optimization. So here the idea is simple. Whenever the media is uploaded, we try to use a media processing service. So assuming so it's we have in here this media processing service. So additionally, it can be our own internal one, or or we can leverage the existing popular ones like Cloudinary or other things, whoever are well known in this field, to to generate multiple variants optimized for different devices and network conditions. For images, it can be like various resolutions and formats like WebP for supported browsers, and for videos we can create multiple quality levels and use adaptive streaming. We'll talk about what is adaptive streaming and all in the you can see in the YouTube discussion point that I have listed down in this video. And so now this CDN, whatever we have now, it tries to serve this optimized variants based on the requesting device that is hitting our servers and network conditions. So now mobile users will automatically receive appropriately sized images, while desktop users will definitely get high resolution versions, and the client itself will send us what is the device information, network conditions in our request, so that we know which the media or which appropriately sized image that we need to serve to the users. So that's how we take care and rendering of various optimized resolution versions, and also we can be very aggressive with the caching strategies and all. Basically, popular media is cached more aggressively, so that the load on our actual servers is quite balanced, and also less accessed ones we can just avoid caching it more and more. So that's how we try handling this rendering part and try to meet the latency requirements that we have listed down. So now let's jump on to our last non-functional requirements that we have listed down. So yeah, the third is basically how do we scale to our 500 million daily active users. So we know that the system that we're designing is for massive global appealed application. So I think we almost already there covered everything bits and pieces, but let's try to see what do I mean. So to maintain performance and reliability and to scale, we have discussed about pre-computed feeds, like hybrid approach that we have discussed, like fan out on read and fan out on write. And for latency, we introduced CDNs along with that optimized resolutions depending upon devices and network bandwidth and all that stuff. And for media upload, chunked uploads for client itself is handling, and the database choice and indexing offer faster queries and all that stuff. So now let's do some math to determine whether our existing strategies are even sufficient or not. So let's say, like average media size is around like 2 MB, or just average, I'm just estimating. So let's say that 10% of the maybe 20% of the users are uploading, so 100 millions multiplied by 2 MB, so it's roughly around 200 TB of binary data each day that we need to have a capacity to store. So starting with the media, this is about something like let's say like for 10 years we need to support at least that thing. So it is going to be 750 petabytes of data for 10 years. So now how do we optimize the storage and all requirements? So it's simple that we know, like S3 or simple storage service or other compatible ones can handle this, but it's not cheap. So so we know that it's not cheap. So what we can do, we always try to move the media that has not been accessed in a long time to cheaper storage, like glaciers and all that thing. And that's when it comes to like actual media byte storage. For the metadata in our actual DB, and let's say like it's 1 KB of each, so 100 million users multiplied by 1 KB is 100 GB of new non-binary data created each day. So and that's how we need to support. So here always the common pattern to always try to reduce the cost for the storage that is going to incur for over a period of a time given the scale that we have. We always try to think from this, like super fast, it's CDN, and then below that it is caching or memory, and after that it's SSDs, and then HDDs and tapes. So this is the based on the frequency ordered from the highest frequent access to least frequent access storage that we normally look for. So yeah, and to basically take care of throughput, we have separate services for post handling, follower as handling, media processing handling. So we can dynamically scale horizontally our microservices to handle the load, which basically in major cloud providers they automatically take care based on the CPU threshold or memory threshold. So that's how we think of the handling scalability for users of that size. So this is how it's going to look like after all the discussions that we have to meet all the points, at least the minimal points that we have laid down in our discussion, and deal whenever we are trying to design systems of this kind. Hope you got at least some things, some points, though I know it's very minimal points that we discussed, but that's how it's going to be. Always trade-offs, what we wanted to focus on, what's our priority, and all that thing. So let's catch up in the next one. Now let's discuss about YouTube. We all know what YouTube is. That's the most used website in the world. So it's a video sharing platform that really allows users to upload, view, and interact with the video content. So that's like high level, at least the basic functionality, the core functionality of what YouTube does. So now that it's clear what it does, let's try to break down our requirements into functional and non-functional. So functional, so the first thing, they should be able to upload videos. So that's the basic functionality from the creator standpoint, so that
only when videos can be populated into the platform, those can be viewed, right? So the first preference is for creators, they should be able to upload videos, and the second requirement is basically should be able to watch stream those videos whatever has been uploaded. So those are like core functionalities that we'll try to focus on. So we can add other functionality as well, like you're able to view information about videos such as like view counts and other statistics. They can search for videos, comment on videos, can see recommended videos, can make a channel and manage the channel, can subscribe to channels, and all those functionalities, like huge amount of feature list that we normally see in YouTube today. But that's like that's not main discussion point for this system that we'll be discussing. That's why those are sidelined for time being. Alright, so core functionalities are listed down, and now let's try to see the non-functional requirements. So first thing is basically we should give high preference for our high availability, and eventual consistency is fine. That's the first non-functional requirement. And the second one is basically we should be able to support large videos of uploading and streaming. So as of now, YouTube restricts 256 GB as the max limit, or 12 hours limit of the video. So it's like that we should have some upper bounds constraint, and then able to support the large files of like tens of GBs of such things. So that's the second requirement that we need to meet. And how are we going to handle such large files uploading and streaming of them is something that we need to keep into consideration. And the third is basically we should really render the videos very fastly whenever user is trying to view it. Basically low latency streaming even in the lowest network environments, like where there is no bandwidth or so. But still even in that situations we should try to render the video adapting to that resolution and bandwidth, and so that's the third requirement. So low latency streaming. And the fourth one is basically the system should scale to high number of videos that will be uploading to our platform. So assuming, let's say just a ballpark number, we have 1 million videos uploaded per day, and the other side we have like 100 millions of views, videos watched per day, something like that. So keeping in those high ballpark numbers that we have, we should try to design system such that it can handle traffic of that scale. So and then the last non-functional requirement is basically we should support resumable uploads, meaning if some because of the power cut or so, the Wi-Fi disconnections, if video is in mid of uploading process, and so we should try to support the resumable from the chunks that have been missed because of the network issues or so. So that's the the last non-functional requirement that we should try to meet when we are designing the system now. And again the other things we can also keep, like how do we protect against bad content in videos or fake accounts or bots, and then we should have a proper monitoring or alerting system and all those things, good to have. But these are the core non-functional requirements. In functional requirements that we'll try to focus on, and let's try to navigate from here and how we can evolve in this discussion. So now that it is clear the functional non-functional, let's try to first mainly identify our core entities that we'll be trying to deal with. I think this will be straightforward and simple because we know what are the core entities straight away after reading the requirements that we have listed down. So the core requirements is basically first one, we can as usual identify it as a user. So either it's an uploader or a viewer. So from those two lens perspective, those are the user entity that we can identify. And the second one is basically the video, the actual the media or the video that's uploaded or watched, and that's the second entity. And then the third one is basically video metadata. So that's like all the metadata that will be associated with that video. So the uploading user, URL reference to that media or transcript or other chunks whatever we have. And we'll go into more specifics of attributes into detail once we go into high level discussion and all endpoints, but these are like, you know, core entities that at least, you know, we need to even to begin with. So yep. So now the core entities are fine. So let's now check on the API contract that we will be trying to expose, so that can be consumed by our clients also. So first one is basically the endpoint to upload a video. So we might have a endpoint like, you know, post upload, where we might take in a video object and video metadata to, you know, create an entry into our system. So this might change, but this is a rough thing, because later we might just, you know, prefer taking just metadata, and video upload will completely delegate it to client responsibility with pre-signed URL and all that stuff. We'll discuss that. But just this uploading video, so one endpoint that we need to have at least for a client to upload whatever they want into our system. The second one is basically streaming video. So this basically helps to retrieve the video data to play it back on the respective device video player and also. So here this is going to be simple get endpoint video ID and this returns video and video metadata. Again, this might change to streamings, chunks and all that stuff, but this is like rough blueprint layout of how the you know, streaming a video endpoint looks like. That's how it's going to look like, and I think mostly this should be decent enough, good enough at least for uploading and streaming, and that's even in our core required functionalities is what we have listed down. So fine. So now that we have, let's try to get into our high level designs and try to understand. So fine. So this is high level design. So here, before even trying to pick one point at a time from functional requirements, let's try to understand a few keywords or jargon. So basically the fundamental information that we need to know about a video storage and streaming whenever we try to deal with our systems. So here the fundamentals. So first things that we need to understand is the video codec. So here basically what does this represent is basically it really helps us, you know, the algorithms which helps us in compressing and decompressing, so that it is more efficient for our storage and transmission whenever it is. So basically this really helps. Basically codec is nothing but the encoder and decoder. They helps us to reduce the size of the video while ensuring the quality remains the same. So again, this basically this encoder and decoder, mostly the algorithms trade off on this points like, you know, time required to compress a specific file and able to support on different platforms, like compression efficiency, like, you know, how much the original file is reduced in size when compared to the compressed file, and also the compression quality. So basically if you see in either in Mac or Windows, you'll see whenever you try to encode or decode, so H.264, H.265, HEVC, VP9, EV1, MP, EG2, MP, MPEG4 and all those are like, you know, algorithms for encoding and decoding. So that's the at least we should have a basic decent functional understanding of what does codec, encoding or decoding mean. And the second is basically the video container. So here is basically this is specific file format that's really stores video data. So here I'm talking about the manifest files, frames or audio and metadata. So it also might have information about video transcripts as well. So so it basically helps us to, you know, dictate files format of for how the video is stored, and so that's like, you know, video container. So what at all it might contain, manifest files, frames and audio, which I just mentioned, transcripts as well of those things. So if we talk about video container, so it means that. And the next jargon is bitrate. So here it's the number of bits that are transmitted over a period of time. Typically we see measured in kilobits per second, kbps, or megabits per second, mbps. So it's basically the size and the quality of video. Based on the bitrate, it really affects the quality of the video. So high resolution means it's basically high frame rates that are measured in fps, frames per second, which have like significantly higher bit rates, like PPIs per pixels per inch and all, versus like low resolution videos which have like lower frame rates, and the quality of the video will also be drastically reduced. So that's like that's what it's called, like bit rate. And depending upon the compression and also the kilobits per second and all that thing, it really affects that. And the final thing is basically the manifest files. So here manifest files is basically, these are like text based documents. Basically what really they help is in video streaming. Whenever your user is trying to view particular video, these are the files that will be exclusively used to stream by a video player, so that you don't feel a buffer, or like so that we get in chunks and all. We'll discuss more about this. So there are typically two types of manifest files here as well. So here we have like primary and media files. So primary files is basically what it does. It basically tries to list all available versions of a video, or basically different formats, resolutions, and chunks, and its URLs if we have stored in some S3 or other compatible storages. And basically the primary is like the index that we normally see in our book or whatever we are trying to see, kind of a root file, and points to all media manifest files and such. So each will try to represent different version of a video, resolution, and which would have split into chunks or segments. Each like there might be like few seconds long or so. So this is what like manifest files will be used exclusively by video players to help us to stream, depending upon the network bandwidth and all, which resolution to pick, and make sure there's no buffer and all that stuff. So that's like the term or jargon that we need to know. So now that we have a decent idea what is video codec, video container, bitrate, and manifest files, let's now jump on to the first functional requirement, which is the user should be able to upload videos. So that's like a basic core functionality that we have listed down in our functional requirements. So here it's basically few fundamental things. So when we try to upload a video, any creator tries to upload a video, so there are a few questions that should instantly hit us, like where are we going to store this video metadata. So basically the name, description, and other details, whatever category or whatever we are trying to intake from end users, that's one thing. And then where do we actually store actual video data. So that's like frames, audios, actual bytes, and so and what do we really store for video data. So like those are all the questions that we shoot ourselves when we try to ask a question of like users can upload videos. Now let's try to address one question at a time. So for video metadata, so we have a roughly ballpark figure of like 1 million videos that will be uploaded per day, that we assumed. So that means for here we have 365 days or so we'll have like 365 million records in the database representing videos. So here so we see the scale that we are supposed to handle. So we need to consider which storage can help us and help us scale horizontally or so in that case, like we should think of databases that can be easily horizontally partitioned based on video ID or so, maybe Cassandra or so such things, so where we can easily partition based on video ID and all, because we are not much worried about bulk accessing videos and all, because it's just querying individual videos whichever the user is trying to view it. So that's how like we choose the specific storage and all that stuff. And so now for
storing video data, so we can try to stick to uploading data to our blob storage, like AWS S3 or similar in Azure or GCP, via the pre-signed URL that with multi-part upload that it comes with the default with the major cloud providers, and that really helps us. How do we handle large blobs and those things? So we'll talk about that, but ideally this is at this point, like the system looks something like this. So basic, the client, any mobile device or anything, web or whatever they are trying to interact with, and the standard API gateway load balancer helps us in handling routing, authentication, rate limiting. And here for media upload, we try to get the pre-signed URL, which will might have TTL of 1 hour or so that client can directly upload using that URL to compatible S3 storage. So here we try to upload directly via pre-signed URL to our S3, and this video service will try to store all this video metadata, and whenever this video upload is completed to S3 as well, we try to store this S3 URLs. So this basically this is the rough skeleton. It looks like at least to begin with, and whatever we have just discussed. So now when it comes to now storing video, we need to now step back and think a while. So and see, like what and all we need to store, how do we need to store, and how, if we store, in which way it's going to be better for us when we are trying to stream or so those are the the questions that we should try to try to lean towards. And let's see, try to break down the approaches the way that we can store and all. The first one is basically the storing the raw video directly. So here simple, we don't do any much of the work. So it's basically we don't do any video post processing. So whatever we get the file from the users, we just try to store directly in our S3, and then just don't perform any post processing. That's what we do. But this really doesn't work because the different devices, whoever are using mobiles or laptops or iPads or tablets or whatever it is, so different devices require different video formats to play back that video in that respective video player. And also, so this definitely, it's not something that we can go ahead with, and this is something big no for us. So then what is the other approach? So the other approach is basically storing different video formats. So here what we do, when we get the video and it's fully uploaded to S3, we do some sort of post processing, to ensure that we convert the video into different formats that can be playable on different devices. So what we do basically, when that gets fully uploaded, there will be some S3 event notification so that acknowledges that video has been completed, and then that ideally gives us the video URL to video processing service. So this will try to do some work. Right now I'm trying to keep this as a black box, but we'll elaborate as we go into deep dives. So this basically what it will do, it will try to convert the original video whatever we have into different formats. So now once it converts into different formats, it will store back those each format as a file in S3, and also it will parallelly update the metadata in our video metadata with all the file URLs representing different video formats that we have now try to convert into. So that's the second approach, trying to store different video formats and all. But the challenge here is basically it still ignores storing small segments of a video for streaming later. So it's something if we store the entire video, so there's no way for client to play. So it needs to download a full video and then play that thing. So if assume if it's a big 20 GB 30 GB or a bigger duration video, so it's again going to give bad user experience. So this is something again we cannot go with. So the ultimate approach that we need, and it's going to help us, is basically storing different video formats as segments. So here basically same as that we have dedicated video processing service, but what we do here is basically we try to split them into small segments. So each, like, maybe a few seconds in length or so, like, let's say 1 minute video, we try to split into like a 5 seconds or 10 seconds of segments, and then we convert each that segment, whatever you have, into different formats, like, playable, like 1080 or other the resolution that we need to have, so that it can adjust automatically based on the bandwidth of network. So that's like basically now splitting into segments, and then now trying to store various formats of that each segment. So this way this is better, because it really enables more efficient video streaming. Basically, whenever now user is trying to view a specific video, so just at the beginning we'll try to fetch the few segments, and then as each segment completes, so we try to append the remaining segments and all, so that now it will be quicker, because as it needs to just rely to get the first or second segments, and then not like big chunk of full video or so. So that's why, like, this basically this video processing service, like trying to split into segments and then storing various formats, and then this drastically helps in streaming later whenever user is trying to use it. But this is a black box again, like I said, but we'll try to elaborate as we go into deep dive discussions. But at least this meets our first requirement of able to upload videos and all. Now we are going to store. That's the 3 questions that we try to shoot for ourselves. So now let's go on to the second requirement. So should be able to watch videos. So now in the above discussion, we just discussed about storing videos. Now they should be able to watch. So whenever initially we are trying to watch a video, we assume that it fetches video metadata from video metadata DB that we have, and then now we know we are storing video content in S3. So we'll kind of like we'll have an endpoint to just give metadata, and then that will contain S3 URL, and we'll try to use that to view it in respective client device. But let's see, like, how they can watch. So first thing is, like I mentioned, so download the video file. So basically this approach is just client will download the whole video to play it, and this video will be used to play in their thing. But here this is not a good approach, because like I already specified above, so if enter needs to be downloaded, the user should be waiting for a long time, and also if he requests for full video and in between he loses network, again he has to start all the way from downloading it again whenever network is back. So this is in the first place is not called streaming. So this is not the approach, but it's a new one that at least we can think of whenever we want to watch a video. And here the second approach is basically downloading segments incrementally. So the same thing, so just what we discussed. So here rather than downloading full video, the system, now we know we are storing in segments, can now instead download video segments to properly stream the video what we have. So here by default we'll have user preferences and all that stored in our system, and also like we would ideally know which video format based on that user's device, bandwidth and preferences, and accordingly we'll try to load the first segment for that video in that resolution or so based on his preferences, which should ideally be in few seconds of the segment that we have, and they will be able to watch video quickly. And then in the background now the client would start loading more segments so that it continue playing the video seamlessly. So simple. So from S3 it will try to download segments incrementally as client keeps watching the video. So that's the thing, but the challenge here is basically it becomes more complex and doesn't really consider fluctuating networking constraints or conditions of the particular device the client is trying to view on and all those things. So we are ignoring it straight away. So basically the next approach should be something that we can consider this challenge. So that's the approach. So here we try to stick to adaptive bitrate streaming. So here basically let's try to understand what is adaptive bitrate streaming here. It really relies on, like, whatever the various segments of videos that we have stored in different formats. Like I said, they are particularly stored in the form of manifest files, like the ones that we normally create during upload time. So let's give an example here. The main primary manifest file will look something like this. So here it will have, like, what is the bandwidth and what is the resolution here, 4K, and the codecs used, and then the here the link to the media manifest file and all that thing. So kind of an index, and the actual media manifest will have this the duration. So each clip is 4 seconds. So this will be of this something of this format that ideally it looks like, and here each segment looks like this, something of this thing. So this basically this primary manifest will act as an index, and it will be used by the client to stream segments as network conditions vary. So basically, now let's see the logic that I just try to elaborate. The first thing is basically the client will try to fetch the video metadata from this endpoint, like get video or metadata, which will try to give a URL pointing to the manifest file in S3. So now once that it gets that, it will try to download that manifest file onto this client device. So now the client will choose the format based on the network conditions or user settings, whatever we have stored in preferences. So it tries to retrieve that URL for that segment in its chosen format, whatever it has been stored from that manifest file, and it will download that the first segment of that thing. So then the client will play the segment, and it will in the background parallelly it will begin downloading more segments that needs to be sequentially attached to whatever the video that user is playing. So, and if a client detects that network conditions are slowing down or improving, it will vary the format of the video segments it is downloading as well. So yeah, same thing. If it gets worse, it will attempt to download more compressed or like lower resolution. That's why we see the clarity of the video resolution going down or going up whenever our network speed is high or low. So that's how, like, this adaptive bitrate streaming really helps to achieve the ability to stream a video and render dynamically the resolutions and the formats and segments, and make them feel like it's instantaneous and such that. So basically now we are trying to rely or involve the client itself as a core part of our system design that we have evolved so far. So that's the second core functional requirements. So after that, this is our rough flow. It's a rough skeleton is what it's going to look like. So now that we have this decent idea, let's jump onto the deep dives. So taking again each the functional requirement, non-functional requirement that we have, and let's see how we can break down and evolve more into that. So first thing is, how do we handle processing of video? This is what, like, post video processing, which was like a black box thing that we just named it as video processing service. So now how do we really handle that processing of video to support this adaptive bitrate streaming, whatever we just discussed about, like how do we break into segments and all that stuff. So here let's try to understand here. So basically when video is uploaded in original format, we need to post process it somehow to make it as available as streamable video to various devices and all that thing. So here we need to think in terms of like DAG, or directed acyclic graph, or pipeline, and all those things. So ideally the end output of that can be something like video segment files in different formats like codec, container combinations, something of that sort, stored in some S3 compatible. And then the manifest files, which I was talking about, primary manifest file and several media manifest files that are also stored in S3. Now let's think about like rough flow or field of operations that will look like stepwise, like to in order to generate segments. So here this video processing service, whatever we have, we need to now think of like stepwise order of operations that we need to break down into. First, it might let's try it away. It might be something like we try to split up the original file into segments. We might use something popular ffmpeg tool. So this basically that segments now will be transcoded, that is like converting from one encoding to another and used to generate different video containers. So this transcode converting from one encoding to another each segment, and then we try to process other aspects of that each segment like audio processing, transcript generation, and all that thing. So once they're all done, we'll try to create a manifest files referencing different segments in different video formats, and then we consider like it's everything is done or complete or so. So it might look something like this. So let's say like we have this video splitter. So in parallel different workers, maybe temporal workflows, we have like various activities, and then in a like we have different workflows and all that thing. We have maybe transcoding, multiple workers, audio processing, transcript generation, manifest files, and all those things that I just mentioned. So and then once every parallel steps, that whatever we can make it parallel and then process it, and then we try to converge every worker's work into manifest files, and then finally we try to store it into S3 and mark that video as upload or complete or so. So here, so all this so here basically temporarily, like I said, intermediate steps in each of the activities of temporal or workflows, we try to store that temporary files in S3 bucket, and then video segments and manifest files and all such that in S3. So this way basically we'll have dedicated here this is just the rough representation of how the intense video processing service flows and the workflows or activities might look like. But that this should at least give us decent idea of how this kind of DAG work looks like, and how can we separate expensive computation of transcoding and all those things to different workers and all that stuff. So mostly we try to use the fully orchestrator system, which can really help us handling this building the graph of work that we just normally saw, and assigning worker nodes at the right time and all. So this I would definitely use temporal, because even at work personally have been intensely using this temporal, and I am in love with that because it really helps us meet all the nitty-gritty details that we need whenever we are trying to build a real system out there in production. So here that's how once we consider all of that, so this is how the ultimate video processing service will look like, and this will use this S3 itself storage service. That's the end result of what the all video processing service will be in properly structured folder structure, and also on all that. And also this we'll try to store this all S3 URLs that it's been processed by video processing service as metadata in video metadata DB as well. So this is how we try to at least meet our first non-functional requirement. So how the processing of the video is going to look like to support this adaptive bitrate streaming and all that stuff. So let's jump on to the second the non-functional requirement, which is supporting this resumable uploads. So now we know the videos that we are going to get into a system, they're never going to be small all the time. So it's going to be big ones, depending upon the size, the duration of the video. It can span to multiple hundreds of GBs or like hours of video content. So how we are going to help them track the progress whenever they are in the video upload flow,
or so. So this is very important because even if like 80% is done and network is lost, and if we don't have reasonable feature, so again they'll have to do it all the way from ground up. So this is something we need to take care. So ideally this or handled out of the box by popular S3 compatible services like multi-part upload and all those things, but it's good to know how it's going to work. So here what we will do ideally is we will try to divide that video file into chunks, each with a fingerprint hash. So a chunk would be small as like, let's say like 5 MBs or 10 MBs in size, and now this video metadata whatever we have in this DB or primary DB will have a field something called chunks. So this would be like all the list of the chunk JSON objects, each with a fingerprint and a status and hash field that we have. So now once we have that, this client whatever it is will post a request to our backend to update this video metadata with the list of the all chunks with each status as like first as not uploaded. So now the client will be uploading each chunk to S3. So when the chunk is uploaded to S3, the S3 acknowledges that that part is uploaded, and it returns as the part number and some e tag or whatever it is. That client relays whatever the S3 has acknowledged that response to our backend. So it might be some another endpoint that we might have exposed, like patch /video / that video ID and chunks. So that's that server whatever we have here, in our case like video service, can verify that fingerprint and e tag via the official S3 APIs or whatever SDK that we're using, and then update that matching chunk the status and change that not uploaded to uploaded status. So this way we will try to get the status of each chunk and upload accordingly. So and for complete upload, basically S3 has an object level notification, that is object created complete multi-part upload. So that's like exactly once for full file, like once per object. So that single event can be ideally used for us to like understand like can we trigger this video processing service, all this intense workflows and all that we just discussed. So that event emit is something that we rely on to kick off this downstream processing of this video video processing and all. But the chunk level progress and all whatever I just described, the tracking and all, we completely rely on this the client. So that is something, it's completely client driven. So if the client stops uploading to our S3 for somehow, later we can still resume by fetching this video metadata to see like which uploaded chunks have status not uploaded, only process that, and which have status as uploaded, we'll just skip that. So this way we have this resumable uploads, and we ignore the chunks which we have already in our system. So that's how like we try to support this resumable uploads and leverage the mostly available out of the box functionality like multi-part uploads of it can be AWS and other similar cloud offerings that we have. So that's how we are going to support the resumable uploads. Now let's go on to the third requirement, so which is support large videos, so uploading and streaming. So here let's try to mostly we got it covered, but now we know what and all the core components are part of our system or design that we just drafted in a flow. So let's try to understand. So we have assumed that we have like 1 million videos are uploaded per day, a rough assumption that we have did, and 100 million videos are watched per day. So this we know it's a lot of traffic in numbers, and we need to make sure that each and every component that we have in our system are able to scale either horizontally or so that it can handle all of this bursty traffic or whatever it is. So let's see, like the first core component that I can see is here video service. So we know that this service is basically stateless, and this main responsibility is to to respond to HTTP requests that the client sends for pre-signed URLs or video metadata updates also. So this can easily scale horizontally because we have a load balancer proxying it, so we can just add more instances of that, and that's how we are going to take care of our video service going down and handling this bursty traffic. So this component is somehow handled. So now metadata, let's discuss about this video metadata. Okay, so we know that this is something we have decided to go with Cassandra DB, and it will horizontally scale due to this Cassandra's default functionalities that it comes out with out of the box, like leaderless replication and internal consistent hashing and all. So since we'll be partitioning based on the video ID, so they will be uniformly distributed, but there might be a situation of scenarios of hot videos. So let's say like video is popular, that's like going viral and all, and so that could be some bottleneck. So that's where we need to have dedicated separate instances. So that's in all separate discussion of how do we handle hot videos and all those things. But ideally this is taken care of by partitioning by video IDs, and it can add more nodes as it's having a leaderless replication and all. So that's also taken care in and out. And the other component is basically video processing service. So this can scale to high number of videos, like more number of that we have getting uploaded. We'll try to anyhow we have this temporal or whatever I was just discussing, so we can add in more workers, more nodes, so that it can easily distribute this DAG work that we have across that multiple workers, and this basically handles all this queuing mechanism and all those things. So this basically trying to talk with multiple queues of workers and having like dedicated transcoder worker or like transcription workers and other workers that we normally deal with, like segmentations and all those things in heavy video processing service, like resolutions whatever we have. So that's how this temporal also is going to take care of that such things. And now the other thing is basically S3. So that's the primary storage for our media and all this file segments and all. We all know that really extremely scales well to high traffic and high file volumes. So the only thing is, if bucket lives in a single region, so we need to make sure that we have the automatic replication across availability zones, multiple availability zones in that region. And also if possible make it as multi-region, and add on some external SDN, so that if it's a geographically distributed application. Of course YouTube is geographically distributed, so now that from region which is closer to the user, we'll try to render it from there. So that's how we make sure that they don't feel even the latency, even if it's geographically distributed across the regions. So based on all this analysis and all, we mostly got it covered. The only thing is additionally, like I said, so we need to introduce this CDN. So here we try to cache frequently accessed files, more viral one that I just mentioned. So we know that it's being accessed more, so every time we don't want to query metadata into our Cassandra and get that from S3 and all those things, we'll try to cache at the CDN. So now this client will try to take care of the nearest edge location of that CDN and try to get this video manifest segments and then render it or stream it on respective video player. The same thing for our video metadata as well. We can introduce a cache in front of this Cassandra and make sure that whichever are having higher hit, we try to store that, and then the turnaround time from the DB to client is reduced by introducing this caches. So basically, yep, so to scale, try to take care of each component if you can originally scale or leverage its default replication, and then multiple workers, and then to make it efficient, try to introduce caches between them, and then CDNs at the edge locations and all those things. So that's how we try to meet this scalability for reads that this system kind of comes up with, and hope at least this is what it's going to look like at the end. This is the how it's going to look like. At least I hope I conveyed like at either couple of points or so where you understood in and out. And yeah, that's all I had for this video. Let's catch up in the new one.
Now let's discuss on post search. So the all social media platforms that we use on day-to-day basis, it can be Facebook, X, LinkedIn, Reddit, Insta, or other platforms where it has a poster that the user is going to write to that platform. So that's the like generic the problem, the system, how we can design around that, such that even if the users base for that platform is in billions, user can retrieve particular post in given time bound, maybe like 500 milliseconds or so. So how can we achieve that and solve the problem, and what is it going to be our thought process, and how we are going to navigate through all the challenges that we encounter, is what this video is about. So let's and the post search, so these are mostly kind of like infrastructure related system problems, and sometimes it's restricted for us not to use search engines like Elasticsearch or like Postgres full text or something of that sort. We should try to think from ground principles and try to come up with a solution from scratch. So that's the overall problem statement that we are going to try to see how we are going to think through. So first thing is as functional requirements. So here functional requirements, the user should be able to create and like post. So that's the basic functionality that we should try to provide for this so user should be able to create and like post. That's the first requirement that we should meet when we are designing the system. The second requirement is you should be able to search posts by keyword. So at least let's say like startup or build. So once he searches with that keyword, whatever the keyword that matches in our system, we should try to retrieve and showcase it to the user in their timeline. So that's the like second requirement, should be able to search by keyword and then give the results for them. The third requirement is he should be able to get the search results, whatever he has searched for, able to filter by either by recency or like count. So whichever has more like counts, that should pop up first and then followed by the less counts, or else the time based, the whichever is recent one, that should be showcased first. So we should provide an option for user to filter it by these two options, recency or like count. So these are the like at least minimalistic functional requirements that we should keep in mind to meet when we are trying to design a system for this post search. So there can be other functional requirements that we can discuss, but that's going to make it more discussion point for this video, or kind of like not just a keyword search. It can be like fuzzy search, meaning the semantic meanings also should be retrieved and showcased to the users. And also we can go for further for personalization, like if I ask for build, so it should as of now it's going to be the same result for me as well as for others who are going to search with that keyword. If personalization is involved, so the results for me and the other person is going to be different based on how I interact with the platform and all that stuff, and search history and all those things. So like this we can even discuss on like images and media and real-time updates, like whenever user tries to create a post, and then should that appear instantly in the search results, or even or is eventual consistency is okay or not. So those are like additional functional requirements that we can keep in mind, but it's not mandatory that we need to get it done through this system design that we're going to discuss now. So these are the minimal functional requirements that we should try to meet. And next is the non-functional requirements. So non-functional requirements is basically these are very important, since this is infrastructure related the problem. So the more emphasis or more focus should be on to meet this all the points that we have. So of course, the first point is fast, and queries meaning the results that user asks for should be retrieved in less than 500 milliseconds. So it should be super duper fast, so that user doesn't get frustrated whenever he's trying to look for a particular post in our platform. And the second requirement is handle high volume of request. So basically, no matter how many search requests that we get, we should be able to support that, and our system should not struggle to retrieve search results for respective queries that user is asking. And the new post, so whatever the new post that users are creating every second or minute, it's not necessary that we provide those posts in the search result instantly. So it's okay to with a delay of like, let's say less than 1 minute, so eventual consistency is acceptable. So that's the one of the requirements which really makes us easier for us to design system better and more reliable. And then all posts must be available, meaning it should be discoverable, including even oldest ones or unpopular ones, not just keeping the popular ones in our system. So whatever the posts are created in our platform, all those should be discoverable and available to the users whenever they're trying to search for. And the final point is optimizing storage. So whatever the post that we are going to store, we should try to optimize such that the storage requirements for us to maintain should be optimized in such a way that we don't just blindly use excessive storage, and indirectly it's going to cost us more money and higher maintenance cost on that stuff. So these are basic functional and non-functional requirements that we should try to meet when we are trying to design the post search related system design. So now I think we have at least functional non-functional requirements clear. So let's try to estimate at least the scale estimations. So assuming so let's take at least nowadays all the platforms of major popular ones like Facebook, Insta, X, or Reddit, or whatever. So rough ballpark figure I assume. So assumptions is very important to estimate the scales. So roughly I assume we have 1 billion users. So this is since we are trying to deal with large scale systems, so that's why I'm trying to assume the higher number. So 1 billion users. So let's try to look given for the 1 billion users. So for write volumes, what is the how many posts are going to get created per second, or how many likes are getting created per second? Let's try to estimate. So post created, so assume we have 1 billion users and 1 post per day per each user. So every user is trying to create 1 post per day. That's the number that we have just roughly estimating. And in a day we have 86,400 seconds, so roughly rounding it up to 100k seconds just for easier calculation. So it is going to be around 10k posts per second that our system should be able to handle. So that's the number that we should keep in mind while we are trying to design the system. Next is the likes created. So let's just take 10 times of the posts created. So this is not just this is easier, just liking the post whatever users are creating. So assuming 10 likes that user is going to make per day, and 1 billion in 100k seconds, so it's going to be just the 10 times of the post per second, which is 100k likes per second. So that's the writes volume that we should try to handle in our system. So now read volume, so searches. So let's say just I'm trying to be as simple as possible. So 1 billion users is doing one search per day, so 100k seconds, so it's going to be 10k searches. So yeah, that's the read volume that we need to handle from our system. So that's the write volume estimates and read volume estimates. And storage estimates, let's do assuming let's say that the platforms are well established and they are quite popular, so meaning so they should be they might be at least a decade long or so. So let's take 1 decade old system, so that is 10-year old. So post searchable is, so we have one user making one post, so 1 billion users daily active users for our platform, so 1 billion posts per day, so 365 days are in year, and then for 10 years, so roughly calculating, so it's going to be 3.6 trillion posts that we need to handle. So the size is of each post, I'm considering 1 kilobytes per post is the size. So overall storage that we need is 3.6 petabytes. So this is the amount of storage at least we need to support all the posts that are coming into our system. So these are like just rough ballpark figure and rough estimates, so that it gives us decent idea or rough idea when we are trying to discuss the non-functional requirements or deep diving into particular discussion point. So we will know like these are the traffic that we need to handle and support, and gives us decent approach to separate which service and all that stuff. So that's the rough the scale estimations. So now after that is core entities, and I think core entities should be simple and straightforward, because it's a very straightforward as it's an infrastructure related problem. So first core entity is the user. So here this is the entity which creates posts, basically the users that are going to interact with our platform. The other entity is post, so that's the thing we are trying to search. So it might have the content and created by a user, and maybe it might even have the like count and so. And the third entity is like. So likes are created when user likes a post. So mostly we are worried about the count of the likes instead of like all the attributes of a like. So that's the core entities that are involved in the system as of now, and we just try to keep it as simple as possible. And after this we are going to discuss about the next thing, which is the contracts or API or system interface that we need to have to provide to the users to consume, or to our whoever the other team that are developing in our organization also. So first thing is the search endpoint, straightforward. So it's going to be simple get endpoint search and query parameters. So it can be any keyword, so it can be startup, build, or any other keyword that user can set for this query param. And the other is a sort order, like we said, so it can be based on the recency or the like count. So these are like two query params that we initially try to support, and this is a simple endpoint which will be consumed for reading or retrieving the relevant post. The other related endpoints are the write endpoints. One is to create a post. I'll just try to keep it as simple as possible, just the endpoint route and not specific body and all that stuff. So and the other thing is liking a post of a particular post, so which is the post ID and the like endpoint. So these are the three endpoints that I can think of straight away: searching endpoint, and then creating a post endpoint, and liking a post endpoint. So these are the three things that we need to try to expose and provide once we try to design the system. Now let's jump on to the high level design, picking up one functional point as a discussion, and see how we can come up with a rough basic flow and then elaborate from there. So the first point is basically should be able to create and like post. So that's the first point that we have listed down in our functional requirements. So this should be simple, and basically we just need to accept the call and write them to our database. So assuming we are a part of, ours is just one service, part of the bigger product where other teams are handling the other services and all that stuff. So I assume that we have already solid established post service and like service. So this is kind of like a black box for me, so we are not going to discuss this, because since our discussion point is more on search related stuff. So there is assuming there's already a post service and like service, so which post service is responsible for creating a post, and like service is responsible for taking client request and creating likes, whatever the user is trying to like. And that load balancer is what is going to distribute to our service. And we have the ingestion service. So so ingestion service, and this is going to write to our database, so which I'm just index database or whatever. So post a table and it has content and likes. So just the rough flow, assuming this there are already black box services that are available developed by other teams, and this is how it's going to be a rough, at least a flow. Ingestion service is going to pick them up and store it into our database. That's the simple discussion point, so I'm not going to discuss or elaborate much more here. And the next discussion point is should be able to search posts by keyword. So this is our problem. So we need to allow users to search. So for this we will try to introduce a simple here to handle authentications, rate limiting, and urgently scaled search service. We'll try to introduce API gateway and a simple client, and this is the whatever the search request, the get request, whatever we have will hit this API gateway, and this routes to our search service. And the search service will try to query our index database where ingestion service has written to, and then we try to retrieve and then provide the results to the users. So this is a simple, at least the rough flow. But now the challenges. So here if you observe, the index is doing quite a lot of work, meaning so we are trying to allow users to search by keyword. So we need to find all the posts which contain that keyword. So if I ask for build, so I need to filter all the posts which contain the build. So the amount of the posts that we will be having in our database, it's going to be in magnitude of trillions. So this is not a small query that it needs to process. So what are our options? So that's the challenge that we need to discuss. So let's see what are our approaches. So the naive solution that we can straight away think of is basically just straight away queries like select star from post, like, and more that keyword filter that we have. So like keyword we search for, and then this would ideally give us the results. But this is very very slow, terribly slow, because our database, whatever the index database that we have, is needs to look at every post and try to see if it's containing that keyword at query time. So database systems are fast when data is organized to match the request that are coming in without an index. So now but here we're trying to filter it at query time. So this is something very slow, and it's not going to meet our 500 milliseconds time constraint that we have. So that's the one of the problem, that we cannot go with this unindexed database. So other approach that we can think of is creating an inverted index. So so the idea behind this inverted index is basically we create a kind of like dictionary like, which maps in a keyword. So keywords here it can be build, a startup, or other keywords that we have. So and this will be mapped to the list of the post IDs that this keyword is part of or is containing in. So this way what we can do is, when it comes to search, we simply grab the key associated with that keyword present in that values list, and return the associated post. So that's how we are going to do it. So far so good. So to keep things simple and faster, let's assume that we use Redis for this. So Redis will try to keep this inverted indexes, which is the keyword, and it is storing all the list of the post IDs which that keyword is part of, and whenever so basically we're trying to store it memory, and query will be blazingly fast. So of course there are durability concerns, and what's the TTL for that, and can we use other memory DB or other stuff so to make it more durable. But as of now, this is the rough intuition or idea we can think of instantly, to make it bit faster of creating in inverted index and see. So here the how do we so how are we going to populate this index? So this should be done when posts are created. So basically when posts are created, we need to try to break them apart inside the ingestion service. So here that's the thing where we need to do all of this work. So kind of what we call is tokenizations, like trying to split by keyword that could possibly match, and then append the post ID. So whatever if let's say one post is coming and it has a keyword build, so when we did tokenization, so then that that ID should be appended to this list of the this keyword that we have in our index already. If not, we need to just create a new one. So this but the challenge here is basically the posts are going to the list of the post IDs are going to get very very large, so especially for common keywords. So we'll have to address this very very carefully, and we'll discuss this eventually. And also we need to write to many keys, so meaning one post can have multiple keywords, so that is going to be part of the multiple keywords. The ID that we need to append should be appended to multiple keywords. So that's also for every post it might have roughly around let's say 10 to 10,000 keywords. So we need to handle all of those things, and that also throws us some scaling challenges that we can think of with this approach. So this is at least this gives us better approach, but though we have challenges, and this outweighs the first one, so we can try to think and go with this approach for our this thing. So the next the point that we will try to discuss is should be able to search results by recency or like count. So that's the filtering that we need to try to provide for the users. So that's the last requirement that we have in our functional requirements. So yeah, so how what are the approaches? So first option is the request time sorting. So here this is the most naive solution that we can think of. Is basically I try to grab all the post IDs for a given keyword and look up the timestamp which is one of the attribute in that post model that we have, or a like count, and then sort those in memory using any sorting algorithms based on that thing. So that's the simple thing I can think of, and this is very very naive. And and also let's assume we are sorting by recency. One example is we are first going to make a request to our index. So here for a given keyword, and then it will that keyword gives us the list of all the post IDs that it has, and then for each of the post ID that we have, we'll try to query this post service for the created timestamp. So once we retrieve all those timestamps for each of the post ID, then we will try to sort this post in the search service and return to the user. This is of course not at all great, because all we are doing is in memory, and this is going to add a lot of latency, and it's not going to meet our 500 less than 500 milliseconds latency that we are supposed to meet. Not feasible for us. So what is the other approach is multiple indexes. So that is the other approach that we can think of. So here is basically the idea is to have two separate indexes. So one sorted by creation time and another is sorted by like count. So we can refer to that as maybe creation index, and the other is likes index. So using our since we are storing it in our Redis thing, so we can have separate keys depending on whether we are sorting by likes or the creation date or so. So for the creation index keys, we can use a standard Redis list. So we are always going to be appending whatever the post IDs that we are going to get, and we just append to that list, and our queries will only take from the last elements that keyword has. So the file likes index, each key can use a Redis sorted set instead of blind list. So this sorted set allows us to keep a list of items ordered by the score, meaning here score is nothing but the likes count for that post. So like the way the priority queue or sorted list works. So with the same time complexity of insertions and queries, we can give the results, either it can be likes based on likes count or the creation date. So maintaining this multiple keywords, it really helps us to give the results in a more better and faster way. So when a new post is created, we'll add it to the both the indexes, that is in a creation index and then the likes index for every keyword it contains. So when a like event happens, we'll update the score in our likes sorted set that we have. So this is the how it's we are going to make a little bit faster with multiple indexes. So the challenge here is basically it's just the amount of the storage, because now we are trying to store in separate keywords for based on creation date and likes count. We are just doubling the amount of storage required for our indexes here. This is valid trade-off given the time constraint that we should meet. This is very negligible when it comes to the outcome that we're getting out of this approach. So these are roughly the rough laws for all our functional requirements. Now it's let's try to take one non-functional requirement point at a time and try to discuss more on it, kind of like deep dives, and that's the core discussion that we need to do, since it's the infrastructure related questions. So now first thing is, how do we handle high volume of requests? So here our in-memory reverse index based system is quite fast, and that's fine, but we are going to be handling a lot of traffic. So here so we do one thing is which is quite a relief for us, is we don't have personalization, and we have up to 1 minute eventual consistency for new post to appear in our search results. So given those two requirements are not in our discussion, so caching is something, one of the tool that we can think of. So anytime we can tolerate stale data and we have duplicate request, we can think of straight away caching is something appropriate for us. So this is more of like scaling reads. So since writes are going to be negligible when compared to the readings, that is search requests, so this is the more of a like scaling reads that we need to think of. So the first approach that we can think of is basically using a distributed cache alongside our search service. So what is this is basically we'll try to add a distributed cache alongside the search service. So here search cache it is going to be again Redis cluster, so that's by default it's going to handle distributed cache. So this would be responsible for storing the most recent results for given search query. So when a search is performed, the search service would first check the cache to see if the results are available. If they are, the search would return results from this cache to the client or the user. If they are not, this would perform full search by querying this index and store the results in our cache for future requests and return back to the client. So here for the cache, the eviction policy can be up to 1 minute on a new post and or less than 1 minute on our cache or whatever. So this will guarantee basically we are never serving results that might not contain newly created post. So that's the thing we can at least think of. The simple way is using cache that we can attach to our search service. The other approach is basically quite better than what we discussed, using a CDN to cache at the edge. So this approach is basically in addition to Redis search the cache that we have. So basically it's a complementary to the previous approach that we discussed. We can also utilize edge caching, which is via the CDN. So it can be either Cloudflare or AWS CloudFront. So most CDNs that we have that out of the this clouds that provide to us, they operate kind of like big set of geographically spread HTTP caches. So we can configure an origin or target for the cache and configure DNS to route through that CDN. So if the cache has an item the user is looking for, it can return it faster than any other alternate option. So we already know that most CDNs have a locations very close to most users. So if it doesn't hit the cache, the CDN will proxy request back to our servers through API gateway, and it will handle the normal way that we normally have. So here using CDN is quite simple. So on the response to our search endpoint, we can add a cache control header, so cache control headers, which tell our CDN when and for how long to cache a result. So when a user tries to hit our search service again with the same keyword, they will first go through geographically local CDN host that we have. So in this case of a cache hit, this user will get the results in maybe like tens of milliseconds versus like 100 milliseconds or less than 500 milliseconds, which is quite faster. So if we introduce this additional edge CDN, that if we have to make it quite faster rather than going through this the search service and all that thing. So this is how we always need to think through to make it quite fast our system, and how can we handle the latency requirements and also the scale that we need to think of. So that's how we are going to handle this first requirements, handling high volumes of requests. So now the second requirement is handling multiple keyword and phrase queries. So here the trickiest part, so till now is we were assuming user is always going to search with one keyword like build a startup. But what if users tries to search for more than a single word? Of course that's how it's always going to be. So it can be a string of multiple words or full sentences and all that thing. So how how do we come up or think through? So assuming at least not full sentence, let's say assume multiple words. So the approach is basically, first thing is we can think of is intersection and filter. So here what we do is simple. So assume the word is Silicon Valley. Okay, so here we know that we'll try to split that by Silicon and Valley, and then do a regular processing of searching by this Silicon and then this Valley, and whatever the results that we get for Silicon and Valley, we'll try to get the common results of both the search results that we have, the common post IDs, and then take them and then try to showcase it to the user. So that's the approach that we are going to do. So intersect them, find all the post IDs which are common in both the search things, and grab the post contents for each of these post IDs by looking up through post service, and ensure they contain these both words, and not a disconnected string, like we should make sure that they are side by side. So not like sparsed or spread across in a sentence, and then return the post to that. So this is like kind of like 3 to 4 steps process that we have. But the challenges here is basically the post ID set that we get may be very large, which really makes it prohibitive to pass over the network and to intersect and all. If there are millions of posts for each keyword, we could be transferring megabytes of data, which need to be put into hash table and intersected. So this is quite harder to do it in less than 500 milliseconds that we have. So that's why this approach is something is not feasible for us. Then the other approach is bigrams or shingles. So here this is kind of like approach that really helps us to meet our requirements. So assume the sentence is something like I want to build a product. So we can try to improve this read time efficiency by indexing bigrams or shingles. So here it is simple. With this sentence we can create a tokens for each pair of words. So here I want and want to and to build a and a product. So here we'll try to create a tokens for each pair of words, and then these can be inserted into our likes and creation indexes that we have in our Redis thing. So when we want to search for let's say I want or build a instead of grabbing build a or I want, we can go straight to that the tokens that we were trying to store as a keyword, and whatever that has all the list of the post IDs, we grab them and then look for the content of that post and give them. So this is how trying to store by pair of tokens coupled together as a keyword in our Redis, and then do a straight lookup rather than intersecting by each keyword and getting the common of them and showcasing it to the user. So this significantly increases the sizes of the indexes, because now we are trying to store a pair of tokens and all, but it's negligible comparing to the latency that we are trying to meet. So this is something that we should try to go with given the time constraint that we have. So that's the second point, that's how we are going to meet. So how we can handle multi keyword or multi phrase queries that we have. So now the third discussion point is, how do we address large volume of writes? So the write volume for our system is quite high. So we have two sources of writes, which is creating a post and then the likes on this post. So let's try to talk on them separately. So the first discussion point is the post creation. So when a post is created, we call the ingestion service, so which was in our initial diagram flow, and which tokenizes the post, that is breaks it into keywords, and then writes the post ID to the creation and likes indexes that we have. So if a post has 100 words, we might trigger 100 plus writes for each word to our indexes. So if a lot of posts are created simultaneously, so at a time, so our ingestion service might get really overwhelmed and it might break down. So in the worst case, we might lose posts or events. So how do we address such heavy traffic? So we can address this by adding more capacity to our ingestion service, so and partitioning the incoming requests. So by using here the logger or stream like Kafka, we can fan out the creation request to multiple the ingestion services instances that we have, and partition load. And we can also buffer requests so that we can handle bursts of post creations. So basically we can flush the batch of the post request to the multiple instances of ingestion service, and that's how we can think of to handle heavy traffic. So and also finally we can scale out our indexes basically by sharding the indexes by keyword. This way the rights to indexes are spread across many Redis instances. So that's how we can think of by introducing event writers, Kafka logs or stream, and then this tries to fan out to multiple instances of ingestion service that we have. And even if this index is heavily loaded, we can think of sharding and by keywords, and then try to spread the load in that way. So this way we have quite a system that can handle a load of any kind. So that's for post creation that we were talking about so far. So this is more of like scaling, right? So now the like event. So for the like event, we partly handle the ingestion of a new post, that is but now our need to index like counts is still something that we need to discuss. So with the existing system that we discussed above, we need to make many writes to our indexes every time a like happens. So we know that like happens more frequently than the post creation. So here we need to think of can we batch the like counts, or can we do in the power of 2 or so that we don't do more often writes than we are supposed to. So this is opportunity. How can we reduce number of writes that we need to do to our indexes? So that's the thought process, or the question that we need to trigger ourselves, and then think towards that question. So first is batch likes before writing to the database. So that's what. So here what we do is batching likes. So the approach is simple. What we take is we can take a batch. So here the Kafka that we have, I can flush maybe every 30 seconds or so, and then instead of writing like every update to our indexes for a given post ID, I can batch it for over a period of like 30 seconds, and then instead of writing 500 writes to our indexes for a viral post or so, we can make one update with an increment of 500. So that's how one writes instead of 500 writes. So this like batcher really helps us to reduce the number of writes to our indexes that we have. So to do this, we will need a secondary batcher service which accepts events and aggregates them over a fixed window, and before maybe 30 seconds, and before writing them back to Kafka to be consumed by the ingestion the service. So this is something flushing over a period of 30 seconds for a given post ID, and make sure that we do bulk update for that particular post likes count and so. that's how we are going to reduce the writes count. So now the challenges with this is basically we it definitely improves on like volume for most viral posts, but it won't reduce the volume of writes overall, since most posts aren't viral. If a post receives even one like per minute uniformly over a day, even though it receives for that day, so like maybe 1500 likes over that day, we don't get any benefit from that batch, since we still have to write one like per minute, because our buffer period is 30 seconds. So same so it's still going to be the same what used to be without this approach. So to even meet that, the second approach that we can think of is this two-stage architecture. So this approach is basically updating the like count into our indexes when it passes specific milestones, that is in the powers of 2 or 10. So we would write to the index when the post has let's say 1 like or 2 likes, 4 likes, or it can be in the power of 10. So this basically reduces number of writes exponentially. So we no longer have to make 1000 writes for 1000 likes, we only have to make 10. But here we have a trade-off. This would mean our index is basically stale. So even let's say even it has ideally in our system one 999 likes or so, which is not in the power of 2 or 10, we are still showcasing it to the user in the power of that. So user is going to see a stale like count or so for a particular period of a time till we hit that power number. So that's the trade-off that we are making, but that's quite acceptable given the amount of the traffic and the writes that we need to do. So in this case cannot be completely trusted, the data that we are trying to showcase, but the ordering is approximately correct. So the basically whenever user is trying to retrieve the post by likes count, the post definitely with 10k will be in front of the post with 1k or 10k 1 or 1k or 1 like. So if we want to retrieve n post for given query, we almost every time we should try to grab the 2 times of n post from the like index for each post in that list, so that we don't miss this ordering of the post by like count. So for up to date like count, then we sort using the that fresh like count before returning to the user. So in this case our storage is an just rough approximation, but our end result is going to be quite precise of what we have. So this is a kind of the two-stage architecture that we are trying to do, and meet both the writes thing and also the retrievals to the users. So the challenge here is basically this is quite complex when it comes to engineering effort, and it needs more thinking and efforts to implement, and yeah, and are also quite complex to manage and maintain as well. But given the complexity that we need to handle, so this is the way that we need to think through and proceed with this approach. So the next discussion point is, how do we optimize storage of our system? So that's the next discussion point. So this system is indexing an impressive amount of data, but our users are mostly interested in very small portion of the post or so. So how can we optimize the storage? So we can put a caps on or limits on our inverted indexes. So we probably won't need all whatever 10 million posts or 100 million posts with the build content somewhere in their contents. By keeping our indexes to let's say limit of 1k to 10k items, we can reduce the necessary storage by orders of magnitude. So it just keeps the posts that are mostly that's what users needed. So and also most keywords, they are often they're seldom searched, meaning they are not even searched at all. So based on our search analytics, we can run a bad job to move rarely used keywords to less frequently accessed but ultimately cheaper storage. It can be S3 or auto cold blob storage that we have. So on a regular basis, we'll determine which keywords were rarely or not at all accessed in the past month. We'll move those indexes from our in-memory Redis instances to our blob in our blob storage. So when the index needs to be queried, we first try to query Redis, and if we don't get our keyword there, we can query the from our blob storage with a small latency penalty, and that's fine because the storage that we're going to save and the cost for our in-memory Redis is quite high, and then trade-off for latency penalty for less frequently accessed keyword is acceptable. So that's how we are going to think to reduce the storage or optimize the storage. So finally, our full system design is something it's going to look in this way. So we have so the post service and like service responsible for creating a post and creating a likes, and load balancer tries to event writer to Kafka, and then this fans out to ingestion service, and then we have a likes batcher in the order of magnitude of 2 or 10, and then ingestion service it's going to update the likes count eventually, and all those things. And here we have our CDN cache and then search cache and all those things. So and then ingestion service for cold indexes, blob storage for less access keywords and all. So this is how it's going to look like at a high level, and this I know this is very minimal discussion and of course this very high level. This video is intended for just rough idea and rough approach and the direction that we need to think through, and how can we navigate through the problems and see the way forward. And also hope you got the gist of at least how can we think of this post search related system when we are trying to design.